logging in again. I don't know if you can see me or not. Just a second. Let's put this.
질문 누가 읽을 거예요? 오늘? 이준혁 교수한테 질문을 받아서 이걸로 해주세요. 이걸로 해주세요. 괜찮죠?
아 온라인이요?
예.
아 네네 알겠습니다. 네.
그걸로 해야지 않아요?
네, 온라인 질문을 받고 이거는 아마 오프라인 말씀하시는 거죠.
Recording in progress.
So I have to make sure that my audio is correct. Let me see. That's precisely the tricky part.
Yes, yes.
Yeah. So let me see, how would I share my stuff?
I guess you got the host, right?
So you are seeing my screen now?
Yes, yes.
Okay, so then the question is, do you hear an echo?
I don't think we hear an echo. Yeah, no.
Okay, good, because I hear an echo. I hope you don't.
Yeah, it's okay so far.
Okay, so then do you see my other picture or not? I have now two Zooms opened up.
Sorry?
Okay, now you see me. I have two Zooms.
Yeah, you have, yeah. Yeah. Yeah, we see your blackboard and your face at the corner. Yeah, good.
So you see me. Okay, good.
Is it iPad or laptop?
It's iPad.
iPad. Then you can by finger you can slide the. Can you see the some small video screen on the right and on the bottom of the right? Yeah, you
This
can
one, you
slide
mean?
and then
Yeah.
you can just slide outside of the screen. Then it will be removed.
Oh, I messed it up. Sorry. What did I just do?
Probably you can also click the minus this on the screen on the video. Yeah, okay. Then, probably you have to slide this.
What happens? Each time I do that, it comes back. Okay.
Yeah.
Share device audio off.
Well, why don't I mean? What's wrong with having this here?
If you're okay, I mean, if you're okay, we're fine, I think.
No, I know. I'm saying from the viewpoint of your students, would they not want to see the speaker?
We see your face. I mean, we also have, we see your face at the upper corner.
Oh, so let's see. Maybe you're saying there's another way to get rid of this.
Sure.
I mean, I can move it around, but not. I cannot get it out.
Yeah.
Oh, it's
no.
not-
Yeah. That's the way. Yeah.
Okay, good. Okay, great. So now I think So you have also there's another screen where you're using this other one.
Sorry, say again, please.
Yes. We can see your face too.
Yes.
Okay, great. Now, is there a way I could see the student's face?
Can you use this? Maybe can you use? We'll try that. We'll try that. There is a camera on the lecture hall, so yeah. Yeah. So Kumnon, how are you doing?
Very good. How about you guys?
Yeah, we are good. We are good. We are in the middle of the school, and so far things are quite smooth.
Great. I'm glad to hear that. I hope that there's no COVID issue or anything like that?
There are one or two new cases in the school, but I mean, I think we are relatively okay. Yeah.
Are people have to wear masks there?
Yeah, we do. Yeah.
Is that because of your school or in general in Korea?
I mean, wearing mask is mandatory indoors so far.
Oh, I see. Okay.
Yeah.
카메라는 작동을 하는 것 같은데요.
네.
시그널이 연결 들어오게끔 지금 설정이 안 돼 있어서 좀 알아보신다고. 지금 출시가 아마 안 될 것 같은데요. 전화는
뭐가 안 돼서 설정이 안 돼서.
카메라로 어떻게 요 뒤에서는 할 수 있는데 뭐 의미가 별로 없을 것 같아요.
카메라 전화하는 게 안 된다고?
그러니까
이게 저쪽에 연결이 안 되면
예, 아직 안 시켜놨다고. 예, 그러니까 뭐 기계 장치가 뭐 많더라고요.
So Kumnon, there is a camera which in principle can screen all the audiences. But since this is the first online session that we are having, I think it's not yet connected to the computer, and the staff is, looking after how to connect that. So probably
okay.
the first lecture you might not be able to see the audiences.
Okay,
But
but so therefore you guys will tell me if there are questions and so on in the
Yes,
audience.
yes. So yeah, yeah. So if there's a question in the audience in the lecture hall, we are going to hand them a wireless mic so they can speak out, so you can hear them. But I mean,
Yes, but somebody that should stop me when somebody asks me.
yes,
questions.
yeah, yeah. So I think if anybody raises hands to ask questions, I'm going to stop you then. I mean, pointing out
Okay,
that
good.
there's a
Excellent.
question.
Excellent. Okay, so it seems like it's
Yeah. Hopefully from tomorrow there will be a camera so that you can see the audiences.
perfect.
Ah.
별로 안 좋으면은 노트북으로 어떻게 한다고요? 요즘 이거 핸드폰으로 되더라고요. 한번 시도해보고.
no, most of the guys are not there. So you can see, Kumla, you can see
I can see what?
Me.
I can see a screen. Somebody standing there. That's all I see.
It's me. It's Kim Young's personal broadcasting. Yeah, but this
Oh,
will,
I can see that. You mean?
yeah, two of us.
Let me see. How would I go and see? Oh, view options. No, that's not where would I go to see? I don't see the options for panels. Let's see. Oh yeah, side by side.
Yeah, but I think
Oh,
this
yeah,
will.
now I
I think
see.
this will not work. I think this will not.
Oh no, it's working actually.
It's
Let
working?
me just, you mean I go like this?
Also,
Let's see.
keep the computer in a good angle so you can see the audience. That will be okay.
Let me just see if I can pin it. Yeah, I'm seeing the. Yeah, that's good. If you rotate it, that'll be good. Yeah, good. Now I can see that there are not many people yet.
Not many.
Okay, good. Yeah, so if you can rotate that, that'll be great. Yeah, like that. Hi, Kim Young. How are you?
we turned off all the microphone from the Zoom. So
Hi, Kumla.
Hello, how are you doing? Nice to see you.
I assume the students are eating breakfast outside.
Yeah,
right?
yeah,
It's-
but in 5 minutes they will come, so just wait.
I can even take a computer out and see who are they outside.
어떻게 할까요? 쉐어하실 때, 쉐어하실 때 이 유선 마이크 그냥 같이 쓰세요. 괜찮죠? 옆에서.
언제 채워요? 지금 채워요, 제가?
아 이거 조금 주의사항만 내가 말한 다음에 그러니까 그다 말해주세요 그냥.
네.
올라가서 본 사람들은
네.
다 뮤트가 돼 있으니까 질문하고 싶으면 손을 들면 뮤트를 풀어줄 거고 아니면 텍스트를 치면 질문 읽어줄 거고.
오케이.
홀에 있는 사람들은 질문을 따고 손을 들면 유선 마이크 덮어줄 거고. 그 두 개만 하고 딱 해주세요. 마이크 두 개 같이 쓰고 얘는 누구한테 줄 거야. 질문을 전달해줄까.
저뭐 하라고 하셨는데 지금 제가 와이파이가
이거 누구한테 넣어줘야지?
하셔야 될 것 같아요. So Kunal, we'll start in 2 minutes. It's okay?
It's perfectly good.
Yeah.
How many students are there?
At this moment, 2 or 3, but they will come. So
No,
how
no,
many
I meant,
participants?
yeah, I see the students now. I meant how many students are there in their school?
50?
50.
How many students or how many audiences in the school? 100 audiences. Yeah. In
Oh,
total,
wow.
yeah.
Okay.
Including professors and doctors.
Now, this is Saturday there, right?
Sorry?
Saturday.
Yeah,
You're
Saturday.
having
yeah.
the lectures
right,
also
right.
on Saturday.
Yeah. It's Friday on your time.
Yes, Friday evening, but
Yeah.
Saturday morning people come there to lecture. That's impressive.
Yeah. The building is empty, but only this hall is full.
And Sunday too.
Yeah, tomorrow. It's quite tough schedule. Yeah, for whole 10 days, we'll have almost 3 or 4 lectures per day.
Wow.
Okay, hello everyone. So let's just start today's program. So before starting, I have some announcement about the questions from the audience. So if you want to ask a question, please raise your hand. Then we'll give you a mic for the question. And if you can also write your question in the chat, then some of the organizers will read it for you. Okay. Okay, we are very happy to have Professor Kumnun Bafar from Harvard. So he will give 3 lectures about quantum gravity landscape and the swampland. So today is the first lecture, so please.
Thank you. Thanks for inviting me to give lectures in the Kavli Asian Winter School. I was very much hoping I could be there physically, but unfortunately, my plans didn't allow me to be there. So I apologize, and it's unfortunately this is the second best thing I could do, namely through the Zoom. Even though we are all tired of Zoom, I'm sorry. I know that feeling very well. So I've tried to make it as interactive as possible by making it look like a blackboard and so forth. And moreover, I would very much appreciate if you guys ask me questions during the lectures, and it's supposed to be really informal. So just feel free to raise your hands, and somebody over there of the organizers will stop me, and then we can answer questions in real time. You know, you don't have to wait for the lecture to be finished. Before I start, can you hear me well, everybody?
Yes, we can hear you well, but
Yes. Okay. Okay. Good. So the topic I'm going to talk about, the title is the quantum gravity landscape and the swampland. So quantum field theories are very well understood. So we know what a good quantum field theory is, and by now we have a lot of techniques to study them. Moreover, we know how to understand even some non-pertuitive aspects of them. So we are really very detailed knowledge about them. We also know about specific classes of them, conformal field theories or asymptotic field theories. So these are theories which make sense at shortest possible distance as well. So in other words, even as energy goes to as energy goes to infinity, then the distance scale goes to 0, the coupling either is constant or it goes to 0. So these are theories which are under control from the quantum field theory perspective. Now, we want to contrast that with quantum gravity. In quantum gravity, if you consider, for example, the gravitational attraction between particles, you can ask what is the strength of the interaction? And you find that the strength of the interaction is proportional to the energy. And in a dimensionless way, you will have an effective parameter which G, you can view the G as going like the energy involved, divided by m Planck. So therefore, as the energy goes to infinity, it automatically means G goes to infinity. In other words, gravity is not asymptotically free theory in any sense. And so we cannot try to go, if we try to go to short distances, which means E goes to infinity, we will have difficulty. The theory doesn't make sense because you get infinite coupling. This is related to the fact that we say if you have distance scalars smaller than m Planck, gravity gets strongly coupled. That's the sense in which the effective coupling becoming large. And so for energies bigger than m Planck or distances smaller than L Planck, the theory becomes strongly coupled. So why is that? What's going on? What is going on is the following. We think that if you have energies much, much bigger than m Planck, what's going to happen if you have two particles scattering? What you're going to have in the middle is actually creation of black holes. If the particles are close together within the horizon distance, so you get black holes. And the question is, what does it come out? Do you get this side or not? And of course, we know that when you create black hole, new things happen. So this suggests that as E goes much, much bigger than m Planck, we get some universal physics dictated by black holes. So this is quite curious. That means that short distance physics, which means here in the large energy, is governed by large distance black holes, big black holes. So short and large are being related. In other words, UV and IR are somehow coupled to each other. This is the feature of gravity, which is very specific and very special. And as you can see, black holes play a key role in this discussion. So when we try to go to short distances, we get black holes getting involved. Are there any questions so far? Okay. I can see you if you raise hands because I have a view of I have a view from the back of the lecture hall. So if you have any questions, I can see you raising hands. And if not, they will let me know if you have raised hands. Now, there's some universal features of black hole that are going to be important. For example, we know that for a black hole, there are some degrees of freedom. So if you have a black hole of mass m, there are some number of degrees of freedom. So in other words, there's an entropy associated with a black hole, which scales like the area over 4 of the horizon of the black hole. The number of degrees of freedom associated with a black hole is e to the entropy. So it's going to involve a huge amount of states given by the e to the area over 4 in Planck units. In 4 dimension, the area of the black hole scales like the mass squared of the black hole. So this tells you that the number of degrees of freedom associated with the black hole scales like some constant times m squared. So that means the number of states as a given m is huge, exponential in m squared. This is again the manifestation of the UV-IR relation. Namely, if you're asking how many states there are at high energy or high mass, you find the number of states is getting exponentially large for large masses. So if I want to restore m Planck, you would write it here with some numerical constant in front. This is telling you that the number of states at high energy, which is a UV statement, is captured by the black hole physics, which is the IR. So there's some universal features of high energy, which again is captured by the degeneracy of black holes, which is known by semi-classical or infrared aspects of quantum gravity, as Hawking discovered. So in the effective field theory first picture, in quantum field theories. We have a notion of effective field theories where we start with the UV and then we integrate out the high energy states and go down to the infrared description or an effective field theory description, which is valid for energies less than some cutoff. So you integrate everything which is a higher scale. But somehow we are saying that this notion is going to be much more intricate in the context of gravity because the states that you're integrating out know about the infrared physics through this mechanism. So there's a relation, and that means that the notion of effective field theory is not the usual notion, and it's going to be more complicated. So in other words, the UV data, which are not crucial for the quantum field theories, you can integrate them out. In the case of gravity, it seems to play a much more major role. In fact, an example of this is that in the quantum field theory, if you ask what is the degeneracy of states for large energy, this cannot go any faster than the energy. Unlike the black hole, where we said that the entropy goes like m squared for large m, this is a lower power. This is a maximal power for quantum field theory is lower. And why is it so low? Why is it lower? The reason it's lower is that if you compactify a quantum field theory on a circle or compute the partition function, thermal partition function, if beta is, if the radius of this is very large, that means beta is the inverse radius. So this could be made as small as you want, and this should be convergent. And for this to be convergent, the degeneracy of states cannot be too much. In other words, you can have e to the minus beta h. You can replace this by e to the minus beta e times the degeneracies of e. And if it's higher power than e to the ae, for beta, it would for some beta there will be no beta in which this converges, whereas at least there is some beta as long as the growth is no more than exponential in energy. In the context of gravity, you will see it diverges this quantity, and this is related to the fact that in the context of gravity, it is okay for this to diverge, because what that means is that if you have a very massive state going in the loop, the geometry changes, and instead of having a circle, you get a cigar-like object. In other words, gravity is dynamical, and you cannot impose the boundary condition to be circle and fix it. That's the difference between quantum field theory and quantum gravity. So again, we see a sharp distinction between these kind of behaviors.
Kumnun, can I have a question?
Okay, so then we come to the central question of the lectures I want to discuss here, is whether one can start with a consistent quantum field theory and couple it to gravity.
Kumlun, there is a question. So
in other words, if this is good quantum field theory, consistent, maybe even conformal, maybe even asymptotically free and everything, so it's nice theory, can you couple it to gravity? Well, if the quantum field theory is described by some kind of a Lagrangian, so some, let's say, gauge fields and some matter fields, so we have some kind of a Lagrangian, which is functions of them. If you want to couple this to gravity, all it means is that you just introduce a metric. You add the metric degrees of freedom, which is make everything covariant derivatives and all that, and the areas and so on, volume and so on, measured with respect to the metric, and you add the Einstein term. And you add the integration over the metric. So introducing this extra degrees of freedom is what we usually mean by coupling the theory to gravity. And naively, at least we can write the action, seems nothing is wrong. So more precisely, the way we should phrase it is the following. Suppose you start with a quantum gravity coupled to matter.
Can you hear me?
Like something like this. And then you consider the low energy limit of this, or consider the effective theory much less than in Planck. So if the energy is much less than in Planck, you can ask whether you get an effective theory. So in other words, in this limit, the coupling with the gravitational mode, remember I told you that it's given by E over m Planck.
Kumlun,
So
can
as
you
E
hear
goes
me?
to zero, the coupling to gravity goes to zero. So you can ignore gravity. You get an effective field theory, which is decoupled from gravity, a quantum field theory. So in the IR, you get such a map. So in this way, for any quantum gravity coupled to matter, by taking E to zero, or E is much, much less than m Planck, you end up getting a quantum field theory. So that's what we mean by coupling to quantum gravity, quantum field theory to quantum gravity, which means the quantum field theory, which is left in the limit as you go to zero energy, or very small energy compared to m Planck. The question is, can you get every quantum field theory in this way? In other words, if you consider the space of quantum field theories, which are consistent theories, and then you start with the quantum gravity theory, the space of consistent quantum gravity plus QFT, and you take the E much, much less than m Planck limit, and you ask which effective field theories you end up getting. Do you get everything or not? In principle, you might get only a subset of these, only specific ones, and you might miss the rest. You might miss all the rest. The question is this map, is it surjective or not? The points, just to set up the terminology, the points that we get here are called quantum field theories that belong to the landscape. That's what the terminology people use, or the quantum gravity landscape. So quantum field theories which are good in the sense that they emerge at low energy, we say belong to the landscape. Are there any questions? Is my voice going well over there or not? All is good?
Yeah, it's good, but there is some problem about the microphone in the lecture hall. We'll figure it out. But yeah, please go ahead.
Well, if it's a problem, I can wait to get fixed. I mean, my voice goes over well.
Just a second. So in Zoom audiences, can you hear the echoes in the lecture hall or not?
Are there echoes there?
Is it fine?
For me, it's fine. I'm asking about your students.
Yeah. So yeah, some people hear echoes. That is the problem, but
Let me see. I can try to decrease the volume. I'm not sure if it's going to
I think it's
help
not
or
the
not.
problem of
Is it
your
helping now?
So it's the problem of the lecture hall, some microphone system in the lecture hall.
Oh. So what if I decrease my volume, does it help?
I think it's not your computer problem. It's a problem in the lecture hall. Yeah.
Okay. So somebody is suggesting you should mute the lecture hall audio. Oh no, but sorry, you cannot. I want to see. I want to hear questions. You cannot mute it.
That's right. Yeah, but problem is if we unmute the microphone in the lecture hall, then the audiences in the Zoom chatting, they will hear some echo. If you mute the microphone in the lecture hall, it's fine, but then we cannot ask your question. So there is a problem.
How about if you mute them and as soon as they ask questions, unmute it? We can mute it, and then when there are questions, we can unmute.
Anyway, please go ahead. We will figure it out. Okay.
Okay, but is it? Can people hear me nevertheless or not?
So we can hear you well, but question is whether the audiences in the Zoom chatting, they can hear you well or not.
Oh, I see. So there's a Zoom, this is being broadcast Zoom for other people. I didn't know that.
There is suggestion that speaker should just come closer to the microphone.
I see.
Yeah.
So I see. So you're asking the participants. I see there are 47 participants. I see.
So Kumnon, I think it's resolved. So yeah, just try. Yeah, please go.
Okay. So the points that are in the image of the map from quantum gravity to quantum field theory is what we call belonging to the landscape. This is the quantum gravity landscape. And the question is if it's surjective or not. The points that are not in the image, if there are such points, the rest of these guys we call belong to the swampland. So the quantum field theories of this type are theories which are perfectly fine quantum field theories, but they just don't appear in the image of a consistent quantum gravitational theory. So the swampland program is basically to try to find criteria to distinguish criteria for quantum field theory to be in the landscape. In other words, we want to understand universality properties of a consistent quantum gravity theory. Just like we say there are consistency conditions for quantum field theories, this will be the equivalent of consistency conditions for quantum gravity. What kind of quantum field theories can it emerge in the infrared? And the criteria for it. Now, as it turns out, the number of theories that are in the image, so I said we don't know if this map is surjective. We actually believe that the number of points in the image is finite in some sense. And therefore, since there's set of quantum field theories infinite, this means they are rare examples of quantum field theories which are consistently in the landscape, and the rest of them don't belong to it. Try to say which theory is good is going to be very hard because you have to pin it down exactly the right theory, and that's going to be very hard to figure out. It is much easier to say what theory is not good. In other words, the features that throw it out of a good theory is much easier to distinguish, to explain them. That's why the theory is called the swampland program, not a landscape program. It's easier to say what is bad rather than what is good. Because to find a good one, you have to find exactly the right, very exceptional cases. So we have to resign ourselves to a simpler task of saying, if you give me a theory, are there ways to distinguish that's to ascertain that's a bad theory? It doesn't appear in the landscape.
Kumnon, can you hear us?
Yes.
Can you maybe emphasize once again why good theories are so rare?
It's not clear from what I've said up to now. I'm just saying we'll see that they are rare.
Okay.
They are not. It's not clear from this point of view at all why they should be rare.
Okay, thank you.
In fact, it's not clear at all why it's not even surjective.
Thank you. Thank you.
Yeah. Okay. So string theory. What does string theory do? Well, string theory provides examples of landscape. In other words, we know what consistent compactification of string theory look like, and therefore from that we can derive what effective field theories arrive. And then we can understand some common features of this. First of all, one thing we see is that very few quantum field theories emerge. In fact, each time we are trying to get theories from string theory, we have very limited ways of getting things. Now, it is not clear a priori whether or not that's a shortcoming of string theory or it's a feature of a consistent quantum gravity theory, because we haven't proven that every quantum gravity should come via string theory. So a priori, if we are agnostic and we don't want to assume that string theory is the only game in town, as we should be agnostic. We should just view this as providing examples and not just the full set of landscape, because we don't know. Nevertheless, we can try to use this to find out what criteria, what kind of features, what kind of common features these few quantum field theories that we get from string theory have. Are there some special properties they have? Surprisingly, we do find that there are some common features. And these common features of the theories that we have also point to what are the bad features for bad theories that are not going to be allowed. In other words, this gives us a hint of swampland criteria. So this gives you some hints, but that's not enough proof, because perhaps there are other ways of getting quantum gravity that's not given by string theory, and we might be misled by the examples that we're getting from string theory. So how are we going to be then sure that we got the right criteria? It is not going to be easy, but what we can try to do is to find other arguments for these criteria which are motivated by string theory. So string theory gives you a motivation for these criteria for swampland, but to try to give other a priori independent arguments for their existence of these criteria. So string theory gives you a hint, and you have to find other explanations to validate it. So for example, you can ask whether or not aspects of black hole can help us. So black holes, let's say, of a given charge and a given mass, we know it exists as long as mass is bigger than or equal to charge in some units. And this feature also tells you about some properties of spectrum of the theory. And for example, we know that black holes evaporate. And again, unitarily it evaporates and so on. And so there are these features of black holes that we can try to use. The only black holes that we know does not have to evaporate are the black holes which are extremal. And even in that case, we think it evaporates, except the cases which are supersymmetric. So except for supersymmetric extremal black holes, we believe all the rest of them will decay. So these are features that are kind of independent of string theory, except for possibly the last one, which is motivated a bit from string theory. The rest of them is completely independent. So we can use features of this and try to see if some of these criteria we find can be explained. We will find some of them are explainable using these ideas, but not everything is explainable this way. For the rest of them, what we find is that we find a bunch of criteria for swamplands, criteria 1, 2, 3, 4, 5, etc., whatever number, from these motivations from string theory and black hole physics and so forth. And we find that there's an intricate relation between them. That if this is true in some limit, the other one is true. If this is true in some limit, this other one's true, and so on. There's an interconnection between these ideas, which reinforce them and gives us more confidence in their validity. Okay, so today what I'm going to do is to talk about 3 examples of these criteria. The first one is that there are no global symmetries in a quantum gravity, in a quantum field theory emerging from quantum gravity. Second one is that is what's called the cobordism conjecture, is that the cobordism of a quantum gravity is trivial. I would have to explain to you what do I mean by cobordism. I will. And the third thing I want to describe is the completeness of the spectrum of charged particles, spectrum of charged particles. And by charge, I mean here gauge charge, because there are no global symmetries according to condition 1. So these are what I'm going to discuss today. Any questions before I start this? Okay. Don't be shy. Please feel free to ask questions. So no global symmetry. Suppose you have start with a U1 Maxwell theory, U1 gauge theory. But let's assume that in fact the coupling is zero. So in other words, view this as a global symmetry. And ask, so in other words, there's no E field, just to set it clear. There's no notion of electrical field. And ask if this is okay with quantum gravity. Are there any problems? Well, if there's a global symmetry and if there is no charge states under this global symmetry, then it doesn't have any impact on quantum gravity or anything because there's no E field, there's no charge. So you might as well assume there are some charge states under this global symmetry. Suppose a charge, one of them is, for example, charge Q. You consider a massive black hole, and you take this charge Q, a tiny charge Q, and throw it inside the black hole. As soon as it falls into the black hole, you have maybe a bigger black hole with some mass M prime, but there is no electrical field coming out because we said this is a global symmetry. So therefore, from the outside, you just see the regular black hole with nothing different from just the pure mass with no extra charges. So the information of the charge has disappeared because there's no impact of it outside the horizon. And when the black hole radiates by Hawking radiation, it emits equal amounts of positive and negative global charges because there's no preference of them because there's no electrical field to bias us for one charge versus the other. And at the end, the black hole evaporates and disappears to nothing. And the net charge during this process evaporates also to nothing. And therefore, you have lost the charge that you started with. So this is the violation of the global charge. So that means if you started with a global symmetry, it actually cannot be a conserved charge because black hole gives you a process to violate it.
Kumnon,
Yes.
is there a problem with the scenario that the small charge is left as a remnant after it completely disappears? The black hole completely radiates?
Yes, so people try to bring up the notion of remnants. And this is related to the question you're asking. So for example, can you have a situation where these charges are the leftover pieces of the black hole? Now, if you have a few of these states, that's possible. But if you have a lot of these charge states thrown in, then you will have a lot of difficulties because it's unbounded how many charges you throw in. Then you have to have a huge number of these infinite number of these remnants, basically. And that's hard to fathom. And people have found sharper ways to say that. But this is basically the intuition.
Okay, thank you.
Now, this is on symmetry that I was just telling you, but it can be generalized.
Sorry, I have another question.
Yes.
So while evaporating, can we assume that M prime does not go less than Q and it does not fully evaporate?
No, it has to go. You see, the problem is that in the Einstein's theory, the only charge that you can see are gate charges. And so M is bigger than or equal to Q only for gate charges, not for global charges. There's no electrical field coming out of this because it's a global symmetry. Therefore, Einstein's equation doesn't even see the Q. The no-hair theorem for black holes tell you it just depends on its mass, charge, and angular momentum, but the charge is gate charge, not global charge.
Okay.
And that's the problem.
Oh, thanks.
Yeah. So there are various arguments to
sorry.
try to say why this is general. Yes?
There is a question in Zoom, and
Yes.
the question is the standard model in the swampland then?
I will come to standard model later, but why would it be in the swampland? What's the motivation for the question? Because you think there are global symmetries in this standard model? As I will explain later, there are things that could have been global symmetries, but as I will say, that they could easily also be gauged or broken at some scale. One example of it, as I will mention, is B minus L symmetry, which in the standard model seems like a symmetry. We do not know if this is broken or not by weak effects. So therefore, we cannot ascertain it's a global symmetry, and we do not know if it's gauged or not. So therefore, it seems like there is no a priori contradiction. Okay, so this is here to try to describe that the global symmetries will not be in any quantum gravity theory, and there are various arguments, other arguments supporting this. So, for example, there are arguments in the context of ADS, which is motivated by holography, give you similar arguments. I have already given the arguments based on evaporation of black holes. The holographic case can be used to extend it to more general cases as well. And so that's one version of it. But at any rate, this is one of the most robust. I wouldn't say that we have proven that there are no global symmetries in quantum gravity, but I think we have a lot of evidence for it. And of course, in every example in string theory, anytime you see a symmetry, it's always gauged. And anytime you try to see it, then it's a gauged one. So it's kind of forced on us by examples as well. Now, this can be generalized to what's called the higher form symmetries. So to say what that is, we can rephrase the global symmetries in a different way. Suppose you have a d-dimensional quantum theory, d-dimensional, and consider in it an operator which is localized on a d-1 dimensional space. Some space u of d-1, some subspace. This is what happens when you have conserved charges. For example, when you compute a charge, so when you have a current associated with a conserved current, you can take the dual of J and integrate over the space or over the subspace ud-1, and this gives you a notion of charge. Conservation of charge means that this does not depend, if you change the topological class of this, as long as you don't cross any charge in the middle, it does not depend on it. So this is the notion of the conservation of charge. So this is what we call topological operator, because you can deform it, and conservation of charge, conservation of the current, will tell you that the integral does not change whether you call it, whether you use it, if you compute the integral over here, over m, see here, it will give you the same answer on the boundaries. So the boundary values are equal, and that means that this conservation of charge is related to this fact, and this means that this operator could be viewed as a topological operator, that if you deform it away, you deform it by the surfaces, as long as it doesn't cross a charge, it's the same value. So here I did for the d-1 form, but I could have had any other form, any other dimension. And so these will give you what we call the higher form symmetries. So for example, if you take a surface which is dimension d-k-1 form, d-k-1 dimensional, we call this a k-form symmetry. And the original case corresponded to k equal to 0 is the usual case. So the k-form symmetry should again be viewed as you have a higher forms, the number of forms, instead of the current being a 1 index, there'll be more indices, and it's a k+1 form. And you take a dual of this and integrate, and that gives you the notion of charge. So the absence of global symmetries would suggest that another way of stating it is that there are no topological operators, that you cannot define it this way. This brings us to another version of stating a similar thing, which is called the no cobordism conjecture. And to define this, I have to first tell you what is the cobordism. We say two manifolds of some dimension m1 and m2 are cobordant if there is another one dimension higher manifold, such that the boundary of n is this m1 minus m2 with some orientation. In this case, we say M1 is in the same class as M2. Of course, this N could have non-trivial topology. Also, we say if you have two manifolds M1 and M2.
There is a question in the Zoom, and
yes?
the question is, what is the topological operator?
Topological operator is an operator which if you evaluate it on a surface or a subspace, and if you deform it, it doesn't change. So it's just dependent on topological class of the operator, of the surface.
Okay, so there is another question in the Zoom,
yes?
and the recent discussions in holography claim information about stuff falling into the black hole in available at the asymptotic space. Should we rephrase the no global symmetry argument in this case, or is it still robust?
Well, the no global symmetry argument has been made holographically by Harlow and Oguri precisely by looking at the idea of trying to reconstruct the define operators on the boundary on patches to try to measure the charge inside, and in this way to show that you will get a contradiction. If you have global symmetry, you cannot reconstruct the operators inside. You get some operator which measures charges which commutes with charged operators inside, and that would be a contradiction with global symmetry. So they gave an argument like that. So it's perfectly consistent with holography to say that there is no global symmetry. In fact, it's required by it.
Kumnon, are you there? Hello, Kumnon. Hi, Kumnon. Can you hear me? Oh. 네. Kumnon, I think one of your devices is turned off. Could you please check it or reconnect? Hello?
Hello? Can you hear
Yeah,
me
now
now?
we can hear you.
Okay, so somehow one of my internet, I have two different
Right.
Zooms. One of them was working, the other one wasn't, so I
Yeah,
could see
you're
it here.
drawing the bench diagram.
Yes, so let's just continue. So we have, let me just go here. So you have two manifolds, which we said that you can combine and get a third one, and we say that there's M1 plus M2 is N, and that's the definition of cobordism addition. I called this M3 before, and the N is the intermediate manifold. There's also a notion of a zero. If you have a manifold M for which there's an intermediate manifold N such that the boundary of N is M, we say that M is zero. That means it can be trivialized. So this gives you an addition, and then you can say what group is the cobordism. And when we say cobordism, you have to be more careful. So when I talk about the manifold, you can ask which kinds of manifolds are they allowed? And this actually brings us to the question of what are the structures of the quantum gravity. For example, does it have fermions? Does it have orientation? Does it have this parity symmetry and this and that? So depending on what structure you have, you get different cobordism conditions on what's allowed. So now what does have to do with what we were discussing before? This is the relation. suppose you have a d-dimensional theory, spatial theory, or d-1 dimensional theory times time. So this is a d-dimensional quantum field theory. So view this space. And so view this as a d-1 dimensional background, or d-1. And suppose you consider a black hole in this space. Now, suppose somebody comes and tries to define a defect in this space, but the defect is defined in a funny way. You take a manifold and you cut out a little sphere, and you just cut out a little sphere here, and you identify them, you glue them. So in other words, for any manifold that you have, you can view this as a defect in this setup by just this trivial operation of digging out a ball and digging out the ball from the space and identifying them. So this is basically changes the topology of the space and introducing this M. This is called the connected sum of this M to this background. But you can physically think of this as a defect. And then what you can do is to throw this in the black hole, that is. So you take this manifold as a defect and throw it in to the black hole, and then let the black hole evaporate. And therefore, this should disappear. What that means is that you have a process in which the M that you started with should go to nothing. In other words, the cobordism class of M should be trivial. And that's true for any M. And therefore, we are saying that the cobordism class of the black holes, cobordism class of any geometry in this d-dimensional object, d-1 dimensional object, should actually be trivial. So for a d-dimensional theory, all the d-1 dimensional objects by this argument should be trivial. Said differently, if they were not trivial, they define a global charge that would be a symmetry of the theory, which we know cannot exist, and it's inconsistent with the black hole evaporation. Now, this can be generalized to other dimensions because you can do the same thing with various black brains and throwing them in and so forth. And therefore, the idea is that this is true not only just for the d-1 dimensional cobordism, but for any such manifold. So if you have any quantum field theory, we expect that all the different dimensional cobordism classes of them are trivial. This in particular means that if you start with a, let's say, 10-dimensional string theory and compactify it on two different manifolds, you get two different compactifications. Let me call theory 1, theory 2, which is basically R in some, if you call this theory in the middle D, 10 minus D, and this is also another 10 minus D theory, R prime, whatever we want to call it, theory 1. Let me maybe perhaps I can use a different notation here. Let me just forget about these. Just you have two different theories, theory 1 and theory 2. However, what we just said is that cobordism classes of them are continuous. That means that you can now use a spatial direction here to go from one to the other. And what that means is that you have an M1 here, which can be interpolated to M2 by a finite action process, which means that there's a domain wall that you can go from any theory 1 to any theory 2. Cobordism class is trivial. So in other words, any compactification of string theory can go to any other compactification of string theory. And this should be viewed as that. That means that there's a domain wall which can interpolate between any theory of quantum gravity to any other one.
Can I ask a question?
Yes.
Are you talking about two different manifolds or two different theories?
2D.
Sorry. So here T1 and T2, are you saying they are different series or they are put on different manifold?
No. So these are two different theories. So let me explain it in a concrete of one particular example.
Okay.
So let's take a 10D theory, compactify it on a Calabi-Yau manifold.
Uh-huh.
You get a theory in 4D with n equal to 2 with some matter content and so on. Suppose somebody else compactifies string theory on a different Calabi-Yau manifold, totally different.
Uh-huh.
You get a different matter structure and different particles and so on.
Uh-huh.
Suppose somebody puts it in a flat torus. You get a completely different with different number of supersymmetries even.
Uh-huh.
So you get a completely different set of theories in 4 dimensions. One has n equals to 4, one has n equals to 8, one has n equals to 2, one has n equals to 1, one has no ends, supersymmetry is broken and all that. The statement is that all of these guys are connected to one another by a finite action process. This is not duality. I'm not using anything about duality. You can go from a higher supersystem one to a lower one by a domain wall, which allows you to do this. And that's the triviality of cobordism conjecture.
Okay, thank you.
So for example, this is a dramatic statement. So suppose we take R space, which is a three-dimensional space, R3. Suppose we say, I don't like to be living in this space. I want to be on a Calabi-Yau, a particular Calabi-Yau, n equal to 2, which comes from a Calabi-Yau, let's say Z manifold. Well, you can create a bubble inside this one by going through that domain wall, which ends up with a compactification that you like. So you can create you can go from any one to any other one by a finite action process. So quantum gravity, in other words, is unique. There's no obstruction in going from one to the other.
Sorry, there is a question in the Zoom.
Yes?
The question is, when you say finite action, what kind of action do you have in mind?
Well, when I say that you have a manifold M1 going to M2 is allowed, I'm using the physical notion that this process involves a finite action. For example, if it's an Einstein theory, you have a curvature plus whatever, fluxes or whatever it is. When you compute this in this background, you should get a finite value. But more precisely, it just means that this is allowed process in physics. Infinite action means it's not allowed.
Okay, thank you.
Yeah. So this is the remarkable. So the triviality of global symmetries, non-existence of global symmetries, which is very much in line with triviality of cobordism, tells you that gravity is unique, that you can go from any background to any other one. And that is not duality. I'm not using duality symmetry. So this is not to be confused with duality. Duality, you have to first change the dimension. I'm not doing that. I'm saying two quantum gravity theories in the same dimension are related to each other by this process. So for example, type 2A and type 2B in 10 dimensions should be related by such a domain wall. Any two theories should be related, even if they don't come from compactification. Now, this is a more general notion of quantum gravity, cobordism conjecture. Cobordism conjecture tells you that any two quantum gravity theories are connected. So the third topic I wanted to discuss is completeness of spectrum. Of charged particle spectrum.
Can I ask about your last point?
Yes?
You said that irrespective of the manifold, means let's say type 1 and heterotic and all these 10-dimensional string theories are, those being equivalent are part of this cobordism conjecture?
The word is not equivalent. The statement is that you can go from one to the other. There's no obstruction going from one to the other. That's already part of this cobordism conjecture.
But without any extra manifold, how can
Yeah. So quantum gravity cobordism is more abstract definition. So you start with the notion of manifold, but you can more generally say that's what we mean. You can go from any background to any other one in a finite action process. That's the more general definition of cobordism. That means there's no obstruction in the physical theory, which tells you that there's a selection rule, which tells you cannot go from one to the other. There is no such selection rule.
Can you argue that?
This is a dramatic statement.
Can you also argue all this more generalized notion of cobordism by absorption by black holes and so on? That was the first motivation of cobordism, right?
Motivation is that, but you cannot prove the notion of, I don't claim I'm proving cobordism conjecture.
Yeah.
I'm just saying that is motivated by this, by the ideas that we know. But we know that should be more general because there are some things which don't come from the compactification.
Okay.
But they would have defined, let me say it in a better way. Suppose you have some background in quantum gravity, that gives you a global charge. If you cannot define a global charge, that's the main point here.
Okay.
I can say it aside differently. So let me just go back to this page. So suppose you have we said that every manifold having one higher dimensional manifold whose boundary is this manifold means that the class of M1 is trivial. If you translate this in the context of string compactification, it means that any compactification you have will end up with nothing In other words, any quantum gravity theory should admit a boundary. That's equivalent to cobordism, triviality of cobordism. That means there is no feature here that is different from nothing. That's another way of saying it. So this is very surprising. For example, type 2B theory in 10 dimension is chiral. Naively, one might think that the chiral theory you cannot define on a boundary space because fermions which are left movers or chiral have no right boundary condition to be imposed upon them. But cobordism conjecture tells you in a quantum gravity they should always be possible to do so.
Okay.
And there are no anomalies and so forth which prevents this from happening.
So for instance, then maybe all 5 different string theories being connected, that's also part of this cobordism.
But in not using duality, you see,
Yeah, of course,
this
yeah,
is
just
stronger than
connected.
duality. Let
Yeah.
me explain.
But
Duality, you go down in 1 dimension lower or 2 dimension lower and you connect things.
yeah.
I'm not doing that. I'm saying type 2A and type 2B are connected in 10 dimensions.
Yeah.
This does not follow from any duality we know. In fact, I do not know how to describe the domain walls, which go from 2A to 2B.
Oh yeah, sure. Okay. So it's a more general
I'm
notion.
not claiming I know. So just to be clear, I'm not claiming I know all the objects which do this. This is part of the conjecture. And there are a lot of evidence for the cases that every, let me say it differently, every boundary that we know or which are known to be supersymmetric can be constructed in string theory explicitly. There are cases where it's not supersymmetric, and those are precisely the harder ones to come up with in string theory.
Okay.
Type 2A to type 2B, you can argue if there's this domain wall between them, it better break the supersymmetry completely. And that's consistent with the fact that we don't know what object is that. So presumably they are strongly coupled objects which don't preserve any supersymmetry. So it makes a very strong prediction of the existence of interesting domain walls and boundaries.
Thank you very much. Thank you.
Right. So this is highly non-trivial. Okay, so let me go back to the completeness again.
There's one more question in the chat.
Yes.
So the question is, how is the cobordism conjecture satisfied in string theory? And I mean, you don't have any counterexample so far in string theory.
Yes, we don't have any counterexample, but that doesn't mean we have proven all of the examples. For example, the type 2A to type 2B, I told you there should be such a boundary which tells you, but we don't know what boundary exactly does that. Or type 2B should admit a boundary, even though it's chiral. We know it should be, our conjecture is true, but we don't know how to construct it. So we don't have a proof for or against it in this case. But every case that allows for a supersymmetric object or a domain wall to do this, we can find all these in string theory. For example, the Hojava-Witten wall is an example of it. If you take R mod Z2 or S1 mod Z2 in M theory, a priori doesn't make sense because it's singular from gravity point of view, but M theory tells you that's okay. That's an example of such a boundary.
Thank you.
In that case, it's supersymmetric, so it's not surprising that we can construct it. And in all the cases which can be supersymmetric, we can construct it with these techniques.
Can I ask one more question?
Yes?
So suppose that there is no boundary or domain or between type 2A and type 2B, then what kind of global symmetry do we expect to have?
So to try to say global symmetry, you have to think about this as a higher form symmetry.
Yeah,
So this would be like a 9-form symmetry or something like that.
I see.
So said differently, if you compactify so imagine compactify this on nothing, on the whole space. Then you have a two quantum field theory, which is one is called 1, one is called 2, and there's no process which takes you from one to the other. That's, in other words, imagine compactifying the whole space on T10. You get two different disconnected quantum gravity theories. And that's like a symmetry that prevents it from going from one to the other. That's, of course, there's no black hole argument anymore there.
Right. Thank you.
Yeah. Okay. Now, so the completeness of spectrum is so to give you a motivation for this, consider U1 gauge theory. We know the global symmetries are in trouble, so we consider gauge theory. But suppose there is no particle, no charged particle. In this case, you can see that df is 0 and d of star f is 0 also. In other words, since there is no electric or magnetic states, then the d of star f and d of f is 0. Of course, if there were, you would have gotten a source term here, the electric charge objects here, and the magnetic charges contribute there. But we're assuming there are no charged particles, so there's none. So these could be viewed as a form symmetries, as a currents, higher form currents, because it's two form, not a one form. But we said there are no higher form symmetries, so this should not be possible. Therefore, it better be that there are some charges. Okay, so we already learned that there are some charges, otherwise you get global symmetries from gauge symmetries. In other words, gauge symmetries and no charge matter gives you global symmetries. But now we add matter. But the question is, do you get all the allowed matter or not? So suppose you have a U1. And suppose you say, okay, I have some matter, but suppose I only get the even charges. So you get charge 2, 4, etc., but no odd ones. This is a consistent possibility because you can add the charges and you get a consistent story. So suppose you are missing all the odd charges. Is there a problem with that? The answer is yes, because I cannot construct a Z2 global symmetry. A Z2 global operator that I can define is simply given by e to the I can integrate something like e to the I pi f. So if you have a magnetic version, let's say, which is plus or minus 1. And this gives you a global charge. It could be either plus 1 or minus 1. Okay, in other words, you use the fact that odd charges are not part of this, and this gives you a possibility for defining a Z2 global operator. And this should not be possible. Therefore, these 1 and 3 and so on should also be filled. In other words, you really have to kill the full global symmetry. You cannot preserve some subset of it. In other words, if you have even charges allowed, you're killing the whole global symmetry to a subset, to a discrete subset. Now, this I have done it in the context of gauge symmetries, U1 gauge symmetry, and this can be generalized to arbitrary gauge symmetries, even for discrete gauge symmetries, even for non-abelian gauge symmetries or discrete non-abelian gauge groups. In those cases, you have to use the no global symmetries in a more general form, which is what's called the a general notion of global symmetries. So what's called, for example, non-invertible symmetries. So if you assume that when we say that there are no global symmetries, we mean there are also no non-invertible global symmetries, which I haven't defined yet, but just there is such a notion. It allows you to generalize this to arbitrary groups and arbitrary representations. Now, of course, there's a naive black hole argument for some of this, namely, if you take a black hole of some mass and some charge, as long as the mass is bigger than charge, we know that such a black hole exists. That means the number of states in your theory of given mass and charge with this condition is bigger than 0. There are states with this entropy, with this mass and charge, I mean. So then suppose you take another one with mass m prime and charge minus q plus 1. Again, as long as m prime is bigger than minus q plus 1, this exists. So because there is such black hole, therefore the entropy is not 0. And if you now combine these two black holes, you get one object, you get another black hole with charge only plus 1, because q and minus q plus 1 by charge conservation just gives you one charge. So you can create a black hole of charge unit 1. I start with this charge unit 1 because this could not have been a macroscopically measurable black hole. I want to start with a big charge. So for big charges, we know that we can trust the Einstein's equation. And so that's why I start with a big charge, and I can out of that get even its charge unit 1. So I get all the charge states, and this is a black hole argument. It's going to be harder to make this argument for the non-abelian discrete symmetries, but basically that's the picture that one can try to motivate from, at least the global cases. Now, black hole arguments can actually be explained in a different way to show that there's more to the story. Now, if you take, for example, a global symmetry G, and let's say, for example, for simplicity, that this is a discrete symmetry, gauge symmetry, not only all representations appear, so suppose you take a representation rho, not only it appears, but if you take very high energy states, the energy is much, much bigger than in Planck, all the representations appear, but their degeneracy is given by the dimension of the representation. One can argue this, as Oguri and Harlow have done, and there are many checks of this idea. So not only representations appear, we can actually know that at high energy, they approach a certain asymptotic structure. Again, using black hole argument, you can show this. So there's some regularity to this story. It's not just that they appear, but they appear in a regular way at high enough energies. So again, we are coming back to the theme I started the talk with, namely at high energy, things are universal and black hole kind of demands it. And this is kind of a picture that's not obvious from a effective field theory picture why it had to be. So black hole again is bringing the motivation for some of these statements. My talk was supposed to be for 1 hour with 20 minutes time for questions. And I actually am more or less finished with what I wanted to say anyhow. So I'm slightly over 1 hour. So it's, I think, it's probably a good place to stop and allow you to ask more questions. So let me stop here. Thank you.
Thank you very much. Questions? Yeah.
Yeah, hi. So at the beginning of the talk, you mentioned that the program is about finding the right within Code's quantum field theories. So by right, you mean like what, the spin structure of the theory, the Lagrangian description or something?
By right quantum field theories, I mean, probably, maybe I misspoke. What I meant by quantum field theories, good ones, are the ones which appear in the infrared limit of quantum gravity theories. It doesn't mean that they are bad without gravity. They're perfectly fine. So I will explain, maybe I will say later that, as I say, almost all theories are in the swampland. That is, almost all quantum field theories are, in that sense, bad. Bad means that they cannot be coupled to gravity. It doesn't mean they are really bad in quantum field theory. For example, n equals to 4 Yang Mills, for any rank n bigger than 22 in 4 dimension is in the swampland.
I see.
So that's a huge number. And the quantum field theories of this type are nice and finite. So nevertheless, they are bad when it comes to gravity.
I see. And I have another question, like when you wrote the path integral description of these basically quantum gravity, so naively it seems that all you are doing is adding a metric field there, a spin 2 field there.
Yes.
So
Yes.
can you elaborate as to what is fundamentally becoming different when you add a spin 2 field, that you really now have some access to the UV data as opposed to, say, the Wilsonian approach in QFT where really you can
Well, that's $100 million question. It's not obvious what should go bad. In other words, naively, that's what has set off the physicists in the wrong direction. They thought that the picture should be as easy as the old story.
I see.
But that's wrong. And that's the whole point of the Swampland program. You cannot just, on the face of it, just couple it. This notion of coupling this to that doesn't work.
Okay.
And I try to give examples from black hole physics, why this may be not surprising, if you assume the black hole properties that we already know are true by Hawking's argument. So that's already a connection between UV and IR, which is unanticipated from the viewpoint of coupling X to Y.
Right. Okay, thank you.
So it's, in other words, gravity is much more delicate, and there are much more restrictions that comes to mind.
Hello. So I have one
Hello.
question about when you go back from the quantum field theory with gravity to the swampland or landscape. So how do you justify whether your when you try to reduce from the theory with gravity to the normal quantum field theory? How do you just justify that the process is correct or not?
Sorry, you mean that if I'm given a quantum field theory, how do I know it's correct or not?
Yeah, how do we justify that the process that we try to use to reduce from the theory with gravity to the theory without gravity is correct or not?
No. What do you mean by the process? I'm asking a physical question. I'm allowed to ask what happens at low energy. That's all I'm saying. Look at low energy scattering of particles in your theory. In that limit, the gravity decouples because the gravitational coupling is E over m Planck. So you can make it as arbitrarily small coupling.
Okay, thank you.
So in other words, it's basically a decoupled sector. So that's all I'm saying. It's nothing fancy.
Yeah, and there is a question in the Zoom, and the question is, does swampland conjecture claim that U1 BL symmetry of standard model should be gauged at high energy?
No, it says it has to be either gauged or broken. We do not know which one.
Yeah, thank you.
But it cannot be global. That's what it says. It cannot be untouched.
Hi. Oh, so you said that this all kind of quantum gravity should be connected through this cobordism conjecture. And if you consider some string compactification to, let's say, lower dimension and go to IR to get some CFT, and can you give me some example of the connection between different kind of CFT from the compactification?
Connections. What do you have in mind?
Well, you said some domain wall to connect.
Yeah. I see. The fact that you can go from one to the other, does it give you some information from one to the other? No, it doesn't. Because as I'm telling you, everyone can go to every other one. So there's not much information in that.
Not much information.
By that, I'm trying to say is that you cannot make any further predictions just by saying that they're consistent. That's all it says. It says a set of consistent theories all can go from one to the other.
Okay, thank you.
Any other question?
Hello.
Hello.
You gave the example of compactifying on Calabi-Yau, going to 4D, and if I understood correctly, you said that there are domain walls between all different type of. Does it imply something geometric about Calabi-Yaus that one understands? Like, are supposed all of them to be trivial?
Yes. So let me be more precise here. So there are two ways you can go from this one to the other. One is through other Calabi-Yaus, and the other one is not through Calabi-Yaus, but through other objects. The cobordism conjecture doesn't tell you that they should go through Calabi-Yaus. It just tells you that there's some other manifold which connects them, right? But it turns out that mathematicians have conjectured that all Calabi-Yaus are actually connected by transitions, by going from geometric transitions from one to the other. This is sometimes called the Reed's fantasy. That this is Reed suggested this, and there is evidence that you can in fact go from every Calabi to every other one by such transitions. And that would be what we call the finite action process. Because the extremal transition for us is just having some particles. So you get, for example, you go to a point where you have enhanced gauge symmetry, and then you can Higgs it, and you go to the other side, and so forth. So there are these kind of things that happen quite frequently in the case of Calabi-Yau.
So there's two questions in Zoom. The first one is, in F theory, the swampland conjectures restricts the naturalness of the PQ branes.
What do you mean by the naturalness of the PQ brane? The existence of them have been suggested. I mean, people have written papers about why the cobordism conjecture in F theory demands certain structure on the PQ7 branes.
So
There's
maybe
that.
Yeah. So maybe I will go to the next question. Yeah. So
okay.
The next question is that, what is the ultimate goal of this program? Are you aiming at constructing the beyond standard models that are consistent with this conjecture?
Well, this is a good question. The word ultimate makes me motivated to be very ambitious. The ultimate goal is understanding quantum gravity. That's the ultimate goal, but that might be a very, absolute, very, what is quantum gravity is what is the answer to this question, because that's what constitutes what's a good theory. It's going to be very tough to get there. So I think could be the ultimate goal. But intermediate goal could be find things which are not quite good and find things that can actually, lessons that we learn. In fact, the aim of these lectures is that at the end, we do make predictions for the observed universe, which are surprising from the viewpoint of quantum field theories. But it's very natural from the viewpoint of Swampland. So my aim is to develop these criteria so you actually see concretely that you have to go beyond the standard model based on other observations we have made. In other words, we use observations in our universe, experimental input, combined with swampland criteria that we have developed to say that since our universe should not be in the swampland, it implies that the resolution implies something about our universe which we haven't measured yet. So that would be a prediction, and I'm going to show you some of this.
Thank you.
That's going to be in the last lecture. Any other questions?
So when you said about the completeness of the charge, you made a unit charged black hole by merging two macroscopically charged black holes. So
yes.
can you see the difference between the charge Q and Q plus 1 in macroscopically?
Well, it depends on what you mean. So in some sense, the answer is yes. You should be able to see the charge quantization by consistency, not by the naive consistency, but we do know that the gauge symmetries and so on, by using the gauge transformation, charge is quantized. So therefore, the answer is yes if you define U1 precisely.
Oh, okay, thank you.
Yeah. So for example, just to give you an example, the existence of a charge quantization is related, for example, to a monopole, which quantizes them and so forth. So we expect that to be the case here. Not only the electric charge exists, also the magnetic charge exists.
Any other question? Maybe in the chat or no?
Okay, the timing is fine now.
Yeah. So it's already 10:20. So if there is no more question, then let's thank Kumnan again for his wonderful lecture and also discussions.
Thank you. Sorry for the technical mishap that happened once, and hopefully we'll figure out how to deal with the echo next time.
Yeah.
For the people who are on the Zoom. And
yeah, sorry for it. Yeah.
And if there's anything I can do to make it more interactive, please let me know for the next two lectures. Okay, thanks everybody.
Thank you very
Bye-bye.
much.
Should I share the slides in Zoom?
Now it's working?
No, so
Okay. Yeah, yeah, change.
do you need also this
Ah,
slider like
yeah, if you have, yeah.
Yeah, we have.
Okay.
will you also use the black hole?
Yeah, just if for any reason someone asks a question, it's easier to.
So,
But
are you ready?
huh?
Are you ready for?
Yeah.
All right, I think we need to start. Luckily, alarming. So this is the second talk of the today's morning session, and the first talk, first lecture by Dr. Toriachi from the Institute and the University of Washington. He will tell us about the solvable models of quantum black holes. So please go ahead.
Okay. So should I speak to here? Is this the? Can you hear me?
Maybe you can use this pin mic or.
Do you wanna using this one or this?
Yeah, it's on. Okay. So can I take it off? Just close. Okay. Okay. Yeah.
Just in case. Yeah.
Okay. Okay. Can you hear me? Yeah. Okay.
Do you see the pin mic if you go away?
Here.
I mean,
Here.
actually you have to a little bit close to the mic.
Okay.
So if it's not convenient, I can bring this.
Okay. Okay. Maybe. Okay. Maybe this is easier. Sorry about that. Should I put it like this or? Where did I put it like this?
Yeah, and it should be close to your mouth.
Ah.
So it will capture your voice well.
Okay. Okay. You can hear me now? It's okay. Okay. Well, thank you very much for the invitation first to give a couple of lectures in this school. Topic of my lectures would be about solvable models of quantum black holes. And it will have 4 parts. So in the first part, we're going to describe black holes in classical Jacobi tight-open gravity that I will try to motivate in the beginning. This is a theory of 2D gravity that is relevant for several reasons that I will describe. But in the first lecture, most of the considerations will be classical gravity. Then in the second lecture, in the afternoon, I guess, I'm going to describe quantum gravity effects within this theory, which is one of the main advantages of these simple models of black holes, that one can understand certain things exactly and learn some interesting lessons from it. Then in the final 2 lectures will be about non-perturbative effects, which will be a little bit more restricted in the sense that we will use some toy models that have been very useful in the past years. And in particular, to understand what the role of space-time wormholes is in the gravitational path integral. And in the last lecture, I will discuss some applications, but that maybe is too optimistic. Most likely, I will the topic of space-time wormholes will take both lecture 3 and 4.
So okay, so now I will start. Please interrupt me at any time. I'm using slides, but I will try to go slow, and please ask whatever question you have whenever. Okay. Okay, I will start with very basic considerations. So first, what is a black hole? This was first found as a solution of Einstein's equation shortly after GR was invented. And there are solutions which have an event horizon, which depends on the mass of the black hole. This is the simplest solution, where nothing can come out of it. And then it has a singularity at the center with infinite curvature. And this began as a mathematical solution of the equations of motions that were not really understood whether they were physical or not. That took much longer. But then black holes became a reality for several reasons. The first one, maybe more theoretical, was the notion that black holes can be formed from collapse of stars. This is the first indication that they can appear in physical processes. And then, well, there were other experimental verifications, but perhaps more recently, evidence from gravitational waves or the picture taken by the Event Horizon Telescope that makes us think that there really are objects that are there that we should understand that are part of the real world. Okay, but regardless of that, that will not be the topic of my talk. Instead, I will focus on the impact that they have in theoretical physics, in particular quantum aspects of these black holes. Black holes, the first thing that was already mentioned in the first lecture is that, as seen by an outside observer, they behave as a statistical system, which is perhaps started with the observation by Bekenstein and Hawking. So they have an energy given by the mass, they have an entropy proportional to the area of the horizon, at least in semi-classical approximation, and they have a temperature that is proportional to the acceleration of an observer at the horizon, and this is really a quantum effect of matter fields in the black hole background. But now, there is something very non-trivial, which is the fact that, well, first, the surprising thing is that these objects have an entropy, which is not obvious from their geometry, that since we are assigning a very large entropy to one geometry, that's not clear why that should be the case. But after we realize that they have entropy, the second surprise is that the entropy is finite. This leads to several paradoxes, which we can call the information paradox. It has different realizations. One of which is concerns the entropy of the Hawking radiation as the black hole evaporates. Another type of information paradox can be derived, particularly by Maldacena, by trying to do calculations in gravity that are really inconsistent with black holes having a finite entropy, and one needs non-perturbative effects to understand. This will become more clear in the next lectures, what I mean by this. Then they have a singularity at the center. This is also interesting theoretically, because this is also a toy model of a cosmology. So this is another reason why they're interesting for theory. Of course, it's not the cosmology that we live in, but at least understanding the interior might help make progress in this direction. And finally, for all these reasons, it has been a very fruitful source of new ideas, mainly derived from holography. Some of them we will see in the lectures. So the idea of holography recently goes by the name of the central dogma. This is just a name to emphasize the role this plays in the field. And this is perhaps more closer to the original idea of what holography is, where we claim that the black hole can be described by a quantum system for any outside observer. So this is taking one step further the observations of Bekenstein and Hawking and all. So in the bottom here we have some black hole geometry, and in the top in this cartoon is some quantum system that for the purpose of an outside observer are indistinguishable. And understanding how this works from gravity is the major challenge of this field. But this, I should say, is also well, we can call it central dogma, but it's also a conjecture that is true in strict theory, that this is the way we expect quantum black holes to behave. it might not be true, but we are going to work under the assumption that it should be true and see what the implications are for understanding quantum gravity. Okay. So this idea of holography leads to the more standard one, perhaps, of related to ADS-CFT when we look at black holes that are really black brains in the extremal limit. Then they have anti-de Sitter throats that are higher dimensional anti-de Sitter. And then the quantum mechanical side of the duality is a higher dimensional CFT that describes that ADS throat. And then ADS-CFT is just to forget about the space where this black brain sits and just postulate that the quantum gravity in this ADS throat is dual to the CFT. And these are the type of examples that arise from string theory. And the goal of these lectures is to develop a better understanding, not for black brains, but for black holes that have ADS2 throats. And these are black holes that work in the near extremal limit. So in the previous lecture, we saw that charged black holes have a lower bound on the mass given by the charge. And where we're very close to this bound, but not exactly, then the geometry develops a very long ADS2 throat times some compact spaces that describe the direction of the horizon. So if we want to understand these near extremal black holes, then that's one motivation to try to study further two-dimensional anti-de Sitter space. Okay, so this is a brief introduction. Is there any question before I start with the next topic? Okay. Yeah, I will follow the review. I think I put it on the website. This review we wrote with Thomas Mertens. I will try to follow it. This is the archive number. And I will mention some references, but I don't want to get distracted, mention them all. You can find them all in this review, the original references. Okay. So as I said, we're going to try to understand the ADS2 throat of near extremal black holes. So let me begin with some review of 2D gravity. The type of theories that will be relevant that I will explain later are dilaton gravity theories in 2D, where we have a 2D metric, G mu nu, we have a dilaton phi, which is a scalar field. And one can show that at the two derivative level, this is the most general action that a dilaton gravity in 2 dimensions can have. And then I'm not going to restrict, I mean, we will also add matter, but for now I will just describe the, the gravity sector. So this is a simple exercise that if you try to write any term that you could write involving phi and g with two derivatives, then you can do field redefinitions to put it this way. And all the freedom in this theory is in the choice of the dilaton potential u of phi. And this looks like what in higher dimensions would be an Einstein term if phi was constant. So you can think of phi as an effective G Newton, space variant G Newton. And u of phi is an extra term. One comment is that there is not really an Einstein frame in 2 dimensions. So if you do a bi-redefinition of the metric, then you're not going to change. This doesn't affect the square root g r term. So the fact that we have a dilaton gravity is really an invariant thing in 2 dimensions, as opposed to in higher dimensions where we can redefine the metric, where we remove the coupling between the dilaton and the metric. Sorry, what? Oh, yeah, this is part of this exercise. You can show that you can remove them by field. For example, here you see that if you rescale, if you do a back transformation of the metric, omega, it doesn't change the square root g r term, but it does add some derivative of omega. So if your original action has a term with derivatives on phi, with 2 derivatives, which I'm assuming at this point, then you can remove it by picking omega to be proportional to phi. So any 2 derivative dilaton gravity can be put in this form, plus matter, that I will describe later. So yeah, I said in 2 dimensions, relatedly something special is that G Newton is dimensionless, so it's not really physical. It can be absorbed as a normalization of the dilaton. And the singularity in this language of 2 dimensions is, which will be important later, are places where phi is 0. So where phi is 0 is equivalent to saying that G Newton is large, and then those are the spaces that the places at which we will say there is a singularity. Okay, so what is Jakib-Teitelbaum gravity? So this is a theory of dilaton gravity with a particular dilaton potential. It has a parameter lambda and a parameter phi naught that are written here. So it's linear in the dilaton. And we have three choices in principle. Lambda could be positive, 0, or negative. If it's positive, we will describe two-dimensional de Sitter. If it's negative, two-dimensional anti-de Sitter. And if it's 0 or a constant, then we will describe two-dimensional flat space, also called the CGHS model. And to see why this parameter lambda is interpreted as the cosmological constant, you can look at the equations of motion that are derived from varying the dilaton, the dilaton, which sets the scalar curvature of the metric to be equal to lambda. So this is the two-dimensional analog of the cosmological constant in higher dimension. In most of these lectures, I will consider the asymptotically ADS case, that, as I said, is relevant to near extremal black holes. And to simplify, we will work in units where the length of ADS is 1 from now on, just to simplify the discussion, to make the formulas look simpler. So this theory, based on what I said so far, this would be the action of the theory. So we have the phi r term, the dilaton potential that is linear, and then this is the Gibbons-Hawking term. This is a term that is needed in ADS because ADS has a boundary, and to make the variational problem well-defined, one needs to add boundary terms if we assume that at the boundary we fix the metric, for example. So okay, this is the top line is the theory. Then this theory usually is presented in a slightly different variables where we rewrite it this way, so we can we can write phi as phi naught plus something else, and then the term proportional to phi naught will be, well, here I define S naught to be phi naught over 40 Newton. S naught is proportional to the integral of R plus its boundary term, so this comes from replacing phi by phi naught. And then we have an extra term that is proportional to the varying part of the dilaton, phi minus phi naught. Phi naught is a space, is a number. And then we can recognize that what multiplies S naught is the Euler characteristic of the 2D space. We can shift phi by removing this constant piece phi naught. And then in the third line, this is the way in which the action is usually presented, where we have this topological term proportional to S naught. We have this term that is proportional to the varying part of the dilaton that we will call phi from now on. And here it's obvious that the equation of motion of actually phi acts as a Lagrange multiplier, enforcing that R is equal to lambda. And this is what we usually refer to by the JT term, and then the boundary terms to make the theory well defined with boundaries. Okay, so the action for asymptotically ADS JT gravity with matter is, well, the topological term I already mentioned, the JT term, the boundary term. Okay, this is a detail. One usually adds also holographic counter terms to make the action finite on ADS2. And then finally, we also have the matter. And to leading order in phi naught, so we will consider later phi naught to be large, and to leading order in phi naught, one can make the approximation that the matter does not couple to the dilaton. So if we have a scalar field phi, then we'll take it action for this. For example, if the field is free, is some just the usual action you will write where couples the scalar field to the metric, but not to the dilaton. Okay, and this will be important later. So this is just a comment that will be useful for later, but I'm not gonna go into too much detail. In a first order formulation of these theories of 2D gravity, a general two-derivative dilaton gravity can be written as something called the Poisson sigma model, that you can find it in this section of the review. But for the case of JT gravity, this simplifies to a BF theory with group SL2R. And just to remind you, a BF theory is a theory with an adjoint scalar and a gauge field with an action given by the trace of the scalar B times F. So the adjoint scalar has three components because SL2R has three generators. Two of them impose torsionless when you go to second order formulation, and the third one becomes the dilaton. And the three components of the gauge field become the frame of the 2D space and the spin connection. So I'm not going to use this too much, but it's just useful to have it in mind that that such a connection exists. Okay, so now, so I defined the 2D theory I'll be interested in. So let me go back to near extremal black holes and make it more precise the motivation of why these theories are relevant in that case. So these are already said in words, but let me go into a little bit more details. So consider four-dimensional gravity with an Einstein term and a Maxwell term. Plus matter that won't be relevant for the background I'm going to consider. So as we saw in the previous talk, there are charged black hole solutions that has this form. They have a time coordinate, a radial coordinate, and angular coordinates. The component f of the metric is given by this. MQ are the mass and the charge, and then they are supported by some electric field given in terms of this connection I wrote there. So this is the metric of the Reiser-Nordstrom black hole. And from this metric, one can try to find the horizons and see that only when m is bigger than q, the singularities are covered by horizons. Now, one can go to different coordinates that make the near extremal limit more transparent, where we expand the radial coordinates to be very close to the horizon. And the position of the horizon depends on the temperature. In particular, at 0 temperature, the position of the horizon is equal to q, which is the extremal limit. And then we define this radial coordinate rho to be the deviations outside the horizon. And we rescale time such that we will consider low temperature, so such that we remove the scale of the temperature from time. Then, if you look at the geometry in these coordinates and you take a low temperature limit, then the geometry becomes ADS2 cross S2. So the radial and time parts of the geometry becomes this. So this is in Euclidean space. Otherwise, there will be a minus here. So rho is the radial coordinate in ADS2 and tau is time. The ADS2 radius in these coordinates is q squared. And then the second term is the S2, which is the directions of the horizon. But now the size of the horizon is constant and proportional to q squared. So we see that if we are very close to the horizon, and here we are close to the horizon because of this factor of t here, essentially. But of course, if we go far from the horizon, meaning large rho, large radial distance, then this approximation will break down and we recover the full Reiser-Nordstrom geometry. So to say it again in pictures, if this is a spatial slice of the Reiser-Nordstrom black hole, then near the horizon we have this ADS2 throat in blue. But then at some point, if you go far away from the horizon, then the approximation breaks down and it goes to asymptotically 4D flat space. And in the right picture, I'm showing the same, but in a Penrose diagram. So the whole region in the middle is well approximated by ADS2 cross S2. And then these white regions are asymptotically flat. And then the white region here are approaching the singularity. Okay. And the theory of JT gravity with matter that I just defined is an effective theory that describes things going on in this throat. So that's the motivation. Okay. So let me make this even a little bit more precise, just to make sure we're all on the same page. We can always decompose a four-dimensional metric or a field in two-dimensional harmonics when we. So I'm not doing a reduction on S2. What I want to do is to rewrite this four-dimensional theory as a theory in ADS2. It will have an infinite number of fields, but I can do it coming from KK modes. And in particular from the metric, we have, and this is what will become the JT metric in this connection. We have the two-dimensional metric in the time and radial directions. So this is fluctuation. This will correspond to fluctuations around the ADS2 metric in the T and R coordinates. Then we have the horizon parameterized here. I parameterized it by yi. It's just 3 coordinates such that the square is 1. So it's just another parameterization of the sphere. We have the dilaton that here I call chi, which is the area of the sphere. And then this is just a factor one adds to make the two-dimensional action look like JT. Then another so these are the modes that will become relevant at low temperatures, and then another mode that becomes relevant at low temperatures are, in principle, SU2 gauge fields that come from the isometries of S2, where, for example, the charge of these SU2 gauge fields corresponds to angular momentum in the sphere. And this is a massless field in 2 dimensions one needs to add. But this is all. Then all the other modes, all the other Kaluza-Klein modes of the metric in ADS2, if we write the theory as a theory in ADS2, will be massive. And depending on what question you ask, they might be relevant or not. Yeah. Oh, yeah, yeah. So this function chi and g depend on t and r, which is, I'm calling x mu here. Yeah, thank you. And this a mu, which is the SU2 gauge field, also depends only on t and r. And this dependence with the sphere coordinates is just the Killing vectors of the sphere. So that shows that the SU2 comes from the isometries of S2. Yeah. Is there any other question? Yeah. Yeah, yeah, it's just the compact space might look more complicated, maybe a bigger sphere or a product of smaller spaces. But yeah, in general, any near-extremal black hole, I think this is even a theorem, that any near-extremal black hole universally has an ADS2 factor. I think it was proven by Kunduri, Lucetti, and someone else, I don't remember the name. But yeah. Yeah, so this is supposed to be a very universal theory for any black hole which is near-extremal. Any other question? Yeah. Oh, I cannot hear, sorry. Is there... did you ask if I can explain one more time where the SU2 field come from? Is that what you asked? Okay. Yeah, you can imagine perhaps a simpler case where the compact space would be just a circle. And then that gauge fields come because you have a zero mode which comes from rotations around that circle. So the circle has an isometry which is just rotated. And then that leads in 2 dimensions to a gauge field which will be U1 in that case, where the charge is just the momentum around that circle. So here the SU2 is just a little more complicated version where the horizon is S2. So the S2 it has 3 Killing vectors, and each Killing vector, which describes an isometry of S2, gives rise to a gauge field on ADS2. So does it answer your question? Yeah. Okay. But from now on, we will consider. Okay. Yeah. Let me continue. Yeah. Oh, the y is because this is. So I wrote it in y coordinates because it's easier to write the Killing vectors. Here, it's just this yj, where j goes from 1 to 3. So a mu has an arbitrary dependence with t and r, but in order for it to be a zero mode in ADS2, it has to have this specific dependence with y, because these are the Killing vectors of the sphere. If I consider more general dependence, that's part of these dot dot dots terms, which are massive in ADS2. Yeah. Yeah. So I'm just writing the 4D metric in 2D language. We'll have infinite KK modes with more general dependence, but I'm just identifying the ones that are massless. Yeah. It depends only on T and R. Yeah. But in principle, if you have a fluctuation where the A does depend on Y, then it will be part of the dot dot dot. That's what I'm saying. Which are massless, massive modes. Okay, so in the throat, the area of the transfer space is nearly constant and equal to q squared. So now we can make the connection with the JT variables. So this area of the S2 will become phi naught, where phi naught is q squared, is some very large constant, plus phi, and phi describes the which depends only on T and R, describes the fluctuations of the size of the sphere. For example, in the Reiser-Nordstrom metric, that sphere will become bigger as we move away from the horizon. So then this phi will slowly increase as you move away from the horizon, but to leading order, the size of the sphere is constant and given by phi naught, which is q squared here. So this is the connection. So the metric that I wrote down before, G, is the metric of the JT theory, and the dilaton is this varying part of the size of the sphere. And then one can check, and maybe I will leave this as an exercise, that the four-dimensional Einstein-Maxwell action becomes JT gravity coupled to matter. So when you write the 4D action in this two-dimensional language, you get a term that is this topological term proportional to phi naught. This will give you the extremal contribution to the entropy, Q proportional to Q squared. And then you have the term which is the leading one that includes the varying part of the of the area of the sphere, and this is the JT term. And this is something one can do by just replacing these variables in the four-dimensional action. And then here, in principle, one will have these SU2 gauge fields that I didn't write down. One will also have U1 gauge field that arise from the Maxwell field in 4D. One will also have matter, and then all their KK modes. So this is the theory that would describe this ADS2 throat. Finally, well, to analyze the 2D gravity, it's important to keep the leading correction in phi naught, this varying piece. But when you look at the action of the matter, I mentioned that the matter does not couple to phi. And this happens because, as I said, phi naught is much bigger than phi in the cases we will consider. Meaning, as I showed before, near the horizon, the size of the S2 is approximately constant, so the variation is small. And then when you play the same game with the matter and you start with the 4D action and then write the 2D action, then you will see that it will only pick up the phi naught term. And then interactions with the varying dilaton will be subleading in phi naught. Yeah. Oh, yeah, so S naught I wrote before. S naught is phi naught divided by 4G Newton. Yeah, yeah. So phi naught is the extremal area and S naught is the contribution to the extremal entropy. Yeah. Yeah, maybe I should have used the same letter. Sorry about that. Yeah. Yeah. So essentially, when you look at matter, you can just forget about this leading piece, or the corrections will be subleading. Also, there are corrections from corrections that come only from the gravity sector that have higher powers of phi, in principle, and those ones are also subleading in phi naught. So if you remember, phi naught is Q squared. So if you take large Q, meaning a macroscopic black hole, all these are really small corrections. Okay. So this is what I mentioned before, the universality of JT gravity. This is the universal low energy theory for any black hole with low temperature and large charges. And this can be realized in a lot of ways. The one I described is the Reiser-Nordstrom in flat space. You can also have Reiser-Nordstrom in higher dimensional ADS. This is a special case of what was asked before. One can also have rotating BTC black holes in ADS3, which is relevant to some applications. In that case, the geometry is even simpler. It's ADS2 cross S1. But in general, we have an ambient space where the black hole sits. We can call MD. And then near the horizon, it will have a geometry ADS2 cross some compact space. And this is yeah. So this is what I mean by it being universal. The fact that this is the universal behavior of the near extremal limit. Yeah. Yeah. Is it understood? Yeah, I think in the case of rotating black holes, it's believed that just from symmetry principles, the same should be true, because everything that I will say is controlled by the emergent conformal symmetry and its breaking, and the same is true for Kerr. But the careful reduction and identifying the relevant modes at low temperatures, I think it was not completely done. There's some progress done by Trivedi and collaborators. They have some, but I don't think it. I think that's something that should be done more carefully. Yeah. But from a symmetry principle, then I think that should be true. Yeah, but it would be nice to see. So, any other question? Okay. Phi naught appears as a topological. Well, maybe that will become clear. Maybe why phi naught is important will become clear in the next slides when I look at the solution. Okay, so let me make an analogy because I think it's important to understand what do I mean by this. So we can consider the more standard case of maybe the first case one learns about ADS-CFT, which is a stack of branes in 10-dimensional type 2B with an ADS5 horizon. Then all I'm saying is the analog fact that, in principle, because the size of the S5 is big, the theory is always 10-dimensional in this example. That leads to ADS5 CFT4 with n equals 4 duality. But something that people do normally is to write this 5-dimensional theory in ADS5 as a theory of 5D gravity with a negative cosmological constant coupled to matter. So what I'm doing is not too different from that. It's just that in the particular case of black holes, as opposed to brains, the geometry is even simpler. It's ADS2. And one could ask, okay, one normal question could be like, okay, why do we expect these theories of ADS2 to be physical since they have no propagating graviton? And you could ask a similar question in 5D. In principle, the number of degrees of freedom of the metric in 10D is bigger than 5D. Nevertheless, we use 5D gravity to understand ADS5. But of course, this depends on what questions you ask. There are questions that are sensitive to the fact that in 5D you have a large tower of Kaluza-Kleinmos that have a small mass, and some questions that are not. So yeah, I'm just drawing. Okay, so the point of this analogy is that using 5D gravity for, in this case, is like using JT for black holes. And yes, the only complication from this perspective from ADS2, so ADS2 has no degrees of freedom, but of course, so this reduction of degrees of freedom of the metric is compensated by the fact that you also have matter, and that matter has propagated degrees of freedom. But also there is an extra complication which will become clear later, which is that in ADS2, we cannot really approximate the transverse sphere to have a constant radius, which is something we do in ADS5. We don't really include the fluctuations of the size of the S5 as in our background. It's a mode that fluctuates in the metric, but one can really decouple what's going on near the horizon to what's going on in flat space. And that's something that will be an important point of the first and second lecture, is that one cannot do it in ADS2. Or, well, we understand how to do it, but it doesn't work in the same way as in higher dimensions. Okay, is there any question? Okay, so let me go back to classical JT gravity, analyze their classical solutions. And for now, let's start by assuming the dilaton is a constant given by 0. and let's see how far can we go and try to understand why this is not the right thing to do. But okay, the equation of motion that remains is that r is equal to -2. This is, as I said, I'm working in units where the radius of ADS is 1 for simplicity. And the motional solution can be written in this way. So I take the coordinates to be t and c. So c is the holographic, is a radial coordinate in ADS2. U and b are the time-like coordinates. Null coordinates, the t plus c and t minus c. And then any metric can be written as a reparametrization of ADS2 itself. So, any solution of this equation can be written as ADS2 up to a reparametrization of U and V. This is, if you're not familiar with this is one way to derive this is to write a metric in conformal gauge and then plugging that into this equation, and then you will see that that's a Liouville equation, and this is the general solution of the Liouville equation, which is equivalent to asking about finding solutions with constant curvature. Okay, so the solution is locally ADS2, which is evident in these uppercase coordinates, which are functions of the physical coordinates little u and little v. But the global properties depend on these functions, and that's what I want to analyze next. So first we have global ADS2. So this is the following choice. So to distinguish it from other coordinates I will use in the future, this bold means that they are coordinates of global ADS2. For this definition of time, the Penrose diagram is a strip. So this is the Penrose diagram of ADS2. It's just a strip. The metric is given by this function. If I define the c and t, then the two boundaries of this global ADS2 are at c equals 0 and c equals pi over 2, which you can see they are the locations where this prefactor blows up. And then if you fix c and you let t evolve, then an observer sitting at fixed c will move along the red lines. These coordinates cover the maximally extended ADS2 space. This is sometimes called an eternal wormhole, because the two boundaries are in causal contact. So you can send the signal from here to here. There is nothing preventing that signal to be sent. So the two boundaries are in contact. And this is different from the situation in higher dimensions, in the sense that in higher dimensions, this is not a strip, it's a cylinder. And then the boundaries are in contact because there is not really two boundaries, it's just one. But this cylinder degenerates into a strip in 2 dimensions. That's why we refer to it as an eternal wormhole. And it's called eternal because you can send signals from one to each other regardless of time, at any time. Okay, then we have the Poincaré patch, which perhaps is the more familiar coordinate systems of ADS2. And here we take the functions u and v to be the identity. So from now on, I will just use for the Poincaré patch uppercase u and v. So the time and the radial coordinates are defined in terms of this uppercase u and v. And here the metric has the standard form dt squared plus dc squared over c squared, which is what I wrote before. And here we can go back to the global patch and write what part of this, what sector of the global patch is spanned by these Poincaré coordinates. And it's this triangle here that I draw in blue. So the boundary is at c equals 0. We have Poincaré horizons in blue at infinite c. And then an observer sitting at the finite t will follow these red lines here. And as opposed to the previous patch, this describes a theory with one boundary, sitting at c equals 0. So this is closer to the picture perhaps people have in higher dimensions. And these coordinates are nice because they simplify the action of the isometry group of ADS2, which is SL2R, which can be described in this way. So they are essentially Moebius transformation of U and V, where A, B, C, D are arbitrary up to, well, AD minus BC being 1. So this is SL2R transformations. And this corresponds to a throat of exactly infinite length. By this, what I mean is that if you measure the size of the throat, let's say you at time equals 0, and you measure the distance from this point to this point, so the length of a spatial slice, that's infinite. And what that corresponds is that the picture you should have in mind is that this Poincaré patch corresponds to the exactly extremal black hole, where M is exactly equal to Q, and the throat of the black hole, the horizon goes to infinity. It's an infinite long throat. And this limit is what's better defined in higher dimensions, but not really in 2 dimensions. Anyways. And finally, we have the black hole patch. This is the last one. The metric is given, the physical coordinates in this patch are this little u and little b given by these functions of the, so this you can think of it as giving the black hole patch coordinates little u and little b in terms of the Poincaré coordinates, big U and big B. They depend on one parameter beta, and the metric has this form now. In terms of little u and little b, they cover this patch of global ADS2, these 2 blue patches. Actually, they really cover only one, and then they cover the other one through analytic continuation. And the boundary c equals 0 is here, so it's a smaller segment than the Poincaré patch. The horizon is at c equals infinity again. And in the maximally extended version where we include these 2 patches, this describes a wormhole between 2 boundaries, but it's a non-traversable one. Because now, for example, if you have an observer here and it sends a signal, then it reaches the other boundary, but it's outside of the, it cannot be detected by an observer here. Sorry, maybe I should say first, maybe it's obvious from the colors, but these red lines are the trajectories of an observer sitting at the fixed C. Here is there a question?
You said that the z equal infinite is the horizon of this spacetime. Then,
yeah,
is this the horizon for black hole, or is it just like outer horizon, like a cosmological horizon or black hole horizon? I cannot distinguish it. So,
A what or a black hole correction? I didn't hear the.
Is the Z equal infinite made by the black hole?
Made by the black hole?
You said that the Z equal infinite is the horizon.
Yeah. So this is the outer horizon of. Is that what you're asking? The blue lines will become. I'm going to say it in the next slide, but they are the outer horizons of. When you apply to Reisner-Nordstrom, they are the outer horizons of the black hole. Yeah.
Okay. Thank you.
Okay. Yes, and okay. As I said, the wormhole is not traversable because if you send a signal from any point in this red line, it will never reach the red line on the other side. Yeah. Well, what I mean is that if you see this theory as arising from the near extremal limit of the Reisner-Nordstrom, that's what that horizon is. Yeah. Well, I mean, here it's obvious there is a horizon because any particle sitting here cannot reach the boundary. So in this coordinate, the boundary is not all the right. In this coordinate, the boundary is just this segment. So any fluctuation or any signal that is sent from a point here cannot reach the right boundary of the black hole patch. Yeah. So it's kind of interesting that in 2 dimensions the black hole is just a special choice of coordinates of ADS itself. This doesn't happen in higher dimensions because in higher dimensions, so there is a similar Rindler patch in higher dimensions, but both the right and the left would be connected in the boundary. So then you're not really describing a wormhole between 2 boundaries. It's more like you're dividing your higher dimensional boundary in 2, and then there is some Rindler patch in the bulk. So this interpretation of the Rindler patch as a black hole is only works in 2 dimensions, where these 2 boundaries are really disconnected. Okay. C is defined here. So I'm defining the coordinates by the lowercase u and v, and then what I call C and T are the sum and the difference of u and v. Yeah. Any other question? Yeah, this is important, so feel free to ask whatever you want now. Yeah.
If you think about this as the throughout geometry of the near extreme or higher dimensional black holes,
yeah.
Then these 2 boundaries are connected in higher dimensions?
No, then there are these different boundaries. They are the 2 asymptotic boundaries of a maximally extended Reisner-Nordstrom black hole. That has 2 flat space boundaries.
Yeah, that's true.
I think I might have a picture in the next slide or so about that point. Okay. Anything else? No? Okay. Finally, as opposed to the Poincaré patch, this throat has a finite length. So here, okay, this is in coordinate. This is the horizons are at infinite c, but the proper length, which is the integral of. So here, let's say we fix t equals 0. It doesn't matter because this metric is independent of time, and we compute the proper length of, let's say, from the boundary to this bifurcation point. Then this length is finite and is proportional to the logarithm of beta. So as the temperature goes to 0, then this throat becomes longer and longer as in this specific way. I didn't mention it before, but of course the distance is infinite if you integrate all the way down to c equals 0. So I'm imagining you put some cutoff in near the boundary, but then other than that, you integrate up to the horizon, and then that distance is finite. If you would have done it in Poincaré, that would give you infinite. Okay. Finally, to understand why this parameter beta is the inverse temperature, one can put this in more familiar coordinates, where we define r as a function of c in this way. We introduce RH to be 2 pi over beta. And then if you just do the exercise of replacing this in this metric, you get something that looks closer to the radial part of the Reisner-Nordstrom metric. And then you can come to this metric and, for example, see from in the Euclidean signature, and you can ask what should the period of t be for the solution to be smooth as the horizon, and then you get to the conclusion that the parameter beta that appeared here is really the inverse temperature of the black hole. Okay, another useful coordinates are, to put it closer to what I wrote before, is rho, which is defined in terms of c in this way, u minus v is c. And then if you plug in this change of coordinates, you get the metric of ADS2 as written before. This is the same as the one I got before from Reiser-Nordstrom, where rho is the radial coordinate and t is time. What do you say, sir? No, well, this is really finite temperature because I have this parameter beta. Zero temperature would be to look at the Poincaré patch. The Poincaré patch is zero temperature, but you should think of this as the near horizon geometry of a finite temperature Reiser-Nordstrom. Yeah, so we have this beta there. Yeah, in the previous slide, when I got this from Reiser-Nordstrom, I rescaled time to remove this factor of 2 pi over beta squared, but here I put it just for, I don't know, just to emphasize that this is at finite temperature. Okay, just to, so this is an important point, but after weak rotation, where send t to it, this becomes the hyperbolic disk. So these two patches, when analytically continue to Euclidean time, becomes the hyperbolic disk where the horizon is at the center, and these curves of finite c that this is let's say the trajectory of this observer in Euclidean time become concentric circles around the horizon, and now the horizon is at rho equals 0. So this is the Euclidean picture of the well, if I would draw it differently, this would be the cigar picture of the Euclidean black hole. And something important is that the reason why this Euclidean black hole describes this two-boundary non-traversable wormhole is because if we cut it at 0 time in this dashed line, this Euclidean black hole, we can think of this as preparing the state that describes this wormhole on the left in Lorentzian signature. So this I will mention it again later. Well, actually, maybe now. Yeah. Okay, so the Euclidean black hole is this, and again, and this is a very general story in any dimension. That the Euclidean black hole, you can think of it as preparing this two-sided eternal black hole. It has an interior, it has a left and a right, and this you can refer to as a non-traversable wormhole. It's also called an Einstein-Rosen bridge, and the Euclidean geometry describes the preparation, while then if you want to see how things evolve in real time, you have to connect to the Lorentzian evolution. So what is the state that we are describing in this dual, if there was a dual quantum system described in this black hole, which would be a quantum mechanical system, then this maximally extended two-sided black hole geometry would be describing the thermophile double, which is this maximally mixed, well, not maximally mixed, but it's this maximally entangled state between the left and the right, where En are the energy levels of the left and right system. And this particular pattern of entanglement is, in this state, is what's dual to this black hole. Well, actually, well, to be more precise, the black hole geometry is not described only by a state, it's also described by what Hamiltonian we pick to evolve in time. So this geometry is described by this choice of state and choosing the time defined by these red lines, or the Hamiltonian that propagate times in these red lines to be the physical Hamiltonian. And this is a manifestation of the ER equals EPR idea that these wormholes are related to entanglement in the dual quantum systems. And then finally, the Euclidean partition function, if we would do the path integral over this cigar geometry, they can be thought of either as, so in this picture where we imagine that this prepares the thermophile double, what they are computing is the norm of the state, because to prepare the state, we will cut in this horizontal line, and we are essentially computing the overlap between the state on the lower part and the upper part. And if you pick this state and compute the overlap from the quantum system, what you're computing is the sum over all states of e to the minus beta e, or the trace of e to the minus beta h, which is the partition function. So the path integral on the cigar geometry computes the partition function of the black hole, of the quantum system dual to the black hole, or the norm of this thermophile double state. You can think of it in either way. Okay, so the physics on each patch of ADS is given by this. So just to recap, these three choices: we have the global patch, eternal wormhole. This is special to 2D. We have the Poincaré patch. This is the extremal. We can refer to as extremal geometry. And then we have this Rindler patch, or the black hole patch. And here the note I indicated to remind you the definition of time on each patch. And naively, we could imagine that this leads to ADS2 CFT1 if we just forget about this varying dilaton and assume that we have this exact ADS2 geometry. But there is a problem, which is that to define what case we are in, we need a choice of clock, because the clock defines these red lines. So to define what physical situation we have in the bulk, we need a notion of time. And as I said before, the bulk geometry is a combination of a choice of state, but also a choice of the time evolution, what Hamiltonian we use to evolve in time. And the problem, one way to phrase the problem is that a one-dimensional CFT that's not provided with a clock. Essentially, the one-dimensional CFT is strictly topological, or it has zero Hamiltonian. And that can be seen easily because, well, they can be seen in two ways. First, one can think what conformal symmetry implies in 1D. So it implies that the trace, in general, it implies that the trace of the energy momentum tensor is zero. But in 1D, you have only one component, which is the Hamiltonian itself, and then that would imply that the Hamiltonian is zero. This doesn't happen in higher dimensions. In higher dimensions, you can have conformal symmetry, but also a choice of Hamiltonian that distinguish between, are you in global ADS-D or in the Poincaré patch of ADS-D? But that's not the choice you can make in 2 dimensions. Another way to see it is that the only density of states consistent with conformal invariance are either a delta function or 1 over E. This is the only 2 density of states I can write without introducing a scale in the problem. And okay, the second one is bad. This B over E is bad. A and B are some coefficients to be determined. But B has to be 0 because otherwise we have a continuous spectrum. This has infinite entropy. And that goes outside the way we expect a black hole to behave. We want it to have finite entropy. So B has to be 0. And then we end up with the first term, which again is a delta function at 0 energy, so it has 0 Hamiltonian. So these are just 2 ways of seeing the same. So the solution that was put forward in these papers, it was motivated by some developments in SYK as well that I won't have, it will not be the topic of these lectures, but it was very important, is that one, in this particular case of 2-dimensional ADS2 throats, as opposed to higher dimensions, we need to break the conformal symmetry. And the way we do it is by allowing the dilaton to by allowing the background to have a dilaton that varies with space. So that's something that breaks the conformal symmetry because the only thing consistent in the bulk, so the metric is ADS2, but of course, to say that the solution preserves conformal symmetry, we also need to look at the dilaton. And the dilaton being constant is compatible with the conformal symmetry, but if we allow it to vary, then it's not anymore. The way we break the symmetry is by studying backgrounds where the dilaton is not constant. I mean, of course, the dilaton is not constant in the sense that we can allow it to fluctuate. But here we are talking about what is the background that we are going to study fluctuations about. Now, when you break conformal symmetry, you don't have this problem anymore. H can be non-zero. You can define a time in an ambiguous way. And this leads to the duality called nearly ADS2 and nearly CFT1. And the n, that's the n here. And the nearly is not about, I mean, we expect this duality to be exact. The nearly, it's just describing how the symmetries in the problem are realized. The symmetries are approximate, but the duality should be exact. And so this is the way in which one has to understand ADS-CFT in 2 dimensions. Yeah, sorry. Okay. Yeah. Okay. Oh, no, well, yeah. So here I was. First, I wrote all the terms that would be compatible with conformal symmetry, but then if you want a finite number of states, then I argue that this has to be 0 actually. So then, if you impose conformal symmetry, you end up only with the first term. So I'm concluding from either approach. I'm concluding that H is 0 in both cases. Here I just wrote the ones that would potentially be okay, but the second one is not. Yeah. Yeah, thank you. Yeah. Yeah. A what? Sorry, can you say it slowly? I couldn't hear. Log R. Yeah, I will mention that in the next slide. Yeah. Well, okay, I can say it now. Essentially, in let's say in Poincaré coordinates, but okay, that's the next slide. Yeah, I will say it next. Yeah. Yeah. Yeah, so it's the small parameter will end up being, I mean, I'm going to describe this in the next slide, but it's going to end up being the temperature itself. At high temperatures, the breaking of the conformal symmetry will be small, and at low temperature, the breaking of the conformal symmetry will be more important. So the coupling constant is dimensionful, and that's the coupling constant of the effect that breaks the conformal symmetry is dimensionful, and so it depends on what temperature you're working with. Huh? On either side. In the quantum mechanical case also, if you look at states very close to the ground state, then the conformal symmetry will be broken, and if you look at states with high temperature, then the conformal symmetry will be approximate.
I see.
I mean, of course, I'm thinking always temperature that are low enough that you are near extremality. Of course, if you, in the case of near extremal black hole, for example, if you take the temperature to be too large, you will go away from the near extremal approximation, of course.
I see.
But if you take it to be large, so if you take it to be small so that you're not away from near extremality, but large enough, then the conformal symmetry will be a good approximation. But if you go at too low of a temperatures, then you won't. Yeah.
I see.
Yeah.
Okay. Thank you.
Yeah. Yeah, that's a
maybe you argued it. You ruled it out from finite number of degrees of freedom, but is it implicit in first argument?
Okay, I will have to think about it. I don't
Okay.
know. I'm sure. Yeah, maybe some subtlety about the way this is derived. But
okay, maybe.
Yeah, let me think about it. I will tell you. Okay. Any other question? Okay. Okay, so yeah, maybe I should have put this picture before, but okay, this is the picture about how this. Yeah, so if we pick the time in the right part of the picture, if we pick the time to be along if we pick the time such that observers at the fixed distance move along the red lines defined by the black hole time, then this is the patch that describes the throat of the near extremal black hole in higher dimensions. So this blue region corresponds to this blue region, and at some point, okay, this blue line describes the point where the ADS2 approximation breaks down, and we go to the two asymptotically flat space geometries that I think was asked before. And then in the top, we have the singularity, where we also, the ADS2 approximation fails. Well, what we will see is that the behavior of the dilaton will tell us from the two-dimensional perspective that this is where the singularities are. But anyway, so this is the black hole patch is what describes the near extremal black hole. And if you write the Penrose diagram of the exactly extremal black hole, you can see that it will look like or the near horizon region of it will look like the Poincaré patch of ADS2. Okay, and then maybe to answer some of the questions about the dilaton. So what are these nearly ADS2 boundary conditions? This will determine how the field behaves at near the boundary. So first of all, for the metric, we want it to be asymptotically ADS2. So here I wrote it in in the Poincare coordinates. So we have, it should behave like this at small c, and then plus subleading terms that can be important in the bulk, but go to 0 at the boundary. And then we have to look at the dilaton, and the way we fix the boundary conditions is, so as I said, we cannot fix it to be 0 because that would be that would lead to other issues. But we fix the dilaton to blow up in a specific way. So this is similar to what people do in higher dimensions. So you look at the basically any field in the bulk, and then you look at how it can behave near the boundary, and it will have usually two components: one that you can interpret as a source, the one that grows as you go to the boundary, you can interpret as changing the Hamiltonian of your boundary theory. And this is this 1/c term. So if you look at the equations of motion of the dilaton, it will tell you that near the boundary it has to behave as 1/c. Usually we will pick the coefficient to be 0 if we want to study the undeformed theory. But the previous argument implies that we are forced to take this coefficient A to be non-zero. If we do this, then we break the conformal symmetry. And you should interpret this as the fact that ADS2 forces you to study it with a source turned on, which is not something that happens in higher dimensions. And what I will show next is that once we include this source and study this deformation, then the theory in ADS2 will be well defined. And again, this parameter A, that is the source of the dilaton, is dimensionful, so this breaks the conformal symmetry. In particular, for example, in the Poincare patch, someone asked before, this solution will be exact, so it will be 1/c everywhere. And then one can see very easily that if you apply a conformal transformation, then it's not respected by this profile. In Euclidean space, the black hole is a disk and the boundary is a circle. And one can interpret these boundary conditions as saying that we are fixing the proper length of that circle and the value of the dilaton at the boundary. And to behave in the same way as these conditions, we need both to blow up as 1/epsilon, where epsilon can be interpreted as the cutoff. So we need both the proper length of the boundary and the dilaton to diverge, but with a fixed ratio between them. So this is one way of thinking of these boundary conditions in Euclidean space.
I have a question. Will there be more generic solution for the dilaton? Like A you assume the constant or any function of the boundary time?
Yeah, it could be a function of the boundary time. Yeah, but we'll assume it to be constant.
But the other generic boundary, does it still like
yeah, they're
work?
solvable. You can do the same if you assume A to be a function of T.
I see. Okay.
Yeah, here I'm restricting to the simplest case. Okay. Okay, so let me describe a classical process using this notion of how to use the dilaton, in a sense, using the dilaton as a clock for a way to define time. And let me analyze the black hole formation in classical JT gravity in ADS2. Just to show you how the dynamics, the purpose of this example is to show you how the dynamics of the dilaton tells you whether you have a black hole or not, and what happens in a dynamical setup where the black hole is formed from, let's say, collapse. But okay, let's begin with the vacuum nearly ADS2 solution. So this is the equation of motion of the dilaton. You can derive it from the action. Say it's an exercise. It's not too difficult. But if you don't have any matter turned on, then the right-hand side is 0. And the solution in the Poincare patch, as I said, is this A/2C everywhere. This picks the boundary to be at c = epsilon. Let's say this red line here. And again, the singularities are where phi goes to -infinity, and they are all behind the Poincare horizon. And here, just to remind you, I said the singularities appear when the dilaton goes to 0, but if you remember, I subtracted the constant piece, phi naught, and I'm taking phi naught to be large. So the singularity going to -infinity means that phi naught plus phi is small. That's just, is that clear? Or should I? Okay. Okay. Okay, so this is the background for the empty Poincare patch. No, 8 has to be positive. Yeah, so that's something that tells you that A has to be positive. So you want the boundary of ADS to be good. Like, you don't want the boundary of ADS to be a singularity. So A has to be positive so that near the boundary where the dilaton blows up, it blows up with the right sign. Yeah.
As a coming from the T or matter or
Well, from this point of view, there is no matter. This A is a choice of boundary conditions.
but I guess that in ordinary black hole, the
Yeah.
same thing happens, right? For example, M is coming from integration constant, but we interpret it is coming from the matter. So is there any such analog here, or?
Sorry, I didn't understand the
So,
question.
for example, in just a Schwarzschild shield, M over R.
Yeah.
M is coming from integration constant, just like here.
Integration constant of
we
what?
interpret that M as the
Oh, you mean integration constant if you solve for like GTT, let's say? And then
yeah,
you do
right.
something.
So the ADM mass is
Yeah.
we interpret it as coming from the T, right?
Yeah.
So here, similar thing happens, or
Yeah, you can think of it that way because this constant A, if you try to derive it from the the extremal black hole, you can think of it as the leading correction of how you glue your ADS2 Poincare patch to the asymptotically flat exterior, and that will depend on the mass, on the charge, for example. So it's like an integration. So in the sense that if you have an extremal black hole, you have an integration constant which can have any mass or any charge.
right.
So that would be the way in which this.
So then it means that something is sitting at the boundary.
Yeah, yeah.
Okay.
In this picture, let me see. Yeah, maybe I should have emphasized it. In this picture, what happened? The way this A appears is that here, in principle, naively, you would approximate the size of S2 to be constant. That's what corresponds to taking the dilaton to be 0 or phi naught. But then the size of the S2 is really increasing as you go away from the horizon to the asymptotically flat space boundary. In this case, the origin of A comes from looking in the black hole background to the leading correction of the size of S2 away from the throat. So A is a parameter in JT, but you have to read it off from, let's say, your UV completion, whether it's this Reiser-Nordstrom or another black hole that has an ADS2 throat.
All right.
Yeah.
Question.
Yeah.
So should you think of the phi naught or phi 0 always bigger than phi, although phi blows up?
Yeah, phi in the examples we will study, which is the relevant limit if you do the careful reduction from 4D. Phi naught is large, is proportional to the extremal entropy, which is large, is because yeah. So let's say in units where G Newton is 1, the extremal entropy is charge squared, but the radius of the black hole is also proportional to the charge. So you want that to be large so that the black hole is macroscopic.
You're saying so you're saying that phi 0 is always bigger than phi, just phi.
Yeah, phi 0 is always large, and you from a purely two-dimensional, like you can consider a two-dimensional theory with a small phi naught. There is nothing stopping you from doing that. But all I'm saying is that that's not what usually arises from near extremal black holes. Near extremal black hole, you always end up with a large phi naught and a small correction around it. So we will focus on that limit.
Yeah, thank you.
Yeah. And that simplifies a lot. As I said, it also simplifies the interaction of the metric and the dilaton with the matter. And so it's an important simplification. Okay. Okay, let me go back to this example. So, yeah, so this is empty ADS2, or you can also think of it as the extremal black hole. And then what happens if we throw, let's say we have as a matter 2D CFT, some massless field, and let's say we decide that time equals 0 to throw a shockwave to the interior of the ADS2 geometry. So that energy momentum tensor will be proportional to E, where E is the energy of the shockwave. This is exact if the matter is massless. Then we can compute the dilaton before and after we throw in the matter. If we compute the dilaton before we throw the matter, it's the same solution as I wrote down before, this A over 2C. And if we compute the dilaton after we throw the matter and we solve the equations, we solve this equation, but now with a non-zero T mu nu, then the solution is given by this simple form. I'm not going to go through the details, but this is very, if you never did it, this is a very good exercise. This is all two-dimensional, so it's very simple, but it's a good exercise to get a little familiar with the theory. Anyways, this is the solution for the dilaton after we threw in the shockwave. And now you can see that if you take C to be constant equal epsilon, then that doesn't satisfy the boundary condition anymore, because we have this term T squared that depends on time. So now the boundary time is not along C equals epsilon, but along this curve where C is some function of T determined by the energy and determined by A. So the boundary has to go, we need to define time such that the boundary goes along this curve to satisfy the boundary conditions. So I'm basically finding this from just taking this function of T and C and setting it equal to A over 2 epsilon, which is this clear? Is there any question about this? Okay, but now we see that the horizon develops because the solution has a finite time span in Poincaré time. Namely, before this red line that we can interpret as the boundary, it went all the way and covered the whole Poincaré patch. But now, if we draw the line for this new function, this new curve, then it's going to hit the boundary at the finite Poincaré time. This is essentially at the point where this is equal to 0. With this combination, 1 minus et squared over a is equal to 0. And then what happens is that the geometry after you throw in the shockwave is essentially picking the time to be the time of the black hole patch or the Rindler patch time. For example, because now in Poincaré time the boundary has a finite span, there is a horizon, a finite temperature horizon that goes from the original Poincaré horizon here to the new horizon here, and this is really a black hole. This is really a black hole horizon, not a Poincaré horizon. And there is some part of the interior that is shared with the previous Poincaré patch. And then here we can see very explicitly if we would have evolved in time without inserting the shockwave, then we will have access to this region because it's part of the Poincaré patch. But because we threw in the shockwave and we back reacted on the dilaton, this part is not available anymore for the boundary observer. So this is the way black hole formation happens in classical 2D gravity. Okay, so I just wanted to show it as an example of how to use the dilaton. If you see, it's very important to track down what the background value of the dilaton is and what the boundary conditions are of the dilaton to give this interpretation. Yeah, I'm assuming it's important that energy is positive, and it's also important that A is positive. And maybe since you asked, it's also important that A is non-zero. So this is one way in which you can see that taking A to be 0 to restore conformal symmetry is a bad limit, because if you take, the time at which this curve hits the boundary is proportional to A, because you have to solve E times T squared over A is equal to 1. Then T is proportional to the square root of A. Mm-hmm. So if you see if A would be equal to 0, then the boundary will collapse immediately after you inserted any matter.
So when the energy of the shock is negative, then this area is extended, or like a boundary that where the line is extended rather than shrink.
Yeah, but you know, because of ANEC that this E has to be positive. Yeah.
And another question is, as you said, this A, in principle, you could choose some function of boundary time.
Yeah.
So if A is not constant but the function of time, then it could be could be positive or negative depending on the time. So in that
Well,
case,
I think to have a well-defined theory, I would restrict to A
only,
being
I
a function of time, if you want, but being positive and non-zero.
Okay.
Even if it would hit zero anywhere, it could be a problem as well. Well, I don't know. Maybe not, but definitely it has to be positive.
Okay.
It has to be non-negative. Yeah. Yeah. Okay. Is it okay? Okay, I think I'm almost done. Okay, we described vacuum ADS and the ADS black hole. Let me remind you or just to say more explicitly what the dilaton profiles are. So in the Poincare patch, again, we get the dilaton that goes to infinity at the Poincare boundary, and it goes to minus infinity in the other boundary, in these lines, for example. And this would be the singularities of the extremal black hole. And then this is the behavior of the dilaton in the black hole patch, where it goes to minus infinity here. These are the singularities of the near extremal black hole. And in the eternal wormhole, the dilaton goes to infinity in both boundaries. But such a solution of the dilaton does not exist with classical matter in the bulk. And so even though I described the Poincarean black hole patch, if you want to construct physically a global ADS2, you need to do something else, which was done by Maldacen and Chi, to create this eternal wormhole. Okay, and then how much time do I have? Huh? It's already time? Let me see. Okay, can I take 5 minutes on this? Okay. Okay, so the last thing I want to say about the classical JT is that if you see, all the dynamics of the theory was determined by the position of the boundary time, of the boundary curve as a curve inside ADS. So JT gravity, the graviton is not dynamical in the bulk, but there is a dynamical boundary graviton which determines the location of this boundary. So you can describe it in Poincare coordinates to be this f of t. So t is the physical boundary time, and the uppercase t is the uppercase c determines the location in the Poincare patch of ADS2. This function of time determines the physics of the model. So depending on how this function depends on time, you have either empty ADS or a black hole. And if you have matter present, then the matter modifies the dilaton modifies where the boundary is, so then the matter modifies the boundary curve. So all the gravity dynamics is encoded in this boundary time, this reparameterization mode. All the conclusions I said can be derived from a simple action of this boundary mode, which is the Schwarzschild action, which I wrote here. So this is an action that can be derived from the JT gravity starting point. This is the Schwarzschild derivative of f as a function of t. And the coupling is proportional to A over G Newton. And as I said, A is dimension full. So this theory that breaks conformal invariance, because this is not invariance under t goes to AT plus B over CT plus D. The scale at which this mode is important is dependent on the energy scale, since the coupling constant is dimension full.
So when t is given by ft, what determines g as f prime?
So this CV in epsilon times f prime is determined by the fact that you want the metric to be asymptotic ADS2. Yeah. So the boundary conditions on the metric determines both t and c as a function of f of t, and then f of t depends on the rest. Yeah. The dilaton. So this c has the energy, the units of length. So if the length is much smaller, and it has the units of 1 over length. Essentially, at small distances, this c is very large, and this c becomes very small at large distances or large times, And then the effects of this conformal breaking mode is important. And in the next lecture in the afternoon, we will study further this boundary graviton mode and solve it, and study quantum gravity effects that come from this boundary mode. Maybe I will stop here for now. So.
Yeah, it's time for questions or comments.
How A enters in C?
So this is C. I define it. C is the coupling of this Schwarzian theory, and C is given by A over G Newton. One way to think about it is one way to derive this action is to do it in Euclidean space. In Euclidean space, you have the disk with some boundary that you choose to satisfy the boundary conditions, and then you can compute how does the action depends on this boundary curve. Yeah, and then you get something proportional to 1 over G Newton because you're computing the action, which itself is proportional to 1 over G Newton. And there is a term in the action, which is the Gibbons-Hawking term that depends on the dilaton evaluated at the boundary. And that's where 8 comes about. So it's proportional to A because it comes from the boundary term, and it's proportional to 1 over G Newton because it's the gravity action. But here I call it C because this is the combination that matters, that sets the coupling of this Schwarzschild mode. Yeah.
The question from the Zoom was, how is this choice of FT related to the choice of U and V you explained at the beginning?
Yeah, so the choice is that depending on the boundary curve, that determines what patch of ADS2 and what state you are really looking at. So for example, if f of t is equal to t, then your time is spanning the Poincaré patch, and then you are in the empty ADS2. If f of t has, I don't know, it was a hyperbolic tangent, something like that, the one I wrote before for the black hole patch, then this curve, even if here I'm writing it in Poincaré coordinates, this curve will cover the black hole patch. So, yeah. So this function f of t has the same information as the previous change of coordinates. Yeah.
So generically, we would understand this ADS-CFT as some isomorphism on the isometric group.
Sorry, I cannot hear you very well. Can you speak
so
louder?
we generally understand this ADS-CFT at some level as some isomorphism between the isometric group of ADS and the conformal group in the lower dimension. So is there a corresponding such relation between this n ADS2 / n CFT1? Or in other words, can I understand this near CFT1, near ADS2 as some subgroup of the original group that you had?
Well, yes. So, okay. So from the boundary perspective, including this A or including this effect, it breaks the conformal symmetry. For example, here, the Schwarzschild has a symmetry where F goes to AF plus B over CF plus D. So, but that's not what you mean by a conformal symmetry of the boundary. The conformal symmetry acts on time. And that symmetry is broken, and the only, well, there are two ways in which it appears. First, that symmetry, yes, it is broken down to only translation. So if you just shift t by a constant, just time translation, then that's still a symmetry. So I guess in the boundary that manifests itself by the fact that it's a Hamiltonian. So you have time translation. So the time evolution operator is just e to the IHT without having to do anything. If you got a time-dependent Hamiltonian, in the case, for example, that you put A to depend on time, then that will be more complicated. So in this case, it's really not very constraining in that sense because that's all you have in the boundary. But from the bulk, you can see that at large energies, the effect of this mode is very small, and then you do expect the conformal symmetry to be approximate. So it's similar to higher dimensions, it's just more complicated because in higher dimension you have the conformal symmetry at all scales. Here you have an approximate conformal symmetry at the high energies and nothing essentially at low energies. Yeah.
Is there any reason we get Schwarzian derivative Is it related to any symmetry of the ADS2?
Well, you could think of it as some kind of pseudo Goldstone boson of the broken conformal symmetry. So yeah, let me see. So actually, okay, ADS2 has more than conformal symmetry. It has the symmetry enhanced to reparametrizations of time. This is similar to the way the conformal symmetry in ADS3 becomes Virasoro. So in principle, you have a symmetry under full time reparametrizations. You should. But then you break. Then when you choose your ADS2 metric, that breaks it down to SL2R. And then this effect breaks it further down to just time translation invariant. So if you ask what are the actions that you could have that are consistent with that pattern of symmetry breaking, this would be the first term you would write down. And this is one motivation to, for example, in SYK is a particular quantum system where this pattern of symmetry breaking appears. You have, in low temperatures, you have an emergent conformal symmetry that at even lower temperatures is broken. And it's broken exactly in this way. And a general argument would tell you that you should have this Schwarzschild mode, and then people, especially Maldacena and Stanford, did a detailed derivation of how this action arises from that particular system. Yeah, so that's you can get it from this type of effective analysis based on the symmetry breaking. Yeah.
Apparently, it seems to have many derivatives, but should I really understand it as a two derivative action of f prime, so that there's no pathologies in these higher derivative things?
No, actually, the higher derivatives are important. They are one way to think about them is that okay. Then let me go. I will go like one slide to. I think it would be useful. Okay, here I was going to say that this is the Schwarzschild, the energy is the Schwarzschild itself. Here vacuum ADS is some choice of F. The black hole is another choice of F. And then we have this SL2R symmetry that is exact. So this symmetry is not broken. The one that is broken is the one that acts on time, not on F of t. And this is a symmetry of the Schwarzschild derivative, and it has some charges. The way you should interpret this symmetry is that it's gauged, so you should not interpret different f of t's related by this transformation to be different. You should just identify them. And if you define the SL2R charges, what this is saying is that you should look at configurations with 0 SL2R charge, where here the SL2R is the gauge one, not the would-be physical SL2R that would act on time. And in Lorentzian space, you can think that the way you would implement it is that if you have the two-sided geometry, you have some SL2R charge of the left boundary, you have a charge of the right boundary, and then you have SL2R charge of the matter inside. And the sum of the three terms should be 0 because you are gauging this symmetry. In Euclidean space, what this means is that you don't integrate over all these reparametrizations f of t, you integrate them modded by SL2R. But anyway, the reason I'm mentioning this is because in a paper of Maldacena, Stanford, and Young, they argue that in the Lorentzian signature is this 0 charge constraint that removes the negative modes that you will have because of the higher derivatives. So that the analysis is there. You can look at it there. But so the upshot is that the higher derivatives are important. They would lead to negative, to let's say ghost-like excitations, but this gauged SL2R constraint removes them. Yeah. What about watch condition?
If I work in Lorentzian Poincare, like how would you phrase this?
In Lorentzian Poincare. Yeah, then you have a condition that the SL2R charge of the boundary and the matter inside should be 0. Yeah, I think it's the.
Don't you have two boundaries, like the horizon and the?
The horizon is not the boundary, and the horizon is at infinity because it's like an infinitely long throat. So in the Poincare you have only one boundary. So yeah, this is for the case of the black hole patch where you have two boundaries. And I mean, I wrote it this way because yeah, as I said, the effects from the Schwarzschild mode becomes strongly coupled at low temperatures. So in a sense, the physics in the Poincare patch is not 100% well defined. Always the way you want to think about it is that you turn on a small temperature and then you take the temperature to 0. That's the way everything is more clear because of the fact that this mode becomes strongly coupled at 0 temperature. Yeah.
So this particular equation becomes a bit singular in the Poincare limit?
Yeah, that's what I'm saying. Yeah. Okay. But also the whole theory becomes, well, we'll see it later, but essentially this coupling constant that is dimensionful becomes 0. Well, sorry, this is not the coupling constant. This is the inverse of the coupling constant, let's say. The prefactor becomes 0 at low energy, at 0 temperature. And then the fluctuations of this time reparameterization mode becomes totally uncontrolled, unconstrained. So the way to deal with that is to always work at finite temperature where things are better understood and then take the temperature to 0 at the end and then you can see what happens.
All right, so no more questions? If then, listening to the speaker again. So we have an announcement from the organizer.
Okay, so as you know, today we'll have a lunch box because cafeteria is closed, and there are about 20 vegetarian dishes. And the other thing is, once your lunch is done for vegetarian dishes, boxes, you can throw into the garbage bags, but the rest of them, put it on the plate, table somewhere, I think you can see it, and somebody else will collect all these leftover boxes. Okay, thank you. So see you later.
Yeah.
여기 한 번만 뛰어도 그러니까 힘들기 때문에 you cannot do.
Yes. Yes, yeah. Is there right? I didn't explain it, but.
뒤쪽이 없어져 버린 게 뒤쪽이 뛰고 있어야 뒤를 앞으로 넣을 필요 없어요 그냥.
마이크
네?
아까 뒤쪽에 한 명 질문.
The simplest derivation is in Euclidean, but you can do it also. And then you have ADS2 because we have this term in the action that is phi r plus 2. Then this is 2D action. Yeah. And then we have plus the boundary integral phi k minus 1. So you integrate first over phi in the bulk, and that restricts r plus 2 to be 0 everywhere. So then the metric in the bulk is region ADS2 up to some way to cut the boundary. So this is a total derivative? It's not a total derivative, but phi acts as a Lagrange multiplier. So then when you evaluate it on shell where r plus 2 is equal to 0, then this part is 0. Yeah, and then you can show that k minus 1 is roughly epsilon times the Schwarzschild. This is just a calculation you can do, like just compute the extrinsic curvature of the curve. And phi goes as a over epsilon. And then there is also here a square root of the boundary metric. And this goes as epsilon squared, if I remember correctly. Then epsilon depends on the finite position. Oh no, sorry, sorry, I think this goes as epsilon squared, this 1 over epsilon, and this goes as 1 over epsilon. So this 1 over epsilon and this 1 over epsilon from phi cancel with the epsilon squared. And you end up with something, here there is a 1 over 2 Newton implicitly everywhere. And then this reduces to the Schwarzschild action.
This is kind of so-called analog of the boundary and the edge correspondence.
Yeah, you can think of it that way. There are some papers of Thomas Mertens where he tries to give that interpretation as well. Thomas Mertens. Yeah, it's kind of like a boundary, like an edge mode of the 2D gravity.
Because that is the 1D boundary action while you start from 2D. Yeah, that's nice method. Nice. So this triple derivative is just coming from the extra boundary condition where T.
You mean that?
Because R contains only double derivative, right? And then
you were asking
right. Maybe this extra derivative is coming from here.
No, this one is even simpler. It's just that at the boundary you want
the boundary condition is at the boundary you want the metric to be, let's say, 1 over epsilon dt squared. This is just your boundary condition. You want the, but then the 2D metric is dt squared df squared plus dc squared over c squared. And then once you pick t to be f of d to t, then c of t is determined such that this is 1 over epsilon squared.
Yeah, right.
And then you solve for c, and it gives you that it has to give.
Yeah, right. That's the other example. You see that usually k or r has only second derivative, but you have extra derivative.
That's what you were asking.
Yeah.
Okay. Yeah.
So maybe that is the origin of the
Yeah.
project.
Yeah, here it comes from this. Right. This boundary condition.
And then epsilon cancels again. Good. Thank you.
Yeah, sure.
I have a very elementary question.
Yeah.
About so, if you think about the four-dimensional Reissner-Ostrom black hole and the dimensional reduction, then you obtain like nearly ADS2 times S2 geometry.
Yeah.
Then the ADS2 is the Poincare patch.
It depends on the temperature. So if the black hole is exactly extremal, then it's the Poincare patch. If it's near extremal, if the black hole is exactly extremal, then the Poincare, then the Penrose diagram is literally has this form of where here you have singularity. This is literally the Poincare patch of exactly extremal black hole, and then near the horizon here, let's say. So this and well, so here, this area will be described by. Well, the Poincare patch will be just the exterior, but the close to the horizon physics of the exactly extremal black hole is described by Poincare patch of ADS2. But then if you have the finite temperature black hole, then it looks something like this. We have this. And then the region that is ADS2 is what I draw before is this patch here. The whole region, but the black hole patch would just be
Even for the infinitesimal temperature.
Yeah, so there is something discontinuous, even classical, that happens at 0 temperature, right? Yeah. So this is another reason why I think the best thing to do, just from my experience, is to always imagine that you work at finite temperature, and then take the temperature to 0 at the end, if you wish. But the 0 temperature limit is a little bit singular. This led to some problems in the past. For example, some claims that the entropy of extremal black hole is 0 by Hawking, Horowitz, and Ross, because of this was not understood very well back then.
But the Reissner-Ostrom black hole has one boundary plus different.
That's what I mean by it being this continuous limit. Any non-zero temperature behaves different than exactly 0 temperature.
How can you understand this two boundaries? This is two boundaries.
Yeah.
For the finite temperature.
Yeah, this is for the finite temperature. But then what happens is that from the perspective of one boundary, the horizon goes to infinity. So the region joining to the other boundary kind of disappears. It goes all the way to infinity at 0 temperature. So that's where. Yeah, you can think of it. If you take the limit, you can imagine that for example, I draw this black hole, but you can also there are black hole patches related by SL2R transformations and such. This would be like a situation where you have like as you lower the temperature and you keep the time on one of the boundaries fixed, then the other black hole patch will become very small. It will look like this. So this will be one boundary and this will be the other one, until it kind of disappears at 0 temperature. But that's why I'm saying that there is something discontinuous, because at non-zero temperature it's always there, no matter how small it is. But then you take 0 temperature and this point that will, if you were an observer here, this point that will connect this side with this side went to infinity from the perspective of this observer. So in that, I mean, I agree with your confusion. I'm just saying that it's just a fact. I don't know. It's a feature of how. Yeah.
Thank you.
But yeah, so this is. So I think it's better to think of it at finite temperature and take it to 0 at the end. Especially because of what I said. Also, this structure model will become strongly coupled as you
where's the other boundary? Sorry. Yeah. We have two boundary in the dimensional reduction set.
From both sides, there are two boundaries. Here you have two boundaries because this is ADS2, which is a strip. And here you have two boundaries because it's the maximally extended eternal black hole. Well, not eternal because it's class space. If it would be in ADS, it would be eternal, maximally extended solution. Yeah, here if you would try to write something similar for higher dimensions, it's just that in higher dimensions you will have a cylinder. And then a solution, there is such a thing as a Rinder patch in higher dimensions, but the two sides, instead of being two separate boundaries, would be like, let's say this is 7, right? It will be one half of this, and the other half, so this will be less, and this will be less. So they're not really two different. It's just one, yeah. This is useful if you want to talk about entanglement entropy of intervals or things like that. This is a wormhole, right? Because if this is a wormhole in the sense that if you look at zero time and in the radial direction, and you remember that the dilaton is actually the size of S2, then the geometry will look like this. Where the dilaton is very large near the boundaries because of the boundary conditions. If I wouldn't, this would be a cylinder if I would take phi to be 0 because it would have just constant area, but that's not a good limit. So, but if you allow for the dilaton to vary, then it will be very large here, then it will go to the minimal value at the horizon, and then it will go back up again at the other boundary. And then, but if you see that how it evolves in time, then it will pinch off at the singularity and not be traversal.
So if we have like brane solution, the near horizon limit becomes this high dimensional Rindler patch. So
yeah, so if you will have. Well, I mentioned the branes just because to mention the connection between the central dogma or holography and what you refer by the CFT. Here it would be I don't know, this ADS5, let's say, from these 3 branes, and then these two sides will be 2 halves of the spatial part of the dual 4-dimensional CFT. Just that here you don't have, there is no spatial coordinate in the boundary, so you only have time, and the 2 boundaries are really 2 separate boundaries. Here they are connected through the spatial. For example, this could be if this was ADS5, then this would be S3, and then this would be, say, the south and the north hemisphere of S3. And this would be like a wormhole in the bulk. It's like a way of writing a kind of wormhole that connects the 2 parts of the boundary, but they're not really disconnected boundaries. Unlike ADS2. Yeah, that's why in higher dimensions it wouldn't work to get a black hole from just change of coordinates. You cannot really, you cannot get a black hole so easily. You really need a different solution, but not in ADS2.
one side and two sides.
Yeah, confusing, but that's why I'm saying, like, you shouldn't. I think it's not physical to take the temperature to be exactly 0. It's not.
We start from near extremal black hole, and we get only Punker patch of ADS2, right? And for maximally extended one, we have two-sided ADS2 black hole.
Yeah. I think that's a very. I mean, we can discuss this, but I think it would go nowhere. I think it's just have to accept the fact that t = 0 is not a physical limit. And,
but as you said, we start from that maximally extended one and take zero temperature limit. Is there any problem?
Yeah, there are problems.
There are.
Yeah, I will mention it later, but.
I see. Thank you.
Well, there are only no problem. There are no problem when you have supersymmetry. So in that case, there is no problem, and then you can really see that the black holes survive at extremality.
Yeah.
But if you don't have supersymmetry, then the extremal limit is not very well defined. I don't think I will have time to discuss the supersymmetric case, definitely. But yeah. But yeah.
You already mentioned that apart from this Wisner-Nordstrom solutions, you can get Cauchy cavity from these 3 solutions as well.
Yeah.
BTC, suppose.
Yeah.
So I suppose hole and I truncate it by an end of the world brain.
Yeah.
My motivation is to get to the doubly holographic pictures of near the cube.
Yeah.
So suppose I have this kind of end of the world brain, and this is an ADS2 slice. I'm assuming the black hole horizon in the high dimension bulk should induce some horizon on this end of the world brain as well. So should I get JT gravity here on this brain world geometry?
Yeah, I guess that's what they argue.
Yeah.
Yeah.
But as far as I know, we always get a topological gravity here, unless we break the conformal symmetry somehow here.
Yeah. Topological. Why do you get? I mean, in principle, the size of S1. So here the dilaton in the BTC case is the near horizon geometry of BTC is ADS2 cross S1.
Yeah.
And phi is the length of the area of the S1. So I mean, in principle, you could have fluctuations where the size of the S1 are varying in this JT boundary.
Yeah. My point is I don't want to get to the near horizon limit of BTC.
What do you want to do?
I have this BTC and I truncate this by an end of the world brain. And this horizon, high dimension black hole horizon, should induce some horizon on the end of the world brain as well, right?
Okay, can you draw the three-dimensional geometry first? Like what is?
Suppose I have this BTC black hole here.
So here you're drawing a finite time slide, fixed time slide.
Yeah, a fixed time slice. Now I want to truncate this geometry by putting end of the world brain. Maybe something like this. So this horizon induces some horizons on this end of the world brain as well.
Okay.
So should we expect JT gravity here on this end of the world brain if I get to the 2D gravity?
Yeah, that's not the way I was thinking about JT gravity. Maybe, but you definitely have in this slicing a varying dilaton too, because the size of the S1, let's say from here is given by the horizon, but then here is increasing, here is also increasing. Here is that something weird. So you also have the same type of behavior of the dilaton as in usual JT gravity. Now whether you get literally JT gravity on the nose, if you do that, I don't know. I didn't think of it that way. What I was thinking is more like the picture I draw, where you have the long throat, and then here you have ADS2 cross S1. So this would be more like describing the physics that happens here. But I'm not really cutting it. Usually the way to think about it is that the propagation outside of the horizon is kind of easy, or because, I don't know, I guess if you assume that if you have a black hole sitting somewhere that doesn't affect, I don't know, if you throw some particle here, it's easy to see how it propagates. And then when it gets to the throat, close to the horizon, then there you use JT gravity to understand what happens to that near the horizon, which is the type of picture I draw here. Here, the only subtlety is that because of this one, you have a U1 gauge field, but to have BTC, you need that U1 to have a near extremal limit. You need angular momentum, which means that you're looking at the background with non-zero charge of that U1. But then the only difference, then the geometry doesn't really factor into ADS2 and S1. There is a mixing term because of the angular momentum. But the way to think about that is that you have ADS2, as I said, but you have it in the background with an electric field turned on. That's the... Rather than that, if you think about it this way, then you do get JT. Now, if you do this that you're saying, I'm not sure. But in principle, I wouldn't expect to get topological gravity. I would expect to get something JT-like. Maybe... Yeah, I would expect to get something like that.
Thanks.
Sure.
카페 대전 가는 사람 카카오 택시로 미리 예약을 하는 사람들이 되게 있더라고.
No problem.
길거리에서 그냥 잡기는 좀 쉽지 않을 것 같다는 느낌을 받았어. 그래서 차마 말을 못했어. 아니 뭐 아니 뭐 8명 다 와도 뭐 30만 원씩 아무 상관없지. 내가 뭐 그런 물정을 좀 알았으면 내가 했을 텐데 차마 거기서 KTX가 한 번에 갈 수 있거든요. 예. 옛날에 뭐 인천에서 시작한 게 있었다고 알고 있는데 한 공항철도로 가야 되는 걸로. 뭐 그렇게 가는 게 더 편하다고 볼 수도 있는데 원래 버스가 좋으니까 기차가 좀 많이 편하다고 들을 수도 있지. 아마 더 늦게까지 다니기도 하겠고. 갑자기 060을 시작하는 거 와서 외국 전화. 아 얘구나 하고 내가 다시 걸었지. 하자마자 전화 와서 내리기 조금 전에 뭔가 그 현금으로 이상한 얘기를 해서 한 10만 원 더 받아 먹어. 더 받고 싶으면 물어본 거 있지. 다 오는 게 더. 내 현금만 나가네. 우리는 뭐 싸게 영수증 다 되는 거예요. 영수증 안 써도. 어차피 그냥 작년에 얼마인 줄 알아야지. 30만 원 쓰면 되나? 비행기를 어떻게 인생에 없는 일본에 그러니까 그런 얘기 하는 거야. 유행 타면 안 돼 무조건. 유행이나 그것도 안 돼. 아 근데 미국에서 온 애들은 왜 사귀지 않았구나. 세금 문제가 있어서. 아니 자기한테 사줬어. 아 사준 건데 이해를 사준 거야? 본인이 사달라 그랬어. 사주는 게 편하다고. 그 세금 때문에. 뭔지 모르겠어. 세금이 뭔지. 그러니까 리엠버스 하잖아요 저희가. 그것도 거기서 몇 프로 세금 있는 걸 미국으로 내야 돼요. 리엠버스 안 된다. 그래서 우리가 사주는 게 차라리. 그러니까 자기한테 사달라 그랬어.
방송에서 뵀잖아요. 그게 방송에서 10월인가? 10월 가을이었던 거. 단풍만 보면서 방송하는 거.
나한테 이제 더 이상
시간이 중요하지 않습니다.
매트릭이 막 마음대로 막 왔다 갔다
갔다 하세요? 과거로도 갔다 오시면 좋을 텐데. 아, 형이 체하게 됐어요?
네, 그러라 하시는데.
오케이.
아, 손 마이크. 이렇게 더워?
그러니까요. 그 온도를 한번 물어볼까? 누가 여기를 여기 거지?
아, 저분은 기계 관리. 누가 민지 알아요? 아, 여기 제가 할게요. 괜찮습니다. 아우, 겨울 외투 갖고 와서 완전히.
그런 거안 줘.
예, 여기랑 좀 가까이 앉아야 돼서. 아니, 이렇게 하는 건 아니에요. 이쪽이 많이 필요하신 분. 네? 뭐래? 온도 밖에 있지 않아요? 밖에?
뭐 자기네는 모른다고. 저 사람 그냥 다 모른다 그러는 거야.
아, 저 안에 계신 분한테 물는 게 아니라 밖에 있는 학생한테 물어봐야 돼. Okay, welcome back. We start the afternoon session. So from today, Francesco Benini from CISA will give 4 lecture series on black hole entropy in ADS, and this will be his first lecture. Please.
Okay, thank you very much for the invitation. Can you hear me well? All right. So, yeah, so I will give a series of lectures about black hole entropy in ADS. And so on the web page, I didn't write reading material, but if you're interested in some extra information, there is a review by Alberto Zaffaroni. This is from a few years back. And in those lectures, he discusses a different example than the example that I will discuss here, but the ideas are similar, so maybe you can find some more details there that are interesting. So the objective of this lecture will be to discuss some recent developments in our understanding of the entropy of black holes in ADS, as well as some other quantum properties of these black holes, in particular entropy and the counting of their microstates. And we already heard various lectures about black holes this morning. Now, of course, this is a topic that has been extensively studied in the past. The story starts with the seminal work of Strominger and Waffa, in which they analyzed black holes in a asymptotically flat space, and they showed that if you use string theory, you are able to reproduce and understand the entropy of these BPS black holes using string theory. Now, since this very first work, a lot of work has been done for asymptotically flat black holes, and in fact, the original results have been refined a lot to an extremely level of accuracy. They are quite impressive. On the other hand, it is also interesting, and this will be the point of this lecture, to discuss black holes in ADS. And one of the reasons is the following, that if you work in flat space, well, we have string theory, is a theory of quantum gravity, but for the string, we only have a perturbative definition of string theory. Of course, we also know about some non-perturbative objects in the theory, which are the D-branes. On the other hand, if we work in ADS, we can use holography, the ADS-CFT correspondence, which provides us with a fully non-perturbative definition of what is quantum gravity in ADS. So if you draw a cartoon, this is a standard cartoon, this will be ADS. Here in the bulk, we have our quantum gravity. And the system is equally well described by an ordinary quantum field theory that lives at the boundary of the space. And in fact, we can use this quantum field theory as a definition of what is non-perturbative quantum gravity in the bulk. So in particular, we can try to use this setup to study quantum effects, and in particular also non-perturbative quantum effects to gravity. Yes. So when we use this setup to study quantum gravity, well, we have some parameters at our disposal, and there are different limits that might be interesting. And in these lectures, I will be interested in a sort of semi-classical limit for gravity, so a semi-classical regime. So what does it mean? So from the point of view of ADS, we mean two things. So first of all, we ask that gravity is weakly coupled. So in other words, the size of ADS is much larger than the Planck length. So the size of ADS is much larger than Planck length. Of course, we could study other regimes. We could try to study a space which is highly curved, or the size of the Planck length, but probably the properties of gravity in this space will be very different from the gravity that we have in the real world. So it makes sense to study this regime. On the other hand, I will be interested in a limit, in a regime, in which gravity is close to Einstein gravity. And what this means is that the scale of higher derivative corrections that come from massive string modes, higher spin modes, this type of things, once again, is much higher than the scale set by ADS. Once again, this is not the only interesting regime. For instance, people study the tensionless limit of the string. That is a very interesting limit. But in this lecture, we will be interested in this particular limit. Now, if we do that and we use ADS-CFT, there is a correspondence between parameters in gravity and parameters in field theory. So this will correspond in considering a particular regime in the quantum field theory. So in particular, the first limit corresponds to taking a large central charge, or if you want, a large n limit in the field theory. The second limit instead corresponds to taking a limit or studying a regime in which the quantum field theory is strongly coupled. So the large n limit poses no problem. In fact, this is a very interesting limit to study in general in field theory, and in many situations, this actually simplifies the behavior of the theory. However, the fact that we have to work in a quantum field theory which is strongly coupled, of course, poses some problems, especially if our objective is to use the quantum field theory as a definition of the quantum gravity, and in particular, if we want to, for instance, do computation in the quantum field theory, and from this computation trying to infer what is the behavior of quantum gravity. And so in particular, this forces us to make use of non-perturbative methods in the quantum field theory, which by now we have many at our disposal. Let me just mention a few. For instance, we could use the conformal bootstrap. We could try to use integrability. We can try to use supersymmetry, and in fact, supersymmetry will be the main character of the lectures. We can try to use numerical methods, for instance, doing some lattice or Monte Carlo simulation of or realization of the quantum field theory. Either way, we need to use some of these methods. And as I say, the main method that we'll be using in these lectures will be, in fact, supersymmetry. So once we have this setup, of course, this is a very general setup, and this idea has been considered from the very beginning of ADS-CFT. We can try to ask many different questions in quantum gravity. As the title of my lecture suggests, the questions that I would like to ask in these setups are about quantum properties of black holes, in particular about their entropy. Now, how, as it has been reviewed various times this morning, it was found by Bekenstein and Hawking that semi-classically black holes have an entropy. So this is the Bekenstein-Hawking entropy. And this entropy goes like the horizon area divided by using all the full units, 4 times g Newton times h bar over c speed of light to the cube. So in particular, we see that this is a quantum effect because there is h bar here. However, it is a semi-classical effect, and in fact, this is the leading contribution in a semi-classical expansion to the black hole entropy. Now, as also was reviewed this morning, the fact that these black holes have an entropy, in fact a large entropy, means that really they should be thought of as an ensemble of states in this quantum in quantum gravity. And if you use the boundary theory to describe this quantum gravity, well, this black hole will correspond to an ensemble of states in the quantum field theory. Now that we have this entropy, well, we can use the standard statistical physics point of view, and we can interpret this entropy as a microcanonical entropy. In other words, as the logarithm of some number of states. So we can define a microcanonical entropy as the logarithm of the number of states. And if we do that, so as I say, the first contribution would be the Bekenstein-Hawking contribution, but then we expect corrections. And in fact, there are many types of corrections that we can expect. So first of all, we can expect some perturbative corrections. We can expect some higher derivative corrections that come from the fact that well, we are doing some, we are using some string theory, and there are, as you said, higher massive string modes that, when are integrating out, produce higher derivative corrections. And then there are various types of non-perturbative correction that we might expect. So, for instance, we can expect non-perturbative corrections that have a classical origin. In other words, if you're doing some semi-classical expansion of the gravitational path integral, whatever that is, we can expect different saddles to contribute. But in general, we can expect also some non-perturbative correction that have a stringy origin. And there can be other type of corrections. So, so the interesting part is that if we use the boundary quantum field theory to describe the system, well, at least in principle, we can unambiguously compute all of these corrections. At least we have a non-perturbative well-defined setup where we can try to set up these computations. And then, once we have computed these corrections, we can go back and try to understand how we can try to interpret them as coming from some hypothetical string theory path integral, which is not an object which is well defined, or we can try to infer what type of rules we can try to use to construct a semi-classical expansion in gravity, and so on and so forth. In other words, we can use it to learn some lectures about quantum gravity. Yes, so this will be the main idea behind these lectures. And so the plan of my lectures will be the following. So I will start discussing some properties that will be useful about extremal black holes. In ADS. And in particular, so at this point in this type of lectures, probably one has to choose whether be general and talk about general ideas, or try to consider a specific example and go in some details. And I think that in this type of computations, having some details is useful. So what I decided to do is to consider a very specific example. That will be the example of ADS5, and try to go in some details in this example. Then we will discuss the field theory way that we'll have to address the microsys of these black holes and try to understand their entropy. So we'll review the four-dimensional superconformal index. Next, we will discuss various limits that one can take on this index, and in particular, we'll focus on the Cardi limit and the large N limit. And then after we have done this computation, we will go back and try to extract physical informations from this mathematical data. And in particular, we'll try to see what type of lessons we can learn from these computations. Now, if time permits, towards the end, I will also discuss other approaches that have been used to the superconformal index in relation to the black hole entropy. An interesting approach is to study the so-called giant graviton expansion, but we'll see how we do with time if we will make it there. Okay, is there any questions so far about this general setup? All right. So we'll start discussing black holes in ADS 5. So as I said, I decided to focus on a specific example, and the example will be the most basic and well-studied example of ADS-CFT. So this is the duality between type 2B, string theory, on ADS5 cross S5, and 4-dimensional n equal to 4, SUN super Young-Mills. Now, in this setup, and in particular, at the beginning or today, we'll focus on the gravitational part of this story. One can construct various objects, and in particular, we'll be interested in black holes in ADS5. This means that these black holes that we will consider, they will wrap the entire S5. So they will not be object localized in 9 spatial dimensions. They will be localized in 4 spatial dimensions. They will wrap the entire S5. Now, these black holes can be constructed. Of course, they can be constructed and work in the full 10-dimensional theory, but in fact, it's very convenient to reduce the theory in a very similar way as it was discussed this morning on S5. And in particular, one can do a so-called consistent truncation from the full theory to a 5-dimensional gauge supergravity. And in particular, in order to study these black holes, one can work with the so-called STU model. So this is a model that contains the graviton multiplet, and in fact is with the minimal amount of supersymmetry in 5 dimensions, plus 2 vector multiplets. And in fact, since the graviton multiplet in 5 dimensions contains a vector, there is a total of 3 vectors. And as it was discussed this morning, these 3 vectors correspond to some isometries of the internal space S5. In doing the reduction, this isometry becomes vector fields that appear in ADS5. Now, as it is usually the case, the black holes turn out to have charges. And in this particular example, they turn out to have 6 charges. So of course, they have some mass. Then they have some angular momentum. And in fact, there are 2 angular momenta. Because we are in 5 dimensions, so the rotation group is SO4. And if we call J left and J right, the Cartans in these two factors, it will be convenient for us to introduce J1 and J2 as the sum and the difference of these two combinations. So in other words, this J1 and J2 corresponds to two Cartans of SO4 that rotates two planes inside R4. So there is some R2 plus R2 inside R4. And these J1 and J2 are precisely the Cartans along R2 and R2. Finally, there are three electric charges. That I will call Q1, 2, and 3. These are the electric charges under the three vectors that I described. And in fact, they correspond to a U1 cubed, which is a subgroup of SO6. And SO6 is the full isometry of the S5. So one could write down five-dimensional gravity. In fact, this is maximal gauge supergravity that contains all the gauge fields of SO6. However, in order to construct the black holes, also in view of the fact that the S5 tends to be squashed, it's enough to work with these three vectors. Now, one can construct these black holes. As I say, they depend on 6 charges. They're in general very complicated. However, it turns out that we can, and for the purpose of these lectures, I will mostly simplify to a simplified setup. So we can take the special case in which the two angular momenta J1 and J2 are equal. I will just call it J. So if we do that, as you say, one of the two angular momenta is 0, and so there is an extra isometry in the system. There is an SU2R isometry. This makes things simpler. And we can also take the 3 charges to be the same. I will call this Q. So if we do that, we get some extra symmetry in here. So in particular, we will get an SU3 isometry from SO6. And so once again, this will make things easier. So if we do that, the solution becomes much simpler. And in fact, this becomes the first BPS black hole solutions that have been constructed in 5 dimensions by Gutowski and Real. And just for the purpose of concreteness, let me write down these solutions in such a way that in the following discussion that we'll make, they will have something concrete to refer to. So this will be the Gutowski-Real solution. So in this solution, so there is a radial coordinate r, there is a parameter a, t is the time coordinate, we are in Lorentzian signature, q is another parameter, and then there are some one forms that we will use to write this solution. In particular, omega will be dt minus nu, and nu I'll write in a second. Then in these solutions, there are some radial coordinates. So one of these coordinates, one of these functions, there are some radial functions. One of these functions is ft. And finally, there is this piece here. This delta r is another radial function. And then here we'll have the coordinate on a spatial S3. So this will be an S3, which will be parameterized by coordinates theta, phi, and psi. And so these coordinates, in fact, will appear in this one form nu. which will depend on this parameter A, and maybe the last piece that I need is this rho squared, which is also a radiant function, r squared plus a squared. As I said, there are these two radial functions that I'm not going to write. This is not particularly important. And finally, this solution has some electric field turned on, which is controlled by this parameter small q. Okay. So this is the solution. It's not terribly complicated. We can write it in this on this blackboard. The important point is that this solution will depend on some parameters that I've called A, Q, and small m. The small m does not appear in this, what I wrote here, because it appears in these radial functions. Okay? So we have a three-parameter family of black holes. Now, what can we compute about these black holes? Well, first of all, well, these are black holes. So, so one can solve the equation delta r of r equal to 0. This turns out to be a polynomial equation of degree 6, so one gets 6 solutions. And the largest of this solution, I will call r plus, it turns out to be an outer horizon. Then this horizon turns out to be a killing horizon. So there is a killing vector that generates the horizon. And this killing vector takes the following form. In terms of some function, some object omega, so this omega will be a function of our parameters A, Q, and M. And this is the angular velocity of the horizon. Then, as is standard, one can look at what is the strength of the gravitational field at the horizon. So the surface gravity. And so from this surface gravity, one can obtain the temperature of this solution, which we will also call 1 over beta. And finally, one can determine the electrostatic potential that I will call capital phi. And this will be given by the value of the electric field, the difference in the electric field between the horizon at infinity. And the electric field is a one form, so we contract it with the killing vector field of the horizon. And this determines this quantity here. So what we have done is to construct the thermodynamic potentials of these solutions, which are omega, t, and phi. And they're all functions of the three parameters that control the solutions, which are, as I said, A, Q, and M. Parallel to this, we can compute the charges of these black holes, and the charges are defined in the standard way as integrals at infinity. So in particular, one can compute the ADM mass of these black holes as an integral at infinity. One can compute the angular momentum of these black holes as the Kumar integral at infinity. And integrating star f at infinity, one also constructs the electric charge. So the charges of these black holes, I will call them E, the mass, J, the angular momentum, and Q, the electric charge. And it turns out that these thermodynamic potential and charges satisfy the first law of black hole thermodynamics. So one can explicitly check that dE is equal to T ds plus 2 omega dj. These two because there are actually two rotation parameters that I will set to be equal, plus phi dq. Now this S here is the entropy, and in fact this is the Bekenstein-Oke entropy. Defined as the area of the horizon. So this is all very standard. The M, yeah, so the M was inside these radial functions that I didn't write. The M only appears there. But it does control the solution. Yes. Well, in some sense, yes, in the sense that you can take these black holes to be much smaller than ADS, and as long as, so you take a very large ADS, you can take a limit in which the black hole still has a small curvature, you know, it's on the Planck length, but it's much smaller than ADS, so essentially it's like it lives in flat space. Of course, it will be, from a 10-dimensional point of view, is a weird object because it's still wrapping the full S5, and in ADS-CFT, the S5 is the same size of ADS. From the 10-dimensional point of view, it's very, in fact, is a sort of unstable object. But from the 5-dimensional point of view, you can surely do that. Yes, any other question? At infinity? Yeah, so these black holes live in global ADS. So this will be in global ADS 5, and so the boundary is S3 times R, and this will be important. This will be important tomorrow for the boundary, from the point of view of the boundary theory. So we'll discuss this.
I see. So this is kind of a rotating charged ADS. Is that correct?
Yes, yes. It's charged, it is rotating, so it's Kerr-Newman, and it lives in ADS. Yep. Okay, there is one more quantity that we can construct, and this is the on-shell action that I will call I-Sugra. So how do we construct this on-shell action? Again, this is a standard computation, and following Gibbons and Hawking, what we can do is the following. So we first go to Euclidean, so we rotate t to minus ITE. When we do that, instead of having an horizon, the geometry caps off, so the Euclidean geometry becomes a cigar, so this is the same picture that we had this morning, of course times some large S3, and really this cigar is it's fibered over the S3. However, there is a substitute for rotating geometries, because when we do that, there are mixed terms between time and space, and so the Euclidean geometry is not real anymore. However, we can redefine A to be A tilde. So if we take imaginary, in other words, if we take imaginary values for this parameter A that I had before, then the metric is real. It is smooth in the infrared, and so we can try to compute this on-shell action. Of course, it is usual in holography. There is a divergence here in the infrared because the space is infinite dimensional. So we need to cure this divergence, and there are various ways to do that. One is background subtraction. So we observe that this divergence here, the black hole lives in asymptotically ADS5. So we can subtract, we can cut the geometry, subtract the on-shell action of ADS5, and then the result, we remove the divergence, and the result is finite. Alternatively, we can do the standard holographic renormalization, and this gives the same results up to a constant. Of course, when we do that, if you want to have a smooth geometry, this fixes the periodicity of this Euclidean variable TE. And in fact, this beta is 1 over the temperature, and of course, this is another way to computing the temperature of the black hole. Now, this on-shell action turns out to satisfy a relation which is called, in GR, the quantum statistical relation. And this is the following. This I sugra is equal to beta E minus S minus 2 beta omega j minus beta phi q, which perhaps I can collect a beta and rewrite in the following way. So if we look at this equation, we recognize that what this quantum statistical relation is telling us is just that the exponential of minus the supergravity action is nothing else than the grand canonical partition function. So if we define z as e to the minus I sugra, this is the grand canonical partition function. And we see that from here, because this is the so if you look at this piece, this is the standard transformation. If you want Lagrange transformation, it goes from the energy to the free energy. Okay, so this was... Yes, so all the quantities here, they're all functions of A, M, and Q. And so we can check that this relation is correct. From the mathematical point of view. From the physical point of view, this relation, as I said, is just telling us that the supergravity action is precisely the free energy, or minus the free energy, well, it's the free energy for the system. And so the exponential of minus the supergravity action is the grand canonical partition function of the system. Sorry? Yes. Yes, I'm discussing this in this specific example, but it's all very general and standard. Now, there are two interesting limits that we can take of these black holes. So one limit is the extremal limit. So in this limit, essentially, we fix the charges. For instance, we reduce the mass, and at some point, the radial function delta r develops a double singularity. Sorry, a double zero. So instead of having a single zero r plus, there is a double zero. And what this means is that, in fact, an ADS2 throat develops. Because of this double zero. And so, well, these black holes have a temperature that goes to 0. This limit here, and I'm saying this for what will come in a second, this limit here has nothing to do with supersymmetry. So in general, there are extremal black holes in a supergravity theory which are not supersymmetric. The other limit, instead, is supersymmetry. So in order to construct black holes with supersymmetry, what we require, there is a killing spinor. So there is the existence of a killing spinor. And in fact, once we have this killing spinor, the killing vector that generates the horizon just becomes quadratic in this spinor. If there is this killing spinor, it means that the black holes satisfy one complex supercharge that I will call Q. And so from the point of view of ADS5 cross S5, these black holes will be 1 over 16 BPS. Now, if you go to the geometry and we ask, okay, when does this killing spinor exist? Well, this will give us a relation among the parameters. And in particular, this relation takes the following simple form, that the parameter Q is fixed as a function of the other two. However, it turns out that if we only do this, the black holes that we are going to obtain have some causal pathologies. So in particular, they contain some closed time-like curves. So if we require that in the Lorentzian black hole there are no closed time-like curves, this forces us to impose another relation on the parameters. And this relation, in fact, fixes also the other parameter m. So at the end of the day, these supersymmetric black holes depend on a single parameter A. And one can see that this condition implies extremality. So in other words, if we take real Lorentzian black holes and we impose supersymmetry, we obtain the perhaps not surprising result. These black holes should be extremal. In particular, they must have 0 temperature, because a temperature will break supersymmetry. Now, when we take this limit, the supersymmetric limit, there are a few peculiarities that will be important. Yes. On the original, this transformation here is a trick to compute the on-shell action. Because if you have the Lorentzian black hole and you want to compute the on-shell action, the problem is that there is an horizon, and so your integral is not going to be finite. No. So this condition comes from the real Lorentzian black hole. So in the real Lorentzian black hole, if you require that there are no closed time-like curves, then we need this condition. In the Euclidean setup, there are no time-like curves because the signature is Euclidean. And in fact, this transformation here was just a trick just to compute the on-shell action.
Is there a Euclidean interpretation of those conditions?
Yes, we'll discuss. So this will appear in many different ways. We'll see. So the supersymmetric limit has a few peculiarities, as I said. So first of all, as we said, beta goes to infinity. That means the temperature goes to 0. So in particular, this means that there is no finite thermal cycle at infinity. This beta diverges. Then one can compute the thermodynamic potentials omega and phi, and one can verify that they go to a constant. But this constant does not depend on the parameter A that we are left with for our black holes. So this means that these thermodynamic potential are no longer good variables for these black holes, because they take the same value for any BPS black hole. So they are no good variables. The other feature, as I described, is that there is an ADS2 throat at the horizon. And these features are somehow problematic for various reasons. So for instance, as I say, so the second point is a problem because if we want to parameterize our black holes using these thermodynamic potentials, they are not good variables. They take the same value for all of them. This also becomes a problem if we want to compute directly the on-shell action, because now we don't have a divergence only in the UV, but we also have a divergence in the infrared at the horizon, because now we have this infinite geometry. Now, of course, one way that we can use, that is the way that has been used in the past, is to just give some temperature, compute the on-shell action, and then take the limit to 0. And if you do that, you get a finite limit for the on-shell action. However, it's more generally, for some reason, you just want to work with BPS black holes, and so you want just to work with the black holes that have 0 temperature. Now, this becomes a problem because you cannot cure this infrared divergence with adding some local content terms. Because, for instance, when you do holographic renormalization, this corresponds in the field theory to the standard renormalization, and that corresponds to adding terms in the UV of the theory. We never cancel infrared divergences with local counter terms. The first feature here will become a problem. Well, we'll discuss later on how to associate these black holes to something in the field theory, and then we would like to associate these black holes to some partition function in the field theory that are a finite circle, but here there is no finite circle. But we will discuss this point later in these lectures. So because of these reasons, this led Cabo-Bizet, Cassani, Martelli, and Murti to propose a regularization procedure of these black holes, which is the following. Yes. No, there is nothing special here. It just depends on how the gauge field has been normalized. If you wish, this 3/2 is related to the fact that in the dual theory, the R charges of the theory are 2/3, but it's not particularly important. You could choose another normalization. Any other question? Yeah, so they propose a regularization. The regularization is the following. So let's impose supersymmetry, but not impose the other condition. Now, if we impose supersymmetry, we only impose one condition. So now we have a two-parameter family of black holes that we can parameterize by A and M, or in fact, we can also parameterize by A and R plus, if we prefer. We don't impose this extra condition that comes from the regularity of the Lorentzian real solutions, but instead we complexify the solutions. So the family of black holes that I described, that I wrote at the beginning, that depends on these three parameters, A, M, and Q. And of course, we can take any values for these parameters, and the equations of motion are solved. So in particular, if we take complex values for these parameters, the solutions are still solved. And so taking complex values for these parameters, we get a complexified family of black holes. This is perhaps a weird object. These are black hole solutions in which the metric is complex, the gauge field is complex, but they still solve the equations of motion. So one can take these black holes, these complexified black holes, so this will be supersymmetric but non-extremal. In particular, they will not have this ADS2 throat, and in a complexified sense, they will have a finite temperature. Of course, this in general may be a complex temperature, so this is a complexification, but they will have a they will have a temperature, a finite temperature, and so they will not have this problem that I mentioned here, and the on-shell action can be directly computed in for the supersymmetric black holes. Now, when you impose this condition here of supersymmetry, you can check that the thermodynamic potential satisfy the following condition. And in fact, from this condition, we see immediately that if we insist that all the potentials are real, beta is real, omega is real, and phi is real, here there is an I, so there is no way of solving this equation. The only way to solve this equation is that beta should go to infinity, which is in fact what happens, and this omega and phi should be constrained, for instance, by this relation. However, if we admit for complexified potentials, well, they will satisfy this constraint here, but beta doesn't have to go to infinity, because if it is complex, we can solve this condition. Okay, so we will work with these complexified black holes. And in fact, it turns out that if you use this parameterization instead of A and M, but use the position of the outer horizon, which is convenient, it turns out that there are two branches of black hole solutions. In other words, you have to express this M in terms of R plus, and then you solve this equation, and it turns out that this is a quadratic equation, so there are two solutions. Yes. Yes.
To preserve the supersymmetry at finite temperature, is that?
No, so the point is that, so for real Lorentzian black holes, if you want them to be well defined, when we impose supersymmetry, we should also impose another condition. And so we go down, so we fix two parameters. However, now what we want to do is to only impose supersymmetry, but not extremality.
So, I mean, what it happens at the final stage? This supersymmetry is there or not?
Yes, so the solution is supersymmetric.
At finite temperature.
At finite temperature.
With a complex temperature, you say?
Yes.
Okay, thank you.
So we complexify the whole system because anyway, the Lorentzian black holes are not well defined. They have some pathology, so at that point we can complexify. But we will see that this complex black hole will play an important role in the following. Yes. Well, in the Gibbons-Hawking prescription, somehow they actually insist on reality, because what they say is that, okay, you go to Euclidean time, and there is just this A that you have to take imaginary. If you do that, actually the metric is real, that is nice, so you compute the on-shell action, and then you go back. So for some reason, they insist on reality, because, okay, I think... Yes. So we will come back to that, and of course, and will be related to the fact that eventually it's very natural to consider complex saddles. Yeah. Sorry, I didn't understand. Which solution you would like to consider? But those have a singularity at the origin. No, they do not appear. Because thermal ADS does appear, but the solution that you are mentioning, no, they do not appear. So I guess that, let's see, they probably, so those are solutions that you do not obtain, for instance, as a limit from the regular solutions. So in fact, I think that this approach shows you why you don't consider them, because if you start with these complexified black holes that have supersymmetric, but they have complex temperature, and then you make you send to zero the temperature, you will never get the black holes that you mentioned, because these are in a complexified sense, these are regular. Well, this regularization procedure, if you want, tells you that what you consider are these regular solutions. Yeah. There is actually another problem that comes to my mind. Maybe I have to think more about it, but it's also not obvious that those solutions are going to preserve supersymmetry. Because you need to make sure that when you perform the orbifold to complexify the time direction, the killing spin are invariant under that. So there may also be a condition that rules them out. But I have to think more about that. Thanks for the question.
Okay, I have a small question.
Yeah.
So in this scheme, do we at least expect that the action is real?
No, the action is not going to be real.
Okay.
But it's well defined.
In what sense? Like well defined
in the sense that I say that you can, so the geometry in a complexified sense is still a disk, a smooth disk. So there is a divergence, which is the UV1, but as I described, the UV1 is simple to remove, and when we remove it, you have a well-defined answer. This action is not real, it's complex, but it's fine.
Okay, thank you.
Okay. Okay, very good. So yeah, I was just mentioning the fact that when we solve this equation, we get two branches of solutions. For Q, I will call them Q plus and minus. These are two functions of A and R plus, and as I said, they come from solving a quadratic equation. These two solutions are related by sending I to minus I. So if these variables are real, they are just one complex conjugate of the other. And this fact will appear, I'm mentioning this fact because it will appear again from the field theory point of view. For most of the part, I will only discuss the first branch, and on the second branch, all the formula will be similar, just up to this substitution. So, okay, with this regularization, we somehow solve the third problem. What about the first problem? Well, at this point that we have these solutions that depend on one more parameter, we can try to define new chemical potentials as the deviation of the chemical potential from these BPS values in the limit that the temperature goes to 0. So we can define what I will call the tau G. G is for gravitational, and tau is just a name, as omega minus 1. So this is the deviation from the BPS value times beta, in such a way that when beta goes to infinity, this goes to 0, and so omega goes to the BPS values. Okay, divided by 2 pi I just for convenience. And likewise, I will introduce delta G as the chemical. So this will be a chemical potential for angular momentum because it's related to angular velocity, and this will be a chemical potential for the electric charge. And here there is a tree just for a normalization reason. So now, as I said, the BPS, the supersymmetric potential must satisfy this relation here. So this translates in a relation among this chemical potential here. So let me write this down. And here there is minus plus 1, depending if we are on the first or the second branch. And this relation here will appear over and over in the following. Yes, sorry. So also here, so this is on the first, yes, sorry. This is on the first branch. And as I said, there are always two branches with this I minus I. And I will just discuss always the first branch. Yes. So supersymmetry imposes this condition here in gravity. So if you require that the Killing spinor is well defined at the tip of the cigar, then you get this condition. If you just require that supersymmetry is preserved at infinity, here you can have a more general odd number. But regularity imposes the plus or minus 1 there. Okay, so finally, that we have this potential here, we can go back and we can write down the on-shell action. So I didn't write before what the on-shell action is, but now we write it and will be function of these variables here, and it turns out that this on-shell action takes a very simple form. Okay. So essentially, this is the grand canonical partition function of these systems of BPS black holes. And in here, notice that I already introduced this variable n that pertain to the field theory, because I'm already using, for convenience later on to compare with the field theory, the holographic relation between the Newton constant in gravity and the rank of the gauge group in the field theory. So these relations relates the size of ADS to the Newton constant. So in the following, I will never write the Newton constant. We always use this n. Now, an interesting feature of this on-shell action is that it does not depend on beta. So remember, now our variables are beta, tau, and delta, but this does not depend on beta. So in particular, we can compute it for these finite but complex values of beta, and then if we want, we can take, we can go back from to, if you want, to the point which is both supersymmetric and extremal, taking beta to infinity, but this on-shell arc will not change. I'm sorry? Yes, yes. This has to do of how these definitions are made. So in this definition, we are not sending I to minus I. Again, these are just details. It's not particularly important. But yes, this, yeah, in fact, it will be important that here you have the same sign. Now, everything that I discussed so far was in this simplified setup in which 2 angular momenta are the same and 3 electric charges are the same, and one can, in fact, write down the general formula. So let me just write it down once for all. In the general formula, this will just be the product of the 3 chemical potentials for the electric charges, and this will be the product of the 2 angular momenta for the 2 chemical potential for the angular momenta. So I've called delta 1, 2, 3, the 3 chemical potential for electric charges, and tau and sigma, the 2 chemical potential for the 2 angular momenta. And this potential here will satisfy a relation, which is essentially the development of this relation here, which is that the sum of this delta A is equal to tau plus sigma minus plus 1. Okay. So now let me go back to the real Lorentzian black holes. These are, of course, the objects that we would like to understand. Okay, so what can we say about these black holes? So first of all, when you impose the SUSY condition, the supersymmetry condition, even before applying the other condition for extremality, this implies the standard BPS relation between the charges. So the energy is equal to the sum of the charges. Okay, so this will be the sum of the 2 angular momenta, and here will be the sum of the 3 electric charges. So this is the standard relation which is satisfied by BPS states in a supersymmetric theory. However, because besides the supersymmetry condition for real black holes, we also to impose extremality, it turns out that these black holes also satisfy, if we write down the charges of these black holes, they also satisfy another nonlinear relation. So the form of this relation is not particularly important, but just let me write it down such that we know what we are talking about. So this relation is surely a different flavor than this one. This is very simple. It's linear. This is non-linear. It's more complicated. And once again, this is the condition that the charges of a black hole should satisfy in order to exist a BPS black hole. So in such a way, such that if you reduce the mass and we get to the extremal limit, then this also becomes supersymmetric.
I'm sorry. Is this a finite temperature?
No, now these are real BPS black holes, so they have 0 temperature.
0 temperature.
Yes.
So is there any kind of extension since you have the supersymmetry at finite temperature?
Yeah, so the point is that, so if we insist, as, the real signal and Lorentzian signature for real black holes, on regularity, supersymmetric black holes should also satisfy another relation. And so they satisfy 2 relations. One is the standard linear relation of supersymmetry, but then there is this nonlinear condition. If the charges do not satisfy this nonlinear condition, there is no regular supersymmetric black hole. If you give up extremality and you work in this generalized, in this complexified world, then you don't impose this relation here, and then, okay, but then all the charges will be complex in general. So here now, I'm going back to the real Lorentzian black holes.
Yeah, so a minor clarification. So some of the terms seems to be dependent on n.
Yes, the point is that so in gravity, all these charges are naturally of order n squared. So you might say that the charges are measured in units of n squared. If you want, you can measure them in terms of the Newton constant. So you need a scale.
Yeah, but it's like it's a polynomial in n, right? It's n to the power 4 and n square. So I'm just wondering that if you fine tune the value of n, there might be some regime where this equation would not be valid.
Let's see, the equation is not valid. So, I mean, this is a classical analysis. And this analysis just says that if the charges do not satisfy this constraint, that you're not going to find BPS black holes.
I see.
They're regular.
Okay, thanks.
Yes, you might find black holes that have these closed time-like curves, but not regular black holes.
I see. Thank you.
But it's purely classical analysis.
Okay, thank you.
Yes. No, in fact not, sorry. So maybe my comment was misleading, in fact. No, as you see, the powers are not, so for large black holes, all the charges of order n squared, but still n appears because, let me see. Oh, yeah, no, you're right, it disappears, yes. Okay, so because of this nonlinear constraint, in fact, we can express one of the charges in terms of the other one. So for instance, we can use J of Q, and it means that there is only Q is the only Q, and in fact, there are some inequalities that one has to solve. So this parameterizes the black hole. So at this point, we can take these black holes. As I said, we can compute the entropy. So I didn't write what the entropy is, the Bekenstein-Hawking entropy. And it turns out that this entropy can be written as in a simple way if we actually use both variables. But of course, we should remember that one is a function of the other one. I'm not writing the relation between J and Q that you can derive from here as some relation that you can write down. So this is the entropy of the black holes. So now what we can do is to go back to the quantum statistical relation that we had before, and we can express the entropy as a function of the grand canonical, of the free energy. So remember that it has the following form. And now we can express these potentials omega and phi in terms of the new potentials that we have introduced there. And if I do that, I get the following. So there is a piece that in fact is 0 for BPS black holes. And what is left is precisely what we would expect for the Legendre transform of the free energy. So we see from this expression that is very natural, although I introduced those potentials there in some way that might look arbitrary, we see that in fact it's very natural because this new potential precisely couple in the canonical way to the angular momentum and the charge for the BPS black holes. And so in fact, we see that the entropy, the microcanonical entropy, is just the Legendre transform of the minus the supergravity action, or if you want, the logarithm of the grand canonical partition function. However, the only thing that you have to be careful about is that it is a constrained Legendre transform, because really there is a relation between these two parameters, so really there is one independent parameter. But apart from that, the microcanonical entropy is the Legendre transform of that. So we discovered the standard result in statistical physics, but we see the role played by these new potentials that are very natural, in fact, when we discuss these BPS black holes. Now, when we do this Legendre transform, and of course you can check, one can check explicitly that if you take the expression that I just erased, okay, here if you take this expression, that was this I pi n squared, delta cubed over tau squared, and you do this constrained Legendre transform, you precisely reproduce this expression here, of course, in which j is a function of q. So this can be checked explicitly. So now when you perform the Legendre transform, you in fact fix the chemical potential as a function of the charges. So this fixes tau as a function of q. And in fact, one can even write the expression. It's not too difficult. Of course, here the entropy has to be written in terms of the charges, and J is to be written in terms of Q. And this relation is a complex relation. However, what we can do, we can take real charges, so we can trace the behavior of real black holes, and we can see this complex variable tau will draw some curve in the complex plane. So this chemical potential tau lives in the upper half plane. And we can draw a curve that this expression forms. So it starts with at the point 1/2, and then it goes to 0 in the upper half plane. So this is essentially the curve that represents real black holes, so black holes with a real charge in this space of chemical potential. And in fact, this is the first branch. And there is a similar curve which is represented by the second branch of solutions. And I remind you that on the second branch, we get exactly the same grand canonical partition function, although the map is different. In fact, it is also nice to write this not in terms of tau, but in terms of q. And for a reason that will become clear in the next lecture, well, we define q in the standard way as 2 pi I tau. Okay, then this q lives inside the disk. And for some reason, it's convenient to write q to the power 1/3, just because the various functions involved, and we will be clear in the next lecture, will be multi-valued in terms of q. And there are some curves in this disk that are that represent the real black holes. These curves look something like this. Okay. So now an interesting observation, and with this I will conclude this lecture, is the following. And in fact, this is something that I learned from Seo Kim. So I hope he forgives me for mentioning this, which is very nice. One can regard the quantity 1 over imaginary of this tau g as some sort of supersymmetric temperature. Of course, this is not the true temperature. So these are BPS black holes. They have 0 temperature. Nevertheless, and in fact, this tau is the chemical potential for the angular momentum. But let's try to interpret this as some supersymmetric temperature. Then if we draw the very same curve, but as this supersymmetric temperature as a function of the charges of the black holes, we get a curve like this. And so, perhaps surprisingly, we find that the thermodynamics of these BPS black holes is qualitatively similar to the thermodynamics of non-supersymmetric, like Schwarzschild black holes in ADS. So when these black holes are small, they behave like black holes in flat space. And you remember that for black holes in flat space, they have negative specific heat. In particular, when the black hole evaporates or emits radiation and becomes smaller and smaller, then it also becomes hotter. So as it loses energy, it warms up. So it has negative specific heat. And we see that here for small black holes, so this is the region for small charges, these supersymmetric black holes behave in a similar way. Of course, they do not emit, and they do not have specific heat because this is not the true temperature, but in terms of this supersymmetric temperature, they behave in the same way. So we can call this part of the core as small black holes. And on the other hand, if you take a Schwarzschild ADS5 black holes, when it is very large, instead, it behaves like a more normal thermodynamic system that has positive specific heat. So in particular, the larger it is, so the larger is the mass, the larger is the temperature. And here we see a similar behavior. So these are the large black holes. So this point here is somehow at order n squared. So large black holes are black holes whose charges in units of n squared are order 1 or higher, and instead the small black holes have charges which are smaller than order n squared. And as we will discuss in the next lecture, in fact, our focus will be on the black holes here, on the large black holes. Okay, and I think that this is a good place to stop for today.
Okay, thank you very much. More questions to Francesco?
Are we taking some order of limits here where we first take the BPS and then the temperature going to 0? Because there is a beta times E minus 2j which you made 0, right? Beta should be infinite there and the term in the bracket is 0.
Yeah, so this relation, so let's see. So this is...
so here it's at finite temperature and then you take it to...
Yeah, so here, I mean, when we write this relation here, so this is valid for generic values of the parameters. And in particular, you see that in this regularization, the nice thing of these regulations that I mentioned is that you don't have to take limits because you can take a complex temperature, which is not 0. And you have supersymmetry, so you work with your supersymmetric system. But the nice thing is that the on-shell action does not depend on beta. So you don't have to take any limit. And now this is 0 because you have supersymmetry, but you don't have to take a limit. And this new chemical potential naturally appears. And also there, well, it's no longer there, but in the definition of these parameters, they look like beta omega minus 1 divided by 2 pi I. So you don't have to take a limit here. Of course, if you want, you can take a limit beta to infinity, and then you go back to the point, if you want, at the origin of this complexification space in which the black holes are both BPS and extremal, and so there will be the analytic, there will be the Wick rotation of real Lorentzian black holes, but you don't have to do it here.
So this is valid for any beta?
Yes.
So can you repeat this story for black holes with additional charges? I have in mind something like, magnetic charges or acceleration parameters, or do the supersymmetry conditions get spoiled?
Yeah, so this is quite general. I mean, of course, the details might vary from setup to setup, but this is very general. And in particular, it does apply to black holes with magnetic charges. Now, in the case of black holes with magnetic charges, I believe that you don't complexify the magnetic charges. You only complexify the electric with respect to the electric variables. And this is related to the fact that, for instance, you usually work in the grand canonical ensemble for electric charges, but microcanonical for the magnetic. Yes, I don't think that in order to regularize you have to do anything with the magnetic charges. But apart from these details, the very same story applies. So BPS black holes satisfy not just one relation, but two relations. So you lose two variables. And you can relax this by working with complexified black holes. And then it's just one relation that you impose. And everything goes through.
Okay, thank you.
Okay, more questions? Maybe the disappearance of beta in what all the calculation you do. I guess that's a regulator that appears in the definition of index. Some index is independent of some fake parameter.
Yes, yes, exactly.
So
this
that
fact
beta is that parameter.
Yes, exactly. So in the index, well, we'll discuss this tomorrow, but in the index there is some e to the minus beta for some Hamiltonian, some supersymmetric Hamiltonian, and this beta is the same beta, and the fact that the index does not depend on this beta matches with the fact that the on-shell axis does not depend on this beta. Yes, thanks.
Further questions to Francesco? Okay, if not, let's thank him again.
Thanks.
And we'll resume at 3:50, I guess. Yes.
Okay. Okay.
So I guess this is your second talk, right?
Yeah. Yeah.
핑계치느라 보기는.
아니 뭐 저는 별로 한 거 없습니다. 그 윤정근 박사랑 김석 교수님이 거의 다 많이 해주고 어저께 오셨어요?
어젯밤 늦게 오셨어요. 일정 내좀 있었어요.
알겠어. 예. And yes. Yes.
You don't need to.
You had better because there is some technical issues. So
What's this?
technician asked us to connect the HDMI so that they can record it. So it's better. So
it's better to
yeah.
use it. Okay,
Yeah.
I see.
So for Zoom it's okay, but
Okay. And this is for your car.
I think it's fine. Now it should. Now it should be fine.
Fully charged?
Yeah, yeah.
But
Fully
just in
charged.
case, I will let.
Okay.
Yeah, leave it here.
Yeah, I was just afraid in the morning that if I use it in the morning and then now that maybe we would not have enough charge, but if now it should be fine. Yeah. Thank you.
네, 아니 뭐 그쵸. 그 주위에 쭉 돌리면 되니까 그건 그쵸. We are going to resume the session soon. I hope everybody came in. So.
Yes. No, no, no. That's it. Okay.
Okay, then we'll start this session. Gustav Joachim Triachis, second talk. He'll talk, continue his presentation. Okay.
Okay. Thank you very much. Yeah. Let me begin with some comments that I already made before, but just to remind you, I guess it wasn't too long ago. So when we talk about the conformal symmetry that the putative dual one-dimensional CFT has, it acts, as I said several times, in this way on times. And this symmetry is explicitly broken by the Schwarzschild theory to only translations. And one can think of this Schwarzschild mode as I think Maldacena gave this name, the time superfluid mode, because it appears from the breaking of this time reparametrization invariance down to SL2R, down to the broken to time translations.
And the Schwarzschild theory controlled this breaking. And again, as I said last time, C has dimensions of length, is the coupling of this Schwarzschild mode. And the CFT approximation is good at short times or small betas. And the conformal symmetry is lost at large times or large betas. Let me say very briefly the Euclidean perspective of where the Schwarzschild comes about. So this is the derivation by Maldacena, Stanford, and Young. So again, the Euclidean black hole is this flattened version of it. The cigar is a hyperbolic disk with the horizon at the center. And we can write the Schwarzschild mode f of t in terms of this little f. This little f is the what would be the coordinate in the Rindler patch. So the Rindler patch corresponds to this little f of t equal to t. Is an element of this first one. We can integrate out the dilaton, which tells you that r plus 2 is 0, so the bulk term of the action is 0. And then what that paper showed is that the whole JT action reduces to the Schwarzschild, which comes from the Gibbons-Hawking term. And the C, which is proportional to the boundary condition on the dilaton A, comes from this dilaton here evaluated at the boundary. And this result is also true in the presence of matter, as long as the matter doesn't have a source on the boundary. And if one adds a source in the boundary for the matter, like we did with the shockwave, then you had to add an extra term that couples this Schwarzschild mode to the specific source. Yeah.
Yeah. To the previous slide. So low temperature, is it beta small or I mean, is it opposite or temperature?
When the temperature is low, beta is very large, and when beta is larger than C,
yeah,
or the temperature is smaller than 1 over C,
okay,
then the interaction with the Schwarzschild that breaks the conformal symmetry is important. So this is large times or small temperatures.
Okay. Yeah, thank
you. Okay. So before I move to quantum effects, let me say a little bit about the thermodynamics of these ADS2 black holes. Like we saw in the previous talk, this is extracted from the Euclidean path integral. At least this is a way of defining what do we mean by the thermodynamics of the dual quantum system described in the black hole. So again, the black hole solution in Euclidean signature is this choice of f of tau. Again, if you remember this big F is the coordinate in Poincaré, and the little f was the coordinate in the black hole patch, which on shell is just equal to tau. And we can just compute the on-shell action of this geometry, which is S0. This comes from this topological term I mentioned before, and we have a disk, so that tells us that the Euler characteristic is such that this coefficient is 1, the way I defined it. Of course, this is why I defined S0 in this way. And then we need to compute the Schwarzschild action in this particular saddle, which corresponds to this black hole. And this is easy to compute, so this has a constant Schwarzschild given by this function of temperature, and then the free energy, or the logarithm of the partition function, is S0 plus this correction of order C over beta. Where is it? Ah, there.
Can I understand that the black hole evolution of time, isn't it? Can I understand this time-dependent solution as that the black hole evolves as time flows?
No, this is an eternal two-dimensional black hole. What this time dependence means is just the change of coordinate of going from Poincaré time to the Rindler patch, which is this black hole patch. So that's this transformation here. But the black hole is eternal in this case.
Okay, thank you.
Thank you. Yeah, so the question is, what is this patch means for the higher dimensional perspective?
Yeah.
So this is what I showed before. So you have the Penrose diagram of the near extremal black hole. This is the patch that gets picked by looking at the region of ADS2 in the near extremal black hole.
Yes, but that's when you look from the near ADS2. Like, but
from the near extremal black hole, that picks this patch of ADS2. The near extremal black hole has a preferred time, which is the time that becomes just the flat space time at the boundary, and that picks the Rindler time, not the Poincaré time of the ADS2 patch.
I see. Oh, okay.
Yeah. Yeah.
The core solution, right?
This is the way the black hole solution manifests itself in the Schwarzschild theory.
Right, but here is not from the metric or whatever, right?
Well, the metric is ADS2, but as I described, the way to describe the way to specify the solution is to specify what patch you are in, and this function determines what's the patch where your boundary theory.
Oh, okay. So
yeah.
Here, how do you fix f tau then?
Well, if you look at, for example, one way is that you can look at the equations of motion of from the Schwarzschild theory, and it will tell you that this is the solution. So the black hole appears as a classical solution of the Schwarzschild theory.
Without looking at deep inside the black hole, is this can be fixed by just looking around the boundary behavior? Or
yes, you could say that way. So this is the boundary graviton on ADS2, and this profile of this boundary graviton tells you which patch of ADS2 you're looking, and therefore whether you have a black hole or vacuum ADS2.
yeah, if that is the case, it's okay.
It's okay. What do you say?
Yeah, if this can be fixed just by the boundary behavior, it will be. I'm satisfied.
Ah, okay. I mean, of course, if you add matter, that affects this mode too. But yeah, okay. For example, in the example I showed, even if you have the matter in the bulk, then that affects the dilaton, and that back reacts on the boundary graviton, and because it moves the boundary. So things that are in the bulk can still affect this boundary mode, but okay. Okay, so we can compute the energy from this free energy by taking the there is another question.
I mean, I just got confused. This f of t has a singularity at tau equal to beta by 2. Is that the horizon, or?
T has a singularity. That's definitely not the black hole singularity. That's just a bad feature of this choice of coordinates, but it's all right. Yeah.
Okay.
You can move it around by an SL2R transformation, for example. Not the SL2R that is broken, the one that is not broken, the one that acts on F.
I see. So the integration limits of tau would be from minus beta by 2 to beta by 2.
Yeah.
Okay. Thank you.
Okay. But here the Schwarzschild, for example, is finite and is constant and independent of tau. So this is one way you can see that when you compute physical things, that they don't have any issue.
In the previous slide, you had just here.
Yeah.
You had said f of tau belongs to diff S1. How did that get fixed?
F
of tau belongs to diff S1. That
yeah.
So how did that diff S1 come in?
How did the diff S1 what?
So in the previous slide, if you go back to the previous slide.
Yeah.
So f belongs to diff S1 there.
Yeah, so f has to be a reparameterization of the boundary time or the time in the hyperbolic disk, so it has to satisfy these two conditions here.
So you are only considering the single winding sector. The other winding sectors are all.
Yeah. Okay. I'm restricting to Okay. The other ones are configurations you can add, but they are not. I would say that's not gravity. That's something else you will compute in this theory. So gravity tells you should restrict to single wind sector. Okay, so we can compute the energy from this thermodynamic relation, and you get summary proportional to Ct squared. This is proportional to T, so you can check it yourself. The entropy is given by this S naught plus something linear in T. Again, this is just this 1 over beta. This satisfies the dilaton gravity version of Bekenstein-Hawking in the sense that the Bekenstein-Hawking entropy is the dilaton evaluated at the horizon, which here is the total dilaton including phi naught divided by 4g Newton. And if you evaluate the dilaton at the horizon, then you reproduce this S naught plus 4 pi squared Ct that here we got from the Schwarzschild. And of course, if you think about the higher dimensions, the dilaton is the area of the sphere, so this is literally Bekenstein-Hawking. And we can go back to the 4D charged black hole and compare, and one can verify that m minus q has this form, and the entropy has this form to linear order in temperature. Here, these higher order corrections come because, at least classically, if you increase the temperature, they are suppressed by the temperature, because if the temperature is too large, then of course you go away from the near extremal limit. But in a low temperature expansion, this is the first correction that appears, and it matches the JT term. Actually, if you do the reduction I described before more carefully, you'll see that S naught is pi q squared. Here I'm using units, I should have said it. I'm going into units where G Newton is 1 just to simplify the formulas. So what you get from the reduction is that S naught is pi q squared, and it's the same that you get from the extremal area. And then this coefficient C is computed to be q cubed. And this we get from comparing the thermodynamics, but you could also get this same formula by deriving, so the near horizon geometry is ADS2, but then you can see to leading order in deviations of ADS2, how does the dilaton behaves, and then that would tell you what A is, that parameter that I introduced before. And if you do that, you will get that A is q cubed, and it matches with it will produce the same thermodynamics. So you can either obtain it by doing the dimensional reduction more carefully, including the leading corrections near extremality, or just comparing like this. And then you can go to your favorite near extremal black hole and compute S naught and C. For example, the black holes that Francesco described has the same, they have more charges, and these formulas are more complicated, but if you look at them at low temperature, they also have a T square correction to the mass and a linear in T correction to the entropy, because they have ADS2 throat, as he said. Okay, and finally, this is just the general dilaton gravity formulas. Let me skip it just for time, but if anyone else. And finally, the last thing I wanted to say about before I move on to quantum effects is that you can study black hole evaporation by adding matter and changing the boundary conditions at your ADS2 boundary. So if you just add matter and put reflective boundary conditions, the black hole would be eternal. But we can put absorbing boundary conditions, or we can couple ADS2 throat to the flat space where it lives, and then the black hole will evaporate. And the way it can be tracked is by writing the equations of motion for the energy of the black hole, which is proportional to the Schwarzschild. And then this will be equal to, for example, for the case of a 2D CFT matter, it will be proportional to the energy flux that the matter is taking away from the throat, which is proportional to the Schwarzschild itself. And okay, one can compute the solution of the classical solution of this theory and see that the entropy of the radiation of this matter is increasing, the entropy of the black hole is decreasing, and one can reach a similar information paradox type issue when these two quantities are the same. Let me see. Yes, I'm assuming large central charge to avoid quantum corrections from the Schwarzschild. Yeah, sorry. Okay, so, but again, this is quantum matter, but it's classical gravity because we are doing classical JT gravity. Okay. Just as a summary, classical dynamics of JT plus matter can be encoded in the dynamics of the boundary mode. To get a sensible decoupling limit, we should include effects that break the conformal symmetry, and the last thing I mentioned, treating gravity classically and matter quantum mechanically leads to an information paradox, just as it does in higher dimensions. Okay. So now let me start with the quantum effects I wanted to discuss for this lecture. So we got this free energy from the black hole, we got this free energy, and entropy, and we saw this reproduce the Raison-Nordstrom for this choice of parameters. Another way to present the entropy is in microcanonical ensemble as a density of states as function of energy. And if one do a Legendre transform of this free energy, one gets that the prediction is the density of states that grows exponentially with S naught plus square root E. So the density of states will have this form, will grow exponentially as the energy is increased with square root E. And the question we want to ask is this, how reliable is this? For example, is S not counting a large number of ground states? And holography in this sense implies something striking, which is that there is a quantum mechanical system with no obvious symmetry protecting a very large number of exact ground states. And this is kind of surprising. But we will see in this lecture that this is a little bit too naive when we include quantum effects, quantum gravity effects from the Schwarzschild mode. And there's another issue that is related that was pointed out a long time ago by Presky et al. In this paper, which is that the thermodynamics of a near extremal charged black hole indicates a breakdown of its statistical interpretation. You can see it in the title of this paper. The problem arises because the energy vanishes quadratically at extremality, but at low enough temperatures, the energy available by the black hole is less than the energy that is emitted by a Hawking quanta, which is of order T. So there should be a breakdown of the statistical description of these black holes when the temperature of a Hawking quanta is comparable to the energy available by the black hole itself, namely where the T is of order Q cubed T squared. This breakdown happens as 1 over Q cubed for Reiser-Nordstrom, but in general is expected to happen as 1 over C for any ADS2 throat. And the expectation, but was not understood very well, is that quantum correction should become large and produce a gap that removes states below this temperature, but it was not very clear how this works in gravity. Particularly, these black holes are large, so then finding quantum corrections near the horizon is a little bit surprising from that perspective. But we'll see that quantum effects from the Schwarzschild mode are actually important near breakdown, the breakdown scale, and this is actually the scale in which I said that the fluctuations of the Schwarzschild mode have to be taken into account. And finally, we'll also explore the effects that quantum gravity made in matter correlators. An intuition for why this might be expected is the following. So as I said, the length of the throat is logarithmic in temperature. But something very special that happens in the extremal limit is that at 0 temperature, the throat is infinite. So then the length of the throat becomes a metric zero mode, namely, we can vary it, we can make very large variation of the length of the throat, but it doesn't affect the action, which is independent of the length. So the fact that the action is independent of the length of the throat means that there is a zero mode coming from the metric. Because it's a zero mode, it should be quantized, and this 1 over C, or this breakdown scale, is the scale at which the quantization is important. Okay. Let me first make some comments about JT with matter before I study quantum effects. In gravity, when we do the path integral over the dilaton, this simplifies a lot when the matter does not couple to the dilaton. And the reason is that, as I said several times, the dilaton is a Lagrange multiplier that imposes r plus 2 equals 0. And then we can integrate out the dilaton, then reduce this as an integral over hyperbolic metrics, which is just the hyperbolic disk up to choices of the boundary curve. And the action reduces to the Schwarzschild. And integrating over the Schwarzschild means to include gravitational back reaction. And this is not affected by the presence of matter, as I will describe in a couple of slides, unless we add sources for the matter, which for now we will not do, but we will do that later. And then we can do the path integral of this Schwarzschild mode and compare that with the partition function of the putative quantum system that is dual to it. And then ask, for example, is it the sum of delta functions or not? Does it have finite entropy or not? And how does it look compared to that classical curve that I showed before? Okay, so let me compute this partition function. So as I said, the saddle point gives me that little f is equal to tau. This is the hyperbolic disk, and this is the classical action again. But then to leading order, we can include deviations around tau. Is equal deviations around f equals tau. And then to leading order, it will have some quadratic piece proportional to epsilon squared. So epsilon is a small parameter. And then from gravity, we can derive what the measure is of integration over this Schwarzschild mode, starting from the gravity path integral. And I'm not going to go through the derivation, but the final answer is this. So it's a very simple flat measure in this epsilon space. So if one does this one loop partition function, we get the classical answer here. And then there is a product over the eigenvalues of the quadratic part of the action, which gives the one loop determinants. And this if we do this by zeta function regularization, we end up with this result that the one loop determinant is a product of C over beta to the 3/2. And the origin of the 3/2 is because a product, well, in zeta function regularization, a product over from minus infinity to infinity will roughly give you a constant. The 3/2 come from the fact that we need to remove 3 modes, which are the ones that generate the SL2R symmetry that we have to gauge. So as I said, there is a broken SL2R, but there is one SL2R symmetry that is exact, and we need to gauge. And removing those 3 modes from epsilon of tau leaves us a factor of beta to the 3/2. Oh, and I didn't write it, sorry. Thank you for the question. So I'm doing a Fourier expansion of epsilon, yeah. So, yeah. Let me see. Yeah. So I'm doing a Fourier expansion of epsilon. So the epsilon n's are the Fourier coefficient. Is that okay? Yeah, sorry, I didn't realize I forgot to write it. Yes. So epsilon n are the Fourier modes, and so n is the Fourier modes. And as I said, it's an element of difference 1, so the epsilon should be periodic in tau, so that's why we get this discrete set of frequencies. And then the product is over all the frequencies. Is that okay? The what? Sorry.
So this epsilon n's large n behavior is known or not?
Epsilon n. I mean, I have to integrate over epsilon n. So I need to integrate over all.
You need to integrate over epsilon n.
Yeah. I'm doing the. Sorry, let me go back one slide. I need to compute the partition function. I need to do the path integral over this Schwarzschild mode itself. And I do the integral over the FS1 mod SL2R, where the SL2R removes this gauged SL2R symmetry. So here I'm expanding around the classical solution, so I need to integrate over epsilon.
I see. So epsilon n is not on the energy spectrum, you see.
Oh, no, sorry. Epsilon n is just the Fourier modes of these fluctuations around the classical solution of the Schwarzschild mode. Yeah, nothing. No, thank you for the question. I should have added some formula here. Yeah, so then I just basically plug this in the Schwarzschild derivative and expand at small epsilon. That's what I'm doing. That's what I'm doing. And then that gives this funny n dependence. This is an approximation at small epsilon, but yeah, if you think of this in terms of C, then this will be valid at large C. Yeah, you can think that if you absorb the C in epsilon, then the higher order terms will be suppressed by 1 over C. Yeah.
There is a question in Zoom, and that is how was the measure determined? How was the measure determined?
Yeah, so there. One way to compute it that was done by Satchenka and Stanford is to go to the first order formulation of JT gravity and writing it as a SL2R BF theory, and then you can translate this Schwarzschild mode into some mode in the SL2R connection, and from the standard measure of in BF, symplectic measure in BF theory, you can deduce this. So this is from first order. And then there was another paper by Trivedi where they do it in second order. They use a ultra-local measure from gravity. It's the standard choice. Yeah, you define the measure over the gravity to be ultra-local, and then you reduce it to this space of the boundary gravity. Yeah. Huh? Yes. Yes, it is. Yeah, so those are the ones that I said, I mean, I didn't show it explicitly, but those are the ones that you can rewrite as SL2R transformations. The gauged SL2R, not the broken one. So those are that's why they don't appear here. One way to see also that they have zero action, for example, so they are really symmetries. Well, of course they have zero action to all orders, but so if so you need to remove them by hand because they don't really generate different geometries. They are related to the isometries of ADS2, and you should not overcount them. And then they give rise to these three halves. Any other question? No. Well, I'm going to say in the next slide also that there are no higher corrections, but
really?
in principle they would be, yeah. From higher dimensions, I don't even, well, it means the same as from 2 dimensions. It's just that if you...
What embodied is, wouldn't it move around the black hole patch up and down?
Yeah, but they are related by SL2R symmetry, so they correspond to the isometries of ADS2, so you should not overcount them. So one way to think about it is that you can write the fluctuation in the metric that would come from so you can go to another gauge where you fix the boundary to be straight, but then this Schwarzschild mode will appear as a different metric in the bulk. And then you will see that if you do an SL2R transformation, it will give you the exact same metric. So then it just, in that sense, it's gauge. It doesn't generate different metrics if you start from the integral over metric. You will be overcounting metrics because of SL2R isometries of ADS2. Yeah. Okay. Is there any other question, perhaps? Okay, so, well, I didn't say it, but the measure is defined up to an overall constant that can be absorbed in S0 anyways. And when sources are turned off, the same applies for matter, actually. If you do the one-loop evaluation of matter path integral around this ADS2 geometry, then to leading order, if the sources are 0, their contribution doesn't couple to the Schwarzschild mode, and one can compute those independently, and they will just give at most powers of S0. So they give something that is independent of temperature. And these are important sometimes, for example, in this quantum entropy story of Sen, where these temperature-independent coefficients that are absorbed in S0 produce logarithmic corrections to the Bekenstein-Hawking extremal entropy. But for the purpose of this lecture, we will just imagine that those are absorbed in X0, and we will not worry about those. But this is only when the sources for the matter fields are turned off. Another comment is that this result was shown to be exact by Stanford and Witten. Let me forget about this caveat. It's not too important. I don't think I will have too much time anyways. And again, as I said before, the quantum effects become large at low temperatures. And one way to see it is that now in terms of the free energy, this produces log T corrections. And if beta is much smaller than C, or times in the UV, high temperature, small times, then this logarithm is much smaller than the classical term proportional to T. And then the classical approximation is good, and the Schwarzschild mode fluctuations are suppressed, and you can forget that you are breaking the conformal symmetry. But when beta is very large, then this classical term in the area goes to 0, and now the logarithm can win on the quantum effects. So this is a concrete manifestation of how this quantum effect can become large. Yeah. Yeah, so they're important at temperatures that are lower of the scale 1/c. So the boundary, let's say if C over beta is large, then the classical approximation is good. If C over beta is small, then the classical approximation is bad. Yeah. The what?
Exactly.
Okay. Yeah.
I mean, maybe because I'm an ignorant, but this Schwarzschild action looks really horrible. And does it mean that it's secretly Gaussian over that center point, or what?
Yes. Yeah, actually, it is one way to. So the way they phrase it in Stanford and Witten is that you can apply. So this DFS1 model 2R is a symplectic space. So you can think of it as a phase space. And the Schwarzschild is the generator of U1 translations. And then you can apply this Deuterman-Heckman theorem to this, or at least a generalization to infinite dimensions because it's a functional integral. And that's one way to see that it's exact. Another way is that, which is a way to even to show the Deuterman-Heckman theorem, is to add fermions. Because basically this measure is the symplectic measure that.
So the hidden symplectic localization structure.
Yeah.
Okay, I see.
But you can also, yes, there is a paper of Adran and Bagretz and Kamenev where they observe that if you take this f and you do this change of variables, so you go from f to phi, where f dot is e to the phi, then the Schwarzschild actually becomes Gaussian in phi. Becomes phi dot squared. But it's not completely. So it is Gaussian in some variables, but it's not completely. There are some subtleties with that calculation at finite temperature, but you might be able to show it that way too. Okay. Let me see. Yeah. Okay. Yeah. Yeah.
So there is some kind of a minimum in the log G. So is there any phase change in the as a temperature change?
Sorry, I couldn't hear the first part. There is a minimum in what you said?
So is there any phase transition in temperature? Because log G has a minimum, right?
Rho of.
One is an increasing function and the other one is a decreasing function.
Yeah. Well, in a sense, this C over beta order 1 is a transition between the conformal behavior and a quantum behavior that breaks conformal symmetry.
I see. So just a conformal symmetry breaking.
Yeah. So yes, you can think of it as a conformal phase or a nearly conformal phase and another phase where all the symmetries are broken and these quantum effects are large. Other than that, I don't think this is a.
So is that the transition between gapped and the ungapped? Is that the?
No, not really. Actually, there are a lot of low line states. So let me go to the next slide and maybe you can.
All right.
Yeah. Okay. So you can look at the density of states that comes from this formula, and it actually has a very simple form. It's this. Is proportional to e to the s naught, but then as a function of energy, it gives a hyperbolic sign instead of just. So the exponential would be the classical behavior, but this exact partition function gives this sinh that at small energies it goes to a square root law near the edge. And so the correct interpretation is that this scale 1/c is not really a gap scale, but it's just this breaking scale where these quantum effects become large. And the system at low energies is not really gapped. This still has a, well, one expects gaps of order e to the minus s, but that's a non-perturbative effect we will talk about in some toy model tomorrow. But other than that, there is a very dense spectrum, but yet the conformal symmetry is still broken. Of course, the nice thing about SYK is that it gives a very explicit quantum system where all this behavior can be seen. Of course, it should also be there in quantum system duals to black holes with ADS2 throat, but at least the ones from string theory we don't really understand well enough. And the second observation that will be important for tomorrow's lecture is that this is not the sum of delta functions. So you could imagine that maybe perturbative gravity effects will turn the density of states into something discrete with finite entropy. But and usually one is not able to compute perturbative quantum gravity effects because in general it's not even a well-defined question. But here it is a well-defined question. One can compute it and yet it still continues. So to see the solution of this in some simple toy models, we will do that tomorrow. And the only other case where I know of similar calculations can be done is BTC black hole in ADS3, which is also another case where gravity is, one can deal with gravity in these dimensions. Okay. Now, I mentioned that it's very striking that the density of states is large at extremality, but we see that it actually goes to zero at zero temperature. So the ground state degeneracy is not unnatural from this point of view. As we see that it's going to zero. And again, there is no gap. So quantum gravity effects from the Schwarzschild resolve both issues, this gap and this extremal energy, extremal degeneracy. Let me mention, I won't have time to discuss it in these lectures, but one can repeat this same exercise with supersymmetric, with theories in supergravity, and then the conclusion will change. There will be a gap and there will be a large extremal degeneracy, so this is not inconsistent with what we will hear from Francesco in the next slides. This is only true for non-supersymmetric black holes. But at the same time, if you have supersymmetry, then this ground state degeneracy is not really unnatural because there is asymmetry protecting it in a sense. Okay, so let me go on to, yeah.
There have been some, I think, rather ad hoc works in trying to understand the entropy of extremal non-BPS black holes.
By who?
By many people, extremal non-BPS black
Yeah.
holes. Trying to compute entropies from certain recoupling, some CFD calculus, maybe based on some hope with attractor mechanism and so on. How would you assess what they have done with your, energy shift computed using Schwarzschild?
Yeah, so I say what they are computing is S0. And they usually in their papers ignore the Schwarzschild mode. So they're computing S0.
Can you give a more refined sense to the precise quantity they are computing? Maybe some entropy with some smearings allowed or whatever. I mean, so would you just say that what they did is wrong?
No, not wrong, but maybe the interpretation is.
How would you interpret what they did?
Well, that's what I said. I interpret what they did as computing S0. Yeah. But so, for example, they do let's say, you mean like the Ashok type calculation?
Yes.
Yeah. So they compute a one-loop determinant integral over all the matter and gravitons and all you can have in 4 dimensions, whether it's supersymmetric or not. And from their language, there is what they call large boundary modes that are large diffeomorphisms. And they have a finite, infinite number of them that has zero action, which are the Schwarzschild modes. What they do is usually just to ignore them and don't integrate over them and assume that it gives some constant which doesn't affect the final conclusions.
But I guess the states that they think they have counted has been shifted up by some renormalization effects in your calculation. Is that the right way of seeing that?
Well, the result should be multiplied by this function of the energy. Yeah.
Maybe the effect. I wanted to view it as because of this interaction effects of Schwarzian, the states that they have counted at zero energy have been shifted up by certain finite renormalization effect because it's non-BPS, not protected states, and so on. Is that the right way of viewing it?
Oh, I see what you mean. Yeah. So I think that there would be extremal states are somehow spread in some.
Yes, spread it into right side
in
or something.
some window of energy. So
yes.
If you compute the number of states in any window of energy, unless it's too small, exponentially small in S0, it will be of order of S0, e to the S0. So you can think of the result as computing the degeneracy in an energy window of order 1, let's say.
1 from 0 to what? 0 to 1 over C?
0, 1 over C, yeah.
Okay.
I just mean not for example, not exponentially. If you do a window of size e to the minus S0, then of course that will just give you like one state or one state. But if you take average over energies of order 1 over C, then then that will be computing what they computed.
Okay,
Yeah.
thank you very
okay.
much.
Yeah,
Thank you
thank
very
you. So now I.
Entropy as a function of T scale? I mean, remember there was how do you solve this issue of Prescale and those guys?
Well, for example, if you compute the energy, including this log correction, the energy, the log correction will produce a correction to the energy proportional to T. So then the energy of the Hawking radiation never gets smaller than the energy available by the black hole.
Oh, but now I realize that if you are not doing PPS black holes,
yeah,
then they don't need to have a Hawking radiation. They can just black hole can split. That's what happens. So I don't know why. I don't see anymore why we need temperature.
Oh, that's true. Maybe in that case it's not very well motivated. But
right.
in the case of VPS black hole, these quantum effects do become
Right,
large.
of course.
Also.
Yeah, if
so maybe the motivation is not as good in that case, but it's still the quantum effects are still there.
Oh, okay. So you are saying there is a linear in T correction from this calculation.
Yeah.
Okay.
Yeah. In the case of supersymmetric case, you actually get a gap. This 1/c. The density of states goes to 0 here, and then you have a large delta function. But yeah, perhaps at 0 temperature, that motivation is not that clear. But one of the conclusions of this is that you should never really work at 0 temperature. You should work at some small temperature and then send temperature to 0 in the end to make sure you're not missing anything. And then you have to break a little bit supersymmetry or go to the complex saddles. Okay. Okay, so let's add matter now. So again, as I said, even as long as the matter doesn't couple to the dilaton, we can integrate out the dilaton, and the integral over matrix reduced to a boundary mole. Then we need to integrate over matter, which is doable for a free bulk matter. So we are going to focus on free fields in the bulk. This is just the only case I know how to solve explicitly. And then at the end, we will integrate over the Schwarzschild mode. And again, this is interpreted as the gravity back reaction. So just to write it more explicitly, we integrate over phi and g. This reduces to an integral over the Schwarzschild mode. And then the integral over the matter needs to be done. And this integral over the matter can depend itself on the Schwarzschild mode, where phi v is the Dirichlet boundary condition on the matter. If we don't turn on sources and this phi v is 0, then the matter part is independent of the Schwarzschild mode. But of course, if we turn on sources, then that's not the case anymore. And for a free matter field, scalar field, the matter partition function has this expression. So it's the exponential of something quadratic in phi because it's a free field in the bulk, and this kernel is just the 2-point function, the reparametrized 2-point function. Sorry, the reparametrized boundary 2-point function of the dual operator to this matter field. So then we need to integrate over the Schwarzschild mode, including this coupling to this extra coupling to the boundary sources. And here phi r is the boundary value, so this is not dynamical. This is the source we decided to turn on for the scalar field. Yeah. So.
The order of integration. Is the order of integration is important? I mean, while doing this.
Yes, it's important because otherwise I will need. Let's say I decide to integrate over the matter first. Then I will need to have the partition function for any metric. But first I integrate over the dilaton that restrict to rigid ADS2, and then the integral over matter can be done with a fixed geometry. And then the coupling to gravity appears only through this coupling to the boundary mode. So the order is important to get. I mean, perhaps one can do another order, and the answer should be the same. I just don't know how to do it explicitly with any other order. So I'm just doing the only thing I know how to do.
Thank you.
Any other question? Okay, so a way to understand where this answer comes from is that I already mentioned. Imagine we turn off the Schwarzschild mode, so we remove this boundary graviton. Then the matter partition, the logarithm of the matter partition function is this, which again, this is just the generating function of boundary correlators when they are free. I mean, free bulk correlators. Of course, this has to be obtained from some strong coupling of a boundary quantum mechanics. And then the generating function is just this. Well, one way to see why this is the boundary correlator is that you can start with the boundary correlator in Poincare time, which is just 1 over the difference in Poincare time to the power 2, and then you can do it to a power delta if you have
non-trivial scaling dimension. And then this answer is just obtained by reparametrization that transforms from the Poincaré coordinates to the black hole coordinates. And then that's where this 1 over sign comes from. So this is fixed by the conformal symmetry again, because before we couple to the Schwarzschild, this is completely fixed by the conformal symmetry. And this is what the correlator would be without the coupling to the Schwarzschild. And we will see that when we couple to the Schwarzschild, this will be modified to a more general function of T1 and T2. And again, to couple to the gravity is just to promote tau to f of tau and integrate over the Schwarzschild mode with the Schwarzschild weight. And just to emphasize one more time, if we turn off the sources, meaning the phi r's are 0, then the C matter is independent of the Schwarzschild mode. And that's why even with matter, the previous result is also true of the partition function I wrote before. This I already mentioned. Okay, so then this path integral over the Schwarzschild mode with this matter correlator can be thought of as a generating function for the boundary correlators of the dual of ADS2. And we can compute boundary correlators by, as we always do in holography, by taking derivatives with respect to the sources, where the phi r are the sources. The surprising thing in JT is that these correlators can be computed exactly, including these quantum gravity effects. So I'm not going to describe the derivation because it would take too long, and I want to move on to other stuff in the next lecture. But let me just mention the result and some physical implications of the actual results. So let's say we want to compute the two-point function, then this is the calculation we need to do. We have the reparametrized conformal two-point function and the integral over the Schwarzschild mode. Again, if we ignore matter interactions, all correlators will be product of this bilocal, because if we compute 4-point functions, it will be a product of 2-point functions, or 6-point function, product of 3, etc. So the real object we are interested in is this bilocal, which we will denote by a line between tau 1 and tau 2, labeled by delta, which is the scaling dimensions. So we want to compute the expectation value of this G delta integrated over the Schwarzschild mode. Okay. Well, again, okay, I think I already said that. And this is true for always. So in general, we need to write the correlator before coupling to the Schwarzschild and apply reparametrization. But something interesting about the two-point function is that the answer is universal, even if you have interactions in the bulk. And the reason is that the boundary correlator is fixed by the conformal symmetry. This would not be true for a 4-point function, because you can have an arbitrary function of the cross ratios. But the time dependence of the two-point function is fixed, so the result is actually true regardless of having bulk interactions or not. And okay, so this is the final answer that we solve these correlators in this paper. All correlators, and this is particular for the two-point function. It's an integral over two variables k1 and k2, and if you see how they appear multiplied by Euclidean time, then you'll see that k squared over 2c is what you should interpret as the energy propagating between the two operators. And then it's multiplied by this complicated function where the plus minus in the gamma function means that you should take all product combinations. It's just a shorthand notation that is very useful, because there will appear a lot of them in the next slides. And then finally, this sinh is just the density of states written in these k variables. This has the form of a quantum mechanical correlator, as I said. So this is what the quantum mechanical correlator would look like. And again, the energy that propagates here is E1 given by K1 over 2C, and this is E2. And we can read off what this OE1, E2 would be, and it's this function of the energy. So this is extracted from these gamma functions. The matrix element being of size e to the minus s naught square is consistent with eigenstate thermalization hypothesis, where we assume that the fixed energy matrix elements of operators should have this form to reproduce thermal correlators. Okay. The first check we can make is that if we look at very short distances, for example, if we take tau to be small,
then the integral is dominated by large k1s. And then we can approximate this product of gamma functions by using Stirling approximation by this simple power law. And then this complicated correlator becomes the conformal 1 over tau to the 2 delta answer. And this comes from the fact that if you compute a 2-point function at very short distances, then this is indistinguishable to doing it in the Poincaré patch, which is, or doing it in without including the Schwarz-Bach reaction. So you satisfy that at short separation, the correlator becomes the conformal one, or the conformal one even at 0 temperature. Yeah, sorry, here I mean small even at the scale of the temperature. And a more non-trivial check is that at large C, we reproduce the full conformal 2-point function at finite temperature. That takes a little bit more work. We can start with the partition function as an example. If we take large C and beta of order 1, then this reproduces the partition function by a saddle point in energies that comes from between these two terms. And this tells you that the energy integral is dominated by this value, which is what we expect. But then we plug it here and we reproduce the partition function I wrote before. Okay, so we can do something similar with a correlator. Sorry, 1 second. Yeah, something important is that this energy is picked at energies of order C. So these are large energies, so this will be important. So if we apply the same to the 2-point function, then this will be picked if we take large C, but times to not scale with C. This will be picked as energies where both of the energies are of order C, but the energy difference that I call omega is of order 1. I'm not telling you why, this is just something you can derive from the specific formula. But in this limit, the integrand of the 2-point function becomes very simple, especially after you apply the saddle point on E2, let's say. Then E2 becomes a function of beta. And then this is what we get. And this is a function of omega, which is the energy difference. And we end up with this formula where we have an integral over energy differences and this product of gamma functions. And essentially, this is just the Fourier transform of the conformal 2-point function. So then we recover that large C, we recover the conformal answer for the 2-point function. One way to think about it is that the poles of these gamma functions is a sum of the quasi-normal mode spectrum of the matter field. And resumming these poles give you this 1 over sine of tau. But then this has corrections at large C, and these are genuine quantum gravity corrections. And the function of time of these corrections is arbitrary. It doesn't respect the conformal symmetry of the... otherwise, it would be proportional to this. Okay. Say something interesting about these correlators. We can analytically continue them to Lorentzian times. So far, I've been talking about Euclidean times. Then this sign, the sign that I wrote before becomes a hyperbolic sign, and the correlator decays exponentially with time by a coefficient given by delta over beta. And this is just the leading quasi-normal mode of this particle in the black hole. At this point, we should be skeptical that this is true at arbitrarily long time, because I said no matter how large is when T becomes of order C, the approximation breaks down and quantum gravity effects become large. And indeed, if one takes very large times, then essentially what happens is that these gamma functions are negligible. The answer for the correlator actually decays as a power law, 1 over T to the power 3. And here I wrote it in this product because each 3 halves come from the 2 energy integrals. So here we see, sorry.
Real-time correlated? Like, is it Feynman or retarded or like?
Yeah, here I was thinking about the
Whiteman just.
The Whiteman, yeah. But you can do different analytic continuations for different ones, and yeah, I think the only difference will be some phase that depends on delta here, whether what ordering you pick. Yeah. Huh?
At the bottom, last formula.
Where, here?
Yeah.
What did I write?
Same thing twice.
Sorry, what?
Same thing twice in the denominator.
Oh, yeah, because each factor of 3 halves come from each of the integrals over k. That's why I wrote it twice, yes. The integral over k1 gives you one factor of t, and the k2 gives you another one. I wrote it this way because in general, you can know what power you'll end up having based on how many k integrals you have. And this goes as 1 over t to the 3, but that you might think that that's conformal, but not really, because this is a power that is universal and independent of the scaling dimension of the operator. So this is a limit where the conformal symmetry is really broken. Okay. The analysis is also valid when delta is of order. Sorry, the previous analysis is valid for delta of order 1, but we can also ask what happened when delta is of order c, namely when the mass of the particle is of order of 1 over g Newton. And then semi-classically, we will need to solve this action, which includes the coupling to the particle. This can be understood as the formations of the gravity solution, where we're essentially gluing two ADS2 disks through the particle world line. And I don't have time to go over this, but you can reproduce all this behavior that you expect from the gravitational back reaction of this particle can be reproduced from the exact answer I showed before. Yeah.
Power being universal again, like how do you understand the power is? How do I understand the power is universal for 2-point functions or n-point functions? Like.
Well, only the 2-point function is universal because any 2-point function, before you couple it to the Schwarzschild, has to have a specific function of times. It's determined completely except for a prefactor.
No, but how do you understand it's always a 1 by t power 3? Like
it's only a what?
How do you understand all the 2-point functions scale like 1 by t power 3? Like what does it mean?
Oh, that comes from the Schwarzschild actor. Well,
so it's like a one exchange of Schwarzschild or something like that. I mean, is that an interpretation like that?
The interpretation of the 3 halves just comes from the fact that at late times you're looking at small energies, and the 3 halves come from the square root edge of the spectrum. So the 3 halves is controlled by the square root edge of the spectrum and not by the matrix elements of the correlators. So that power is coming from that feature of the spectrum.
Is it like a loop of Schwarzian, extent of Schwarzian, something like that, or is that an interpretation like that? It's a loop of Schwarzian mode or an extent of Schwarzian
not
mode?
really a loop, because yes, this I should have said this. This 2-point even though the partition function is one loop exact, the 2-point function is not. The 2-point function is not one loop exact. It includes any number of loops of the Schwarzschild mode. So it's very non-trivial that we were able to even find such a formula. So you have to the exact solution for the correlators is not as straightforward as for the partition function itself. So when t becomes large, you really need to resum over all the loops if you were talking about
and
loops.
this is the resummed answer, like
it gives this power law. Yeah, that's the answer. Okay, and finally, let's see. I guess I have like 10 minutes or so. Okay, we can play a similar game with the 4-point function. Now this is not universal. This is just for free fields, where I will assume that the 4-point function. Well, I mean, if I assume that if the field is free, then the 4-point function will be a sum of different terms that come from different weak contractions of the boundary of the bulk field, and each of them can be written in this way. So I have 4 insertions, and in the bulk they come from different ways of weak contracting them. These two are easy to compute because the Hamiltonian commutes with this bilocal. Essentially, well, okay, that's just a true fact. So in a sense, the energy propagating here and the energy propagating here have to be the same. So there are really 3 independent energies. But this one is more complicated. There is not really any constraint, and the energy propagated in the four legs can be arbitrary. And this is more interesting, and I think I will have to skip this, but this is the one that leads to the chaos behavior in the OTOC. Okay, instead of looking at that, let me focus on term by term by imagining that you have different operators, so that singles out one particular contraction, and we can look at each of them individually. So this is the case without this crossing in the bulk. And the answer here is a very simple generalization of the 2-point function. As I said, in principle, we have E1, E2, E3, and E4.
well, in general, let me write the more general answer, where I integrate over the 4 energies independently, where this d mu is the density of states. These are the usual time propagation factors, where I have e to the minus delta t, and then this is the energy in each channel. And then I will rewrite the 4-point function in terms of this fixed energy amplitude, where the energy is labeled by case. Then for this diagram, I said that because the bilocal commutes with the Hamiltonian, E2 is equal to E4. And this is the answer. So this amplitude at fixed energy is proportional to a delta function of E2 and E4. And then the rest are just essentially a product of two 2-point functions. So the first one is a 2-point function of these 2 operators. It depends on K1 and K2. And the other one is the product of the other pair of operators. So, okay, this is what I put here. So this is these 2. And this is the other fixed energy 2-point function. So it has a very simple formula. And this is why this is kind of a the boring contribution. Okay, one can check again that this is at large C gives you the conformal answer. Let's skip this. Okay, and then finally we have this more interesting OTOC. Okay, in this case the answer is much more complicated. There is no energy conservation in the sense that the 2 energies are different. There is no delta function, and I'm just writing it to show you that there is a formula that is known, but of course it's kind of ugly. Not much you can learn from just looking at it in a couple of seconds, but it involves this complicated integral over this variable u, and it is what it is. And this u has a particular contour of integration. One can make some checks. Let me skip this. Well, this check is just that if you take delta to be 0, then this reduces to sorry, if you take delta 1 to be 0, then this amplitude reduces to the 2-point function for delta 2. If delta 1 is the identity, then this 4-point function should reduce to a 2-point function. This is just a check. Okay. Yeah, maybe in the last, maybe I will make some comments about. How much time do I have? Is it done? 10 minutes. Okay. Okay, I will finish with some comments about quantum chaos, and it shouldn't take too long, hopefully. Okay, I will try to be quick. So the more interesting limit of this 4-point function is the out of time order correlator. Here it means that we take in Lorentzian time a correlator where we insert an operator at time c, then at time t, then 0, then we go back to t, and then we go back to 0. And this ordering appears when you want to compute the double commutator, which is the commutator between an operator inserted at 0 and t squared. The motivation to compute this commutator is that this should be a signature of chaos about how the perturbation generated by delta 2 gets scrambled in the dual quantum system observed by as measured by another operator delta 1. So in a chaotic system, this double commutator will grow exponentially, and that defines the Lyapunov exponent. But in gravity, this is a 4-point function that is computed by a scattering of the 2 particles close to the black hole horizon. And if the time separation is very large, then they will be highly redshifted, blue shifted, and the interaction will happen at very high energies near the horizon.
Gravity that way? I mean,
sorry, what do you say?
I mean, the gravity computation rules. I mean, can you motivate why is it given that way?
You mean why this is given by this?
Yeah, yeah.
Yeah, so, well, let's look at the OTOC. You can think of these 2 operators as creating the initial state and these other 2 as creating the final state. And then the overlap is the S matrix near the horizon of that. Yeah, so it's, sorry, the calculation is not the double commutator, but just the OTOC.
Yeah.
Yeah, I think that would take me a little bit to explain, but maybe I can tell you later. But,
okay.
But yeah, you just interpret this 4-point function as an inner product between 2 states, each created by this pair of operators.
Okay.
Yeah.
And now, let me just show you how this comes about from the exact answer of the Schwarzschild 4-point function. For that, we're going to take large C. And as I said, when C is large, the integrals are dominated by large energies. So here I parameterize the 4 energies in terms of E, is like the average energy, and omega are the energy differences. And in terms of this variable E and omega, the correlator takes this a little bit simpler form, not too simple, but simpler than the previous one. So we have an integral over energy differences, and this omega can be interpreted as the energy that the particles have that we are inserting. So these are the energies of those particles that are interacting in the bulk. This delta function is the energy conservation of those scattering near the horizon. Then we get this factor, which is essentially bulk boundary correlators between the propagator, between the insertion of the particle and their propagation near the horizon where they interact. And then finally, we have this gamma function, which, if we write in terms of Kruskal momentum, has this very simple form. And what this is telling you is that essentially this is a shockwave interaction near the horizon. Yeah. So this is the result. So the physics, we are reproducing the physics that when you insert these two particles, they meet with very high energy, and the correlator is being computed by some shockwave interaction between them. In 2D, something important is that there are no literally shockwaves because the metric is always ADS2. The correct way to think about it is that the interaction is through the boundary mode. For example, even though the geometry is always ADS2, as you cross from one side of the other, the dilaton is modified. Then the position of the boundary particle is modified because the dilaton changed. And that's the way the shockwave interaction appears. So this is a little different than in higher dimensions, where in higher dimensions there is really a shockwave geometry. And this is really a bulk S matrix. Then the integral over 4 frequencies can be done exactly, and this is the answer. It depends on the 4 times. And for the configuration I wrote before, then this variable C, which is some kind of cross ratio, not really a cross ratio because this is not conformal invariant, but this depends on the time t. The scrambling time is defined as the time at which this variable becomes of order 1, so it's logarithmic in C. And there is a large separation between two important scales, the dissipation time of order of the temperature and the scrambling time of order of log C, which is log G Newton. And then further we have another scale, which is the scale of this breaking of the conformal invariance. So let me finish by just showing a plot of how the OTOC behaves that we can deduce from this exact answer. So first there is some transient behavior at a scale smaller than the separation time. After that, the OTOC decays exponentially with time with a factor given by 2 pi over beta, and this is the maximal Lyapunov exponent. So this is the Lyapunov exponent of the dual quantum system, which happens to saturate the Maldacena, Schenker, and Stanford chaos bound. So this is the initial behavior. And then when the time becomes very large, of the order of the scrambling time, then this approximation breaks down, and then the correlator decays exponentially. Sorry, one more comment. The fact that the OTOC is this constant minus something that grows with time means that the double commutator grows with time. Here there should be a square. So the double commutator, no, not the commutator, but the double commutator is growing with time. Sorry. Okay, after the scrambling time, this decays exponentially, and this comes from tails in the wave function of that propagates the particles from the boundary to the bulk where they meet. It's not really sensitive to the high energy interactions near the horizon. At some point, these tails dominate, and they decay according to the same quasi-normal modes that control the 2-point function. And then at very, very long times of order 1 over C, then the OTOC goes to a power law, which is the analog of the t to the 3 that appeared in the 2-point function. And again, this is a quantum effect that is becoming large. Finally, this is the last slide. These are the diagrammatic rules, so we can write any correlator as you draw a circle, then you write the bilocal lines that connect the different weak contractions, And then each external line is an energy. Each vertex where a bulk meet the boundary has this. One has to insert this vertex function that is essentially the absolute value of the matrix element of the operators. And whenever two bulk lines meet, you have to insert this very complicated function, which happens to be the 6J symbol of SL2R. And when we computed this was more like well, we expected that it should be a 6J symbol, but we didn't put it by hand. This is based, the expectation was based on this BF understanding of JT gravity. But anyways, this actually is very important in something I might mention in the last lecture if I have time in connection with wormholes. Okay. Well, okay, this I can say quickly. So one can also study one-sided states where one inserts particles that are interpreted as end of the world brain. So one can create one-sided black holes. And the wave function can be computed from these correlators. And so this is an example for what is the partition function with such boundaries. This is dual to these one-sided black holes. Let me skip this. And then finally, okay, this is really the last thing I will say. One can also compute partition functions over not matter correlators, but also defects, where one inserts conical deficits in the bulk. And I'm not going to go through the details, but it essentially reduces to the same type of Schwarzschild and path integrals that I described before. One can do a similar calculation when one adds geodesic holes to ADS2. And finally, well, here I listed some of the methods that have been used to find these correlators. This free particle approach that I mentioned before, the one we used with Thomas and Herman, and finally the particle magnetic field approach by Kitaev, Su, and Yang. So you can find those references, the derivations, if you're interested. Okay, I think I will finish with this. Thank you.
Okay, we have some time for questions and discussions. Any further questions?
So you got very impressive result about the 4-point functions, but what is the take-home message out of this expression?
Well, I tried to illustrate some things one can derive from it by looking at the OTOC and the late time behavior. So in a sense, that's what I was describing in the last slides. That's one thing. One can, it's just a very explicit system where one can solve things exactly and study the physics that would not be available in higher dimensions. For example, even classically computing this Schwarzschild, computing the shockwave interactions classically in higher dimensions is very difficult. If you try to compute the analog of the OTOC in higher dimensions, it was like one can show that it has to have this Lyapunov behavior, but similar formulas are not really easy to derive.
Right. So could we go to the just the integral expressions where you have a lot of gamma functions at the I mean numerator? Yeah.
This
right.
one.
Yeah,
Yeah,
that's
this
fine.
is the
Yeah. So, I mean, apparently there are lots of, I mean, the poles of the gamma functions. So, is there any physical consequence out of this singularity?
Yeah. So that's essentially what I was describing in the example. So for example, when I wrote this formula, let me see. This formula that I said that this describes the shockwave interaction in the bulk, this comes from a particular pole in that integral over U. So there is a, let me go back. In this integral over U, there is a pole, I think it's this one, I don't remember, I can check. There is one pole that dominates in the classical limit, and the residue at that pole gives you the shockwave S matrix.
Shockwave.
Yeah. So that formula I wrote before comes from evaluating just one of these poles. Then what the physical interpretation is of the other poles, I don't know.
Okay, thank you.
Sure. But yeah.
Okay, any other question?
So you said in supersymmetric case, the spectrum is completely different. So 2-point and 4-point function will be modified, right?
A little what?
2-point function for supersymmetric case is different.
Yeah.
And also 4-point function
Yeah.
will be very different. So what's the difference? I mean,
Well, I mean, the difference is that the theory is different. So if I have supersymmetry, I need to also include fermion modes that come with the Schwarzschild. They are not negligible. So it's not doing supersymmetry is not only changing the matter spectrum. It also changes the Schwarzschild mode, and the contribution of these fermions can change the answer. Just something completely different. There is not much that is known. So, for example, one can study n equals 1 JT, and in that one, the 2-point function is known, but not the 4-point function, I'm pretty sure. But that one is kind of boring. It's more similar to the bosonic one. But then one can study n equals 2 or n equals 4 JT. And those are the ones that are more interesting because they have R-symmetry groups. And also they are the ones that arise from the black holes in n equals 2 JT is the one that describes the black hole in ADS. And n equals 4 is the one that describes black holes in 4D supergravity. And yeah, not much is known. The only thing about correlators, I think there was a paper by Maldacena, Lin, Rosenberg, and Shan from the summer where they compute the 2-point functions for n equals 2 JT. And I think that's as far as people went because the theory gets more complicated. Even if we do supergravity, we're not computing protected quantities. So if you add supersymmetry, it gets actually even more complicated. It doesn't get simpler. So only the 2-point function is known.
Okay, any other questions? Okay.
This is just for curiosity. So when K1, K2, K3 satisfy some partial conservation, or K1 plus K2 plus K3 equals 0, gamma has the pulse and the real line. And is there anything special happens when these poles are really on the real line? Then it means that there is a non-decaying mode there and maybe some interesting.
Yeah, I don't know. I will have to look at it. I don't think that yeah. But usually here you're integrating over K. So because this is has measure, well, yeah, it's difficult to see whether how much that contributes, but.
Then the case where you have an imaginary part, which is you have a decay there, while if it's touching the real line, you don't. So, actual resonance should be there. So, maybe some kind of real scattering there.
I don't know. Let me see. For example, did I write it down? No. Well, I was just going to say that in this example where one of the delta goes to 0, there is one pole that dominates and it's not in the real axis. So I don't know the general answer to your question, but I know examples where there are other poles that are the important ones. So I don't know. I think it's just not that. It's very non-trivial what happens after you do all these 5 integrals. It's hard to see. Yeah, I don't have a good answer. Sorry. Yeah.
Okay.
So in the case of these near extremal black holes, you say like I have to interpret the shockwave computation as really being mediated by some Schwarzian.
Yeah.
But how do I interpret it for like say like just a Schwarzschild, not an extremal black hole or something with a near.
Well, if the black hole is not extremal, then the JT is not a good description.
JT is not a good description, but it's there. I'm trying to match. How do I it seems to be a boundary mode here, but there it seems to be like really gravitons propagating and so on.
Yeah, well, okay, yeah, you can think of it in a resumming iconal, gravitons iconally. But from the perspective I had in mind, this is coming from the back reaction on the metric. The metric is really different in the shockwave.
No, but what I'm wondering is, would you say even in non-extremal geometries there would be a boundary mode kind of interpretation?
No. There is really the shockwave geometry that is giving the scattering.
But
so the geometry is different. What I'm saying is that in 2 dimensions there is something special, which is that the geometry is always ADS2. But for example, even in the near extremal case, as I said, the interaction of the boundary graviton comes from the change in the dilaton. And in higher dimensions, the dilaton is part of the metric. So that's one way to connect what I said in 2D to 4D. Because in 4D is really...
But in this picture, the whatever is being exchanged seems to be away from the horizon and so on, right? Like, because it's a boundary mode.
Well, the whole ADS2 is close to the horizon.
Whole ADS2.
If you think of Reisner-Nordstrom, you should think of the whole ADS2 as being, in that sense, the horizon of the charged black hole.
Yeah, maybe I want to rephrase. Like, so if there's no, even in the non-extremal case, like say a chargeless black hole or something, I shouldn't expect a similar boundary kind of.
No, I mean, you should expect the shockwave to produce a maximal Lyapunov behavior anyways. But yeah, you should not expect the origin to be a boundary model in any sense.
Okay.
It's really the metric that is back reacting and changing.
For further questions, you may ask over the dinner. So let's thank the speaker again.
Thank you.
And we may have an announcement from the organizer.
Yeah, I guess now Dino box may be ready out there, so we do something similar to lunchtime. Okay, thank you.